Okay. So, all right. Very good evening, all. So, in the yesterday's session, we discussed the other switching devices. Let us discuss the last two numericals from the first chapter. And after that, we'll be discussing about the second chapter, that is the AC to DC converters. So, let us first read it. This numerical is regarding the parallel connection of the MOSFET. Okay. As we know, the MOSFET is a device which is having a PTC, that is a positive temperature coefficient. Okay. So therefore, for the parallel connection, the MOSFETs are generally preferred. Why the SCRs are not preferred, that thing we already discussed in the previous sessions, right? Because SCR is having a negative temperature coefficient, and suppose if SCRs are connected in parallel, and if the load increases, then definitely the current flowing through the SCR increases, and if the current flowing through the SCR increase, due to that more power loss will be taking place, and due to the more power loss, more heat will be generated, and the temperature of the SCR increases, and due to that, as it is a NTC, na, negative temperature coefficient, so if the temperature of the SCR increases, its resistance decreases, right? And if the resistance decreases, then again what happens, the current flowing through the SCR will further increase. So that was causing the problem. But by a effective cooling method, right, nowadays also we are using the SCRs in a parallel, right? So let us discuss this numerical. Two MOSFETs which are connected as shown in the figure carry a total current of 30 ampere. Okay, so they have given the total current is 30 ampere. Total current is a 30 ampere, right? Next, the drain to source voltage of MOSFET M1 is a VDS1 is equal to 4 volt, and MOSFET M2 is VDS2 is equal to 4.5 volt. Find the difference in current delta I sharing if the current sharing series resistances are RES1 4.5 ohm and RES2 0.3 ohm. Okay, so this is the data they have given. So here what this current 30 ampere indicates, this 30 ampere current is nothing but total current I. Okay, so let me first write it as, yes, total current I is nothing but I1 plus I2. Na, simply apply KCL here, we'll be getting I is equal to I1 plus I2, but I is 30 ampere, na, right? So let me write it as I is equal to I1 plus I2. Again, total current I is 30 ampere, so 30 is equal to I1 plus I2. Consider it as equation 1, right? Next, now what this VDS1 and VDS2 tells, yes, VDS1 indicates, yes, if you check, this is a MOSFET we are having, so here it is a drain terminal, here it is a source terminal, right? So VDS1 is nothing but, yes, let me indicate, VDS1 means voltage across these two terminals, VDS1. Similarly, for the second MOSFET, the voltage across these two terminals is a VDS2. Are you getting the point? Let me indicate it as a, here this is a VDS2, drain to source voltage, right? Now you can check these two are connected in parallel. So can we say that voltage across this branch, this full branch I am saying, voltage across this full branch is equal to voltage across this full branch, right? What is the voltage across this full branch? Can we write it as a, yes, it is equal to VDS1 plus I1 into RS1. I1 into RS1 is nothing but voltage across the resistance RS1. Okay, and voltage across MOSFET is VDS1, right? So can I write VDS1 plus I1 into RS1? That should be equal to VDS2 plus I2 into RS2, right? So let me write it as VDS1 plus I1 into RS1 is equal to VDS2 plus I2 into RS2. Yes or no, right? Next, further they have given VDS1. What is the VDS1? It is a 4 volt. 4 plus I1 we need to find it, right? So I1 into RS1. RS1 they have given, it is a 0.4. So let me write it as 0.4 into I1. That is equal to VDS2. It is a 4.5. So 4.5 plus RS2 into I2. RS2 is 0.3. 0.3 into I2. So from this, we can form a difference, one equation, right? So it is like a 4, let me take this term, sorry, this term to the left hand side. So 4 minus 4.5, so it is a minus 0.5 is equal to minus 0.4 I1 plus 0.3 I2. Yes or no? This is your equation 2. Now can we solve? We are having two equations now and two unknowns, I1, I2. These are the two unknowns and we are having two equations. So can we solve these two equations? Yes. So if we solve these two equations, we'll be getting solving. Let me write it as solving 1 and 2. Yeah, solving 1 and 2. How to solve the equations, right? I'm considering that you will be knowing how to simplify these equations, right? Okay. Simply, if you multiply this equation 1 with a 0.4, you will be getting it as 0.4 I1. Here it is minus 0.4 I1. Then you can add the equations. You will be getting the I1 and I2 value, right? So I1 is 13.57 ampere. 13.57 ampere. And what is the I2? I2 is equal to 16.42 ampere. 16.42 ampere, right? So this is the I1 and I2 we are getting. But our task is not to find the I1 and I2. Our task is to find, yes, difference in current sharing. Okay, that is the delta I. We need to find. Okay, so how to find the difference in current sharing is I2 minus I1. I2 is more, I1 is less, na, right? So we can write difference in current sharing. Either we can find it in terms of ampere or we can find it in percentage also. Okay, so let me write. Therefore, percent difference in current sharing is equal to I2 minus I1 divided by total current I into 100. So if you check, it is equal to 16.42 minus 13.57 divided by 30 into 100, right? So if you simplify it, we'll be getting it as equal to yes, it is a 9.5. Okay, 9.5%. 9.5%. Is this clear? This is a percentage difference in a current sharing. Okay, and this is the final answer. Is this clear? Right, 9.5. Okay, sir, can't we do by current division rule to find the branch currents? My friend, when generally we use the current division rule, only the resistance or the impedances will be present, na? If you, yes, suppose if I use the current division rule for these two branches, right? It is like this is here we are having the voltage drop, here it is also voltage drop. So I cannot directly blindly use that current division rule here. Are you getting the point? Right? So if the only registers are present, then in that case we can use the current division rule. Okay. So this is the final answer. Next, let us discuss the next question. Yeah. Yes. This is regarding again the on state power loss and the off state power loss, or turn on power loss and the turn off power loss, right? During the transition period. So let us read it. The IGBT insulated gate bipolar transistor used in the circuit has the following data: T on, right, 3 microsecond. On time they have given T of 1.2 microsecond. Duty cycle D is equal to 0.7. D is equal to 0.7. VCE saturation is equal to 2 volt. Okay. And Fs is equal to 1 kilohertz. Now in the yesterday session, we discussed about the IGBT. If you recall it, when IGBT, when the operating point is in a cutoff region, then we can say that the IGBT is operating in an off state, right? And if the operating point is in a saturation region, okay, then we can say that the IGBT is in an on state. Okay, so that's where specifically they have given VCE sat. VCE sat means what? When IGBT is acting as an on state, what is the voltage across collector and emitter? That indirectly they have given the voltage drop, that is the on state voltage drop of the IGBT. It is a 2 volt here. Okay, switching frequency is 1 kilohertz. What are the switching power losses? Yes, switching power losses during turn on and turn off, that we need to find. Okay, so switching power losses is nothing but your energy loss, okay, into your switching frequency. That is the sorry, turn on time or the turn off time respectively, we need to find. So let us first understand this question. Right, so suppose when IGBT is in a on state, when IGBT is in a on state, right, means which mode of in which region our operating point should be? The operating point should be in a saturation region, yes or no, right? So consider this voltage is VCE, okay. So when IGBT is in a on state, it is like it is acting as a closed switch, it is acting as a closed switch. Consider this current is a IC, consider this current is a IC, right? So let me write, when IGBT is in on state, is in on state, okay. So if IGBT is in a on state, right, so it is like IGBT is operating in which region? Saturation region, okay. Can we apply KVL to this outer output loop, right? KVL to output loop, KVL to output loop, or the output side you can say, okay. It is a VCE plus VCE, right, minus IC into REL, minus IC into REL, right, minus VCE saturation we need to consider, right, because IGBT is in on state means what? It indicates that your operating point is in a saturation region, na? Right? So we need to write it as minus VCE saturation. This is very, very important. And this is equal to 0, right? So now what is the meaning that VC saturation? It is like a on state voltage drop of our IGBT. Okay. Next, put the values here. It is a 200 minus IC into what is the REL? It is a 10 minus what is the VC saturation? It is a 2 is equal to 0. So therefore we can write it as a 198 is equal to IC into 10. So therefore IC, if you check, it is equal to 198 by 10. So it is a 19.8 ampere. This is the current which is flowing through the IGBT, or the current in the circuit, or we can say the current in the load even, okay, when IGBT is in a on state, when IGBT is in a on state, right? So it is a on state current actually, right? On state current, that is a steady state current final, okay, when device is in a on state. It is a 19.8 ampere. Next, when IGBT is in a off state, when IGBT is in a off state, at that time what happens? At that time the device current will become 0 only, na, right? Device current will become 0, yes or no, right? So when device current is 0, when device current is 0, so can we say that voltage across device is equal to VCE only? Are you getting the point? Let me write here, when IGBT is in off state, yes, IGBT is in off state means what? It is like an open circuit now, okay. So if it is open circuit, IC will be 0, right? So let me write it as IC is equal to 0 ampere. So if IC is 0 ampere, okay, so therefore what about the voltage across the load? It is a IC into 10, so that voltage will be 0, now voltage across load will be 0. And if we apply KVL, we will be getting VC, that is the voltage across device, is equal to 200 volt, yes or no, right? So let me write VCE is equal to 200 volt. That indicates voltage across device, voltage across device, right? So, and current flowing through the device 0 ampere, voltage across device is 200 volt, okay. This is when off state. Similarly on state you can check voltage across, sorry, in the on state current flowing through the device is 19.8 ampere. What is the voltage across device? That is a VC set, na? It is a 2 volt, okay. Next, so now can we draw the switching characteristic, okay, during on state first, okay, switching characteristic during the on state. So let me write, yes, switching characteristics during on state, during on state. So it will be like this. So this is the time t. Consider this is a voltage across device VCE and current flowing through the device, that is a IC. Okay. Suppose from this instant the switching starts. Okay, switching action initiated. Okay, so when during the turn on or the during the turn on transition, okay, during the turn on transition, okay, switching characteristic during on means what? During the turn on transition, actually we are going to discuss. Okay, during the turn on transition, how the current is changing? Current is changing from 0 ampere to the final value. Okay, so current characteristic will be like this. Yes, current will be like this. Yeah. It will be initially 0 and after that it is increasing, and next at this instant suppose it will be reaching the final value. This final value is 19.8 ampere. This is your IC, means initially it is a 0. It is like here our device is in a off state. After this point it is like our device is in a on state. Okay, device is in a on state. So what this indicates? This indicates your turn on transition. Na? This indicates turn on transition. Okay, so let me write it as this indicates your turn on transition, means it is like a T on time because it is a time, so that's why it is a T on. So current is changing from 0 towards the final value and it is a linear. Okay, they have not commented anything, so we are simply considering it as a linear. Second thing, when IGBT is in off state, what is the voltage across IGBT? We know na, we have calculated it is 200 volt. So therefore voltage across IGBT will be 200 volt. So it is like this. Initially this voltage will be equal to 200 volt, right? This value will be 200 volt. Next, once on turn on transition initiated or turn on action initiated, after that IGBT's voltage go on decreasing. Strictly speaking, yes, this voltage should decrease from 200 till 2 volt only, because they have given the on state voltage drop of the IGBT is 2 volt now, right? But if you take it as, right, I will tell you in both the ways. If you take it as 2 volt, if you take it as a 2 volt, I'm saying, I'm considering now I have I'm showing it as to the 0 volt. That is when IGBT is in on state, I'm considering it as a 0 volt. But strictly speaking, as per given data, yes, it should be changing from 200 volt to the 2 volt only, right? It should not reach 0. But if you put that 2 volt here, if you consider that 2 volt here, and if you simplify that curve, and if you simplify that power loss, then your option will not match. Actually, this question they have asked in one of the PSU, state level PSU examination for 1 mark. Okay, so if you consider it as a 0 volt, then and only then your option will match, right? If you consider it as like from here to 2 volt, then the answer correct option or the you will be getting correct answer. But in the options, that answer is not there. Okay, means simply what they are expecting that you can neglect the on state drop. You can neglect the on state drop. Are you getting the point? I'm repeating. Strictly speaking, when IGBT is in an on state, the voltage across the IGBT should be equal to 2 volt as per given data. As per given data, it should be equal to 2 volt. But we can solve for 2 volt also by considering the on state drop of 2 volt also we can solve. But if you solve like that, you will not get the option, right? You will be getting the answer, but that answer is not there in the given options. Okay, and I am saying that this question they asked for the 1 mark and they are considering that, right? They have not mentioned anything in the question, but they are considering that, or they are assuming that you can neglect this drop. Okay, so right. So next, so it is like this decreasing and here it is 0. So what is this? This is your VCE. This is your VCE. Okay, this is during on state. Yes or no? That is the turn on transition. Now, can we find the power loss during the turn on transition? Can we find the power loss? Yes, we can find now, because one is decreasing, one is second, one is increasing. We know the expression for the energy loss. From the energy loss, we can find the power loss, right? So let me write it as power loss during the turn on transition. Power loss during the turn on transition. Let me write here power loss during turn on transition. Turn on transition. Yes, it is a first thing is 1/6 into this voltage, it is a 200 na, into this current, it is a 19.8, into turn on time. What is the turn on time? Let me write it as a T on, into our switching frequency, right? Because I am writing directly for power na. Okay, for energy if you write, then here we need not to consider the switching frequency. Okay, for power if we want to write, then we need to consider the switching frequency also, right? So let me write it as a switching frequency, Fs. So you can check, it is a 1/6 into 200 into 19.8 into what is the turn on time they have given? They have given it is a 3 microsecond, right? So 3 into 10 to the power minus 6 into what is the switching frequency? It is a 1 kilohertz. So into 1000. So from this, if we check, this is equal to yes, it is a 200 into 19.8, right? Into 1000 into 3 into 10 to the power minus 6. Okay, divided by 6. So it is a 1.98. Yes or no? 1.98 watt. This is your power loss during turn on transition. This were, yes, simplified, or were calculated by considering the on state drop is equal to 0 volt. But as per the given data, it is expected that yes, the on state voltage drop is non-zero now, because they are saying that it is a 2 volt. Okay, but if you put it as here, if you draw the plot like this by considering as a 2 volt here, then the thing is we need to write the expression for this curve, right? And after that we can write the expression, even we can solve for the power loss also, but that answer will not be there in the options. Are you getting the point, right? We simply, they are saying that you can neglect it. Okay, so it is a 1.98. Next, yes, second, during the off state, let us find. Okay, during off transition, turn off transition. Yes, during turn off transition, during turn off transition, so yes, VCE and IC, right? During turn off means, suppose here we are having the switch is in a on state. Okay, switch on state means current is high, voltage is 0. Okay, so current is high. So let us consider, yes, the current flowing through the device is a high current, and voltage across the device is a 0. So it is a 0, right? So this is your like a IC, and this is a, or let me write it as a VCE. Okay. Next, once the turn off transition initiated, okay, turn off process initiated, yes, voltage across device go on increasing, current flowing through the device go on decreasing. Okay, so let me write here, yes, voltage across device is increasing from here. Okay, suppose till this we are having the turn off transition. Okay, and it is like after this our device is in a off state. So here this voltage we are having final voltage, and how is the current? Current will be like this, decreasing to the 0 value. Okay, IC and VCE, right? Next, now again it is a linearly decreasing, one is linearly increasing. What is this value? This value is equal to 200 volt now. What is this value? This is equal to, we have calculated during the on state, it is a 19.8 now, right? 19.8 ampere current is flowing, so it is a 19.8 ampere. Okay, now can we find the power loss again? So power loss during off transition is equal to 1/6 again, right, into 19.8 into 200 into turn off time into switching frequency. Okay, so it is equal to 1/6 into 19.8 into 200 into what is the turn off time? Turn off time is equal to 1.2 microsecond. 1.2 into 10 to the power minus 6 into switching frequency, it is a 1000. So if we check, it is equal to 19.8 into 200 into 1000 into 1.2 into 10 to the power minus 6, right? 0.792, 0.792 watts. This is your P off. Is this clear? Right? So if you check the options, 0.792 and 1.98. So 1.98 and 0.792. So option C is the correct option, right? Okay. Next. Okay. Yeah, I will solve it by taking the 2V also, right? This is only for your understanding, by considering the on-state voltage drop of 2 volt. By using that also, I am going to solve it. Okay, but here this is only for the understanding purpose. Okay, so let me solve it by using the by considering the on-state voltage drop of 2 volt also. Okay, so this is the additional I am saying. Okay, additional I am saying. Yes. So if on-state drop means voltage drop of 2 volt is considered, then how it will be? Yes, characteristic we can draw. Time t 0. Let us first simplify for the turn on transition. Okay, so turn on transition. So let me write it as a turn on transition. Means it is like device is in an off state here. Okay, VCE and IC. Device is in off state means it is like a VCE will be high, right? Okay, it is a 200 volt. After that it is decreasing na, to 2 volt only. It will be decreasing up to 2 volt. It will not reach the 0. So it is a 2 volt here, right? This voltage is a 2 volt. Is this clear? This is your turn on transition. Okay, and this is like your on time. Okay, turn on time, and this is a device is in a on state. Okay, next, how the current will change? Current will change like this. From 0, it will start increasing, and again it will reach the final value. What is the final value of the current? It is a 19.8 now, we know. 19.8 ampere. Okay, so this is for VCE. This one is for IC. Okay, next, now you cannot use that 1/6 expression here. Please be careful. Whatever the expression we have written here, 1/6 into, yes, this magnitude into this magnitude, this expression is not valid. Okay, in this case, because you can check here, it is not reached to the 0 value, right? It has not reached to the 0 value. So we need to write the expression for this VCE. Okay, I will show you only how to write the expression. After that, only the integration part is there. Okay, that you can simplify at your own. Okay, so how to write this expression for VCE? Let us discuss. So VCE expression, whether it is a increasing or decreasing, it is a decreasing. It is a linearly decreasing, na, right? So slope is a negative, right? So slope is a negative. So simply we need to put, let me write it as a VCE is equal to slope negative. Slope means what? It is a change in y divided by change in x. So you can check corresponding to the t on time, right? How the voltage VCE is changing? It is changing from 200 volt to the 2 volt. Okay, so what is the change? It is a 198. Okay, so 1 is the minus because slope is negative. So it is a 198. That is the change in y actually. Okay, because on y axis, let us, we are having the VCE. Okay, so voltage VCE changing from 200 volt to the 2 volt. So that's why it is a like here initially is a 200, finally is a 2 volt. So difference, if you check, it is a 198. Okay, and minus definitely. Divided by change in the time is t on. Change in x means t on here. Change in time. Okay, into t plus the initial voltage. It is a 200 volt. Plus the initial voltage. It is a 200 volt. Right. So is this clear? Now you can check here. If t is equal to 0, t is equal to 0 means this point. So if you put here t is equal to 0, this term will become 0. Vc will be equal to 200 volt only. Okay, 200 volt only. Let me write it as only 200 here. Okay. Next, as time increases, you can put here t is equal to t on. If this is t is equal to 0, t is equal to t on means this time. Yes or no? This instant. So this particular time is a t on. If you put here t is equal to t on, this will get cancelled. 200 minus 198, you will be getting 2 volt only. Okay, this is the VCE. Next, we can write the expression for IC also. How is the expression for IC? It is simple, na? Linearly increasing, slope is positive. Okay, so change in Y, it is a 19.8 divided by change in X, that is a T on into T. So this is your VCE, this is your IC. So now from this, we need to find, yes, total power loss. Total power loss we can find. How to find? So let us first write for the energy loss, and after that you can simplify it for the after that we can simplify for the power loss also. Okay, so energy loss during the turn on transition, that is a T on, is equal to, yes, it is a integration, okay, over 0 to T on, integration over 0 to T on, it is a VCE into IC into dt. Integration of power is nothing but energy, na? So what here we need to replace the VCE with this expression, IC with this expression, and next we need to simplify this one. Are you getting the point? From this you can get the energy loss, and if you multiply that energy loss with the frequency, you will be getting the power loss. Okay, so you can try it at your own. Similarly, you can get the PT on. PT on means like on transition power loss. So it is a ET on into frequency, into switching frequency, right? So you can simplify this, and if you check, the options will not match, right? So simply they are expecting that we should neglect it. Okay, but they are not mentioned anywhere whether you can neglect on state voltage drop and those things. Okay, but they are assuming that you can neglect. Okay, so like this. So friends, this is about the first chapter. Okay, switching devices. We have done the detailed analysis. Lot of concepts are there regarding the your SCR. Okay, and after that other switching devices. Let me add few points. Sometimes they have asked the theoretical questions like, right, SCR is a dash controlled switch. Suppose the question is like SCR is a dash controlled switch, and suppose the options are like voltage, current, charge, and the last option suppose none of these. Okay, voltage, current, charge, and last one is suppose the none of these. Okay, so please keep it in mind. SCR is a charge controlled device. Strictly speaking, SCR is a charge controlled device. Okay, why it is a charge controlled device? Because by considering the gate triggering method blindly, we can say that it is a current controlled. But if you check in the SCR, we are having the 5 different turn on methods. If you check for those 5 different turn on methods in a forward voltage triggering, what we are doing? We are maintaining the voltage in a high voltage, right? So by considering the forward voltage triggering, can I say that the SCR is a current controlled? No, we cannot say SCR is a current controlled, because in the first triggering method, that is forward voltage triggering, it is like we are increasing the forward voltage across the device. Okay. Second method, we are having the gate triggering, we are increasing the gate current. Okay, we are circulating the gate current. Third method, we are having the dV by dt triggering. In the dV by dt triggering, we are changing the dV by dt. Fourth method, temperature triggering and the light triggering. So overall, if you check, yes, in all the 5 methods, particularly what we are doing, yes, we are controlling the charge only, na, right? Because if you check gate triggering also, we are circulating the gate current, means what? We are injecting the charges only, na, right? So SCR is a charge controlled device. But suppose sometimes they have asked the question like this, SCR is a dash controlled device, and in that they have given the option like a charge, then definitely you need to tick the charge only. Second, suppose same question, SCR is a dash dash controlled device, and if the charge option is not there, then we need to go for that current. We need to go for the current. Are you getting the point? Please get it clear. Please get it clear. SCR is strictly speaking, it is a charge control device only. But in the option, if charge is there and current is also there, then we need to select the charge only. But suppose same question they have asked, and if the charge is not there in the option, only voltage, current, and remaining two options are different options. Okay, then we need to tick for yes, current. Are you getting the point? Because current is nothing but your again rate of flow of charges only. Okay, so please keep it in mind. Okay, so SCR is a charge control device, but if in the options, if charge is there, well and good. If the charge is not there, we need to tick on the current. Okay, next, some students are having some confusion like why the BJT is a current control device. You can check the BJT operation. BJT, in the BJT, what we are doing, we are changing the base current na? And accordingly our device is switching from on to off and off to on. You can check the output characteristic, you will understand. BJT is a current control device. MOSFET is a voltage control device, because in the MOSFET what we are doing, we are applying the VGS voltage na, across gate and source terminals. We are maintaining the voltage, high voltage. But due to that high voltage, whether the charges are entering, whether the charges are injecting into the device structure, no. Because the gate terminal in the MOSFET, if you check the construction, the gate terminal is isolated na, from the device structure. And between gate terminal and the device structure, we are having a SiO2 layer, silicon dioxide layer. Yes or no, right? So that's why keep it in mind. Okay, we are only changing the voltage, but the charges are not injecting into the device. Okay, so that's why it is a voltage control device only. Okay, MOSFET. Similarly, IGBT you can check, because channel is forming there na, in the MOSFET. Similarly, in IGBT also, we are having the N-type channel will be there formation. Okay, so IGBT is also voltage control device. VC is the voltage. VGE, get to emitter voltage. Okay, that voltage is controlling the operation of the your IGBT. Okay, GTO is a fully controlled switch. Okay, GTO can be turned on by using the gate signal only and turned off by using the gate signal only. Okay, so GTO is a current control device. GTO is a current controller device. Are you getting the point, right? So these are some of the points. Okay, they may ask, sometimes they have asked these questions. Okay, right. So next, let us move towards the next chapter, that is the rectifiers. It is also known as a AC to DC converters. Okay, AC to DC converters. So right, let us put the heading rectifiers or AC to DC converters. Very important chapter. In this chapter, we are going to discuss, yes, uncontrolled rectifiers, controlled rectifiers, single phase, three phase, right? In the single phase, half wave, full wave rectifier. Okay. In the three phase also, half wave rectifier and a full wave rectifier. In a full wave rectifier, again, we are going to discuss the center tapped transformer configuration, bridge configuration. In the bridge, again, we are having the two two configurations. One is the semi-controlled and second one is the fully controlled. Okay, fully controlled and semi-controlled, or you can say the half controlled. Okay, semi-controlled or the half controlled. So AC to DC converters, right? So strictly speaking, this is a converter which converts AC voltage, AC to DC converter, where input is a AC. You can say the fixed AC, and output is either it is a variable DC or fixed DC. It depends on whether your converter, okay, is a controlled converter or uncontrolled converter. Okay, so I am writing in general it as a output is a DC. Output is a DC. Okay, if, let me write it as, yes, for uncontrolled controlled, uncontrolled converter, or you can say uncontrolled rectifier. Output will be fixed DC. Fixed DC. Okay. And if we are having a controlled rectifier, then the output will be your controlled DC, or you can say the variable DC. Controlled DC or variable DC. Okay. Now, what is the difference between uncontrolled rectifier and controlled rectifier? Uncontrolled rectifier means the rectifiers where we are using the uncontrolled switches, just like a diode. Okay. So diode rectifiers are your uncontrolled rectifiers, right? Why these are known as uncontrolled rectifier, we are going to discuss. Okay. Controlled rectifier means where we are using the controlled switches, just like your SCR. Okay. SCR is the most popular or the popularly used in these AC to DC converters, right? Next, where these AC to DC converters finds their applications, you can check where the circuitries in which we require a variable DC supply, right? In those circuitries, yes, generally the rectifiers are used. In industry, if you check in a paper mills, in a textile mills, okay, generally the rectifier is required. If you check, we're having a traction system based on a DC, okay, traction system based on a DC. In that case, also the rectifier is required, right, to run, to provide the supply, okay, to the DC motor. Next, again, you can check the HVDC system, okay, HVDC transmission. In the HVDC transmission, we already discussed during the introduction of this subject, okay, that in the HVDC we require at one side we require a rectifier, and at the second side we require an inverter. Okay, so in HVDC transmission also these converters finds their applications. Okay, so also DC motor drives also, right? In DC motor drives, yes, these converters finds their application, right? So now one by one let us discuss the circuitries and which loads we are going to consider are R load, RL load, RE load, that is the battery charging circuit, right? RLE load, okay, RL load with freewheeling diode and so on. Okay, so let us put the heading single phase half wave uncontrolled rectifier, okay, with purely resistive load. So single phase half wave uncontrolled rectifier with, yes, purely resistive load, with a purely resistive load. Okay, so single phase half wave uncontrolled rectifier means definitely the diode will be there. Okay, and load we are going to discuss R load. After R we will discuss the L load, and after L we will discuss the C load. Okay, pure capacitor, pure inductor. Okay, so let me draw the circuit diagram. Single phase AC supply. This is a diode, and here it is a purely resistive load. So this is the VS, diode D. Consider voltage across diode is a VD. Current flowing through the diode is a ID. Consider source current is a IS. Here it is a R. This voltage is V0. Current flowing through the load is I0. Okay. So in the waveforms, yes. First is the VS. Which is a Vm into sine of omega t, positive half cycle, negative half cycle, again positive half cycle, and next negative half cycle. Okay, so it will be continue 0 to pi, pi to 2 pi, 2 pi to 3 pi. Next, V0 waveform and I0 waveform. The V0 waveform. Okay, I0 waveform will be like this. Right? This red one is I0. And this one is a V0. Okay. So the waveform for VD, voltage across diode. Okay. So this pi, 2 pi, 3 pi. Here it is pi, 2 pi, and here it is a 3 pi. Okay. So now let us discuss the circuit operation. Okay. And why I have drawn these waveforms like this. Okay. Let us discuss. Right. So Vs is the single phase AC supply, which is equal to Vm into sine of omega t. Okay. So it is a pure sinusoidal supply we're having, right? Vs is equal to Vm sine omega t. So we're having a pure sinusoidal supply. You can check if it is a Vm sine omega t means what? 0 to pi. Sine 0 is 0, sine pi is 0. Between 0 to pi, the sine values are, you can check, sine 30 degrees, sine 60 degrees, sine 90 degree. Okay. 120, 150, etc. Okay. So those values will be positive only. Okay. So we're having Vs is a positive half cycle during 0 to pi. During pi to 2 pi, sign of that value will be negative. So that's why here it is a negative half cycle. Again positive half cycle, again negative half cycle. Okay. So we're having a Vs is a purely sinusoidal voltage. Vs is a purely sinusoidal voltage waveform. Okay. At omega t is equal to pi by 2. If you check at omega t is equal to pi by 2, it will be having a peak value. No? It will be having a peak value. And what is this peak value? It is a V max. So here Vm indicates the peak value of the supply voltage, right? Next, so here you can check from the Vs waveform, we're having it is like a positive half cycle, that is a positive values, negative values, positive values. Again, after that, we will be having the negative value, again positive, again negative, again positive, again negative. Okay, so it is a continuous waveform, right? For some interval, we're having the positive values, next interval, we're having the negative values, and so on. Okay, so what the Vs positive and what the Vs negative indicates? Please listen. Vs positive means it is like a supply voltage is a positive. So suppose if supply voltage is positive, and if I consider, yes, the polarity of the supply voltage is like a plus here and minus here. Please listen it carefully. Okay, because for all the circuitries we require this. Okay. So when Vs is positive, 0 to pi, Vs is positive, and I am considering that the polarity of the supply voltage is a plus here and minus here. Okay. The meaning is this supply voltage will try to circulate current in this direction, na? Because we know for the EMF, yes, that is the electromotive force, from the positive plate, actually the current will come out, na? Right? So that's why here from positive, yes, positive polarity, the current will come out. So that's why the supply voltage will try to circulate current in this direction. So this is a plus minus. When Vs is negative, what should happen? When Vs is negative, like it is a plus here and minus here, means the polarity of the supply voltage should be reversed. Okay, polarity of the supply voltage should be reversed. So here it is plus, here it is minus, means we are considering that Vs positive, right? So during Vs negative, yes, the polarity should be reversed. Means here it is plus, here it is minus. So you can check if Vs negative means if polarity is plus here, minus here, this Vs will try to circulate current in the anti-clockwise direction, na? Right? So one is trying to, so for some interval, Vs is trying to circulate current in the clockwise direction. For second interval, yes, Vs is trying to circulate current in the anti-clockwise direction. Okay. So now let us discuss how the circuit operates. Right? So now in the circuit, if you check in the circuit, we are having diode D. So this is the supply voltage. Okay, here it is a supply voltage. This is a load, and here it is a switch we are having. Okay, so you can check here. Diode is an uncontrolled device, na? Diode is a uncontrolled device, right? So that's why, yes, controlling circuitry is not required in order to turn on the device. Whether we require the controlling signal, no. in order to turn off the device, whether we require the commutation circuitry here, no, right? So that's why in this circuit we are having only supply, that is the source, load, and a diode D, that is a switch. Okay, that is the switch, right? Now let us discuss the circuit operation. So here, when Vs is positive, that is from 0 to pi, the polarity is like a plus here and minus here. So it is like a, this is the highest potential point in the circuit, this is like a lowest potential point in the circuit. Highest potential is appearing at the anode of diode, lowest potential is appearing at the cathode of diode through the load. Okay, so you can check here. Here potential is whatever the potential here, the highest, the same is appearing at the anode of diode. Here potential is through the load, we are having this potential is appearing at the cathode of diode. So here can we say that when Vs is positive, diode D will be in the forward bias mode, because anode is at a higher potential compared to that of the cathode. So therefore diode D will be in a forward bias mode. So important conclusion, right? So during 0 to pi, okay, for omega t is equal to 0 to pi, yes, Vs is positive. Vs is positive. Vs positive means what it indicates? Diode D will be in a forward bias mode. Okay, diode D is in forward bias mode. Forward bias mode. Okay, so diode D will be in a forward bias mode. Similarly, when Vs is negative, what will happen? For omega t is equal to pi to 2 pi. For omega t is equal to pi to 2 pi, what will happen? So for pi to 2 pi, just now we discussed the supply voltage is negative. Supply voltage negative means this polarity should be reversed, right? So polarity is reversed means here it is minus, here it is plus, right? So here it should be minus, here it should be plus. So now it is like this is the lowest potential point in the circuit. This is like a highest potential point in the circuit. Lowest potential will appear at the anode of diode. Highest potential will appear at the cathode of diode. So cathode potential is higher than that of the anode. So what about the diode D? Forward or reverse bias? Come on. When Vs is negative, yes, anode potential will be less than that of the cathode, na? So diode, sorry, anode, yes, anode potential is less than that of the cathode. So diode D will be in a, yes, forward or reverse bias? Diode D will be in a reverse bias. Okay, diode D should be in a reverse bias. So please, yes, understand this. During pi to 2 pi, Vs is negative. So that's why our diode D will be in, okay, diode D is in reverse bias mode. Reverse bias mode. Is this clear? These two are very important conclusions. Okay, please keep it in mind in this circuit. I am repeating, when Vs is positive, that is during 0 to pi, polarity will be like upper, this terminal, upper terminal positive, lower terminal negative. So that's why diode D's anode will be at a more potential, higher potential than that of the cathode. So that's why diode D will be in a forward bias mode. Similarly, when Vs is negative, the polarity will be like this: lower terminal high plus, upper terminal minus. So lesser potential is appearing at the anode of diode, higher potential will be appearing at the cathode of diode. So cathode is at higher potential than that of the anode. So diode D will be in a reverse bias mode. Okay, diode D will be in a reverse bias mode. Now, yes, now let us discuss the circuit operation during omega t is equal to 0 to pi. Okay, during omega t is equal to 0 to pi. So what will happen during omega t is equal to 0 to pi? It is like a, here it is plus, here it is minus. And just now we discussed the when 0 to pi, when Vs is positive, diode D will be in a forward bias mode. Okay, so when diode D is in a forward bias mode, and as we know, diode is an uncontrolled device, it is a passive device. Okay, as soon as it becomes forward bias, it turns on. Yes or no, right? So when Vs becomes positive, that is from 0 to pi, our diode D will immediately turn on. Okay, so during 0 to pi, can we draw the equivalent circuit? Yes, during, let me draw here, during omega t is equal to 0 to pi, yes, we can draw the circuit. Okay, we can draw the circuit because Vs we are having, it is a positive. It indicates diode D will be in a forward bias mode. Forward bias means what? Diode D will be in a on state only, na? Diode is an uncontrolled switch. Okay, as soon as it becomes forward bias, it will turn on. So how is the equivalent circuit? Equivalent circuit will be like this. This is the diode which is acting as a short circuit here. Okay, Next, here we are having the supply voltage, and here it is a load. So this type of circuit diagram will be having. Okay, so you can check this is a Vs, polarity is plus here, minus here, right? This current is a Is, this is the diode current ID, this is the diode voltage Vd, load resistor R, voltage across load is V0, current flowing through the load is I0, right? Now you can check here during this interval, our diode is in a on state, means diode is acting as a short circuit, right? Now important thing, it is I am considering that, or we are considered that in this circuit we are having a ideal diode. Ideal diode means it is a diode or the device, right? During its on state, its voltage drop is a zero. Voltage drop is zero. But suppose in the numerical, if they give you the on state voltage drop of the diode is 2 volt, for example, 2 volt, then instead of this short circuit, we need to consider it as a 2 volt drop. Okay. If we'll discuss it while discussing the numerical if requires. Okay. So this is a short circuit. I'm saying this is a short circuit because diode is in a on state. Now you can check during 0 to pi, we're having this circuit equivalent. Okay. So can we say that current will flow from source towards the load through the diode? Yes or no? Definitely current will flow because diode is acting as a short circuit. Okay. So here can we write Vd is equal to 0 volt because diode is in a on state. So let me write Vd is equal to 0 volt. Vd is equal to 0 volt. That is a voltage across diode. Voltage across diode. Right? Now can we apply KVL to this loop? KVL to this loop. Yes, it will be plus Vs minus Vd minus V0 is equal to 0 now. KVL to the loop, it is a minus to plus, so that's why plus Vs. Plus to minus, so minus Vd. Plus to minus, so minus V0 is equal to 0. Out of that, what is Vd? Vd is 0, so we can say that this is a 0. So therefore, can I say V0 is equal to Vs here? Yes or no? Load voltage, V0 means load voltage. It is same as that of your supply voltage. During 0 to pi, we are discussing. During 0 to pi. Next, now V0 is equal to Vs. Vd is a 0 volt we are having. Okay. What about the I0? According to the Ohm's law, can we write V0 is equal to I0 into R? So what is the I0? I0 is V0 by R, right? So let me write I0 is equal to V0 by R. But what is V0? V0 is Vs, na? So we can write it as a Vs upon R. Okay, so this is the I0. This is the I0. Is this clear? Now I0 is Vs by R. So what about the ID and Is? Can anyone? What about the value of ID and Is in this circuit? I have written the expression for I0. What about the ID and Is? Whether those will be same as that of the I0 or different? Yes, we're having only single loop. Okay. Right? Same, correct? So here you can check ID, Is and I0 all are same, na? We are having only one loop, we are having only one path. Okay, and in this loop, we are considering 3 currents, na? Right? So all are having the same value. So let me write it as a Is is equal to ID is equal to I0 is equal to Vs by R is equal to Vs by R, right? It is a Vs by R. Yes, it is a Vs by R. Supply voltage divided by resistance. Okay. Now let us just check the waveforms during 0 to pi. Okay, during 0 to pi, we are having Vd0. V0 is same as that of the supply voltage. I0 is equal to Vs by R. So I0 will be in phase with the V0. The only thing is change in a magnitude. Change in a magnitude. Okay. Yes. So you can check the waveforms. Yes. During 0 to pi. So here it is a 0. Here it is a pi. You can check V0 is the same as that of the supply voltage. Supply voltage is like this. V0 is also like this. Okay. So this value is same as that of the supply voltage. V0 is equal to Vs. Right. Next, what is the I0? I0 is this Vs by R, na? That is a V0 by R only. Okay. So if suppose resistance value, let us consider it as a 10 ohm. If resistance value is 10 ohm, definitely I0 will be, yes, less than that of your V0, but the nature will be same as that of your load voltage. Okay. If load voltage increases, I0 also increases. If load voltage decreases, I0 also decreases, right? So next, What about VD? VD is equal to 0 volt. VD is equal to 0 volt, right? So this is the circuit operation during 0 to pi, right? Pi to 2 pi, what will happen? Let us discuss. During omega t is equal to pi to 2 pi, what will happen? Yes. So during omega t is equal to pi to 2 pi. During omega t is equal to pi to 2 pi. Okay. Pi to 2 pi. Yes, what will happen during omega t is equal to pi to 2 pi? During pi to 2 pi, if you check, the supply voltage is negative, na? Supply voltage negative. And we have discussed during pi to 2 pi, supply voltage is reversed. So it is like, yes, diode will be in the reverse bias mode. Yes or no, right? So if you check in this circuit, yes, in this circuit, supply voltage is negative, means it is like a minus here, plus here. Diode D will be in a reverse bias mode. So when diode D is in a reverse bias mode, means what? It acts as an open circuit, na? Yes or no? It acts as an open circuit. Okay, so we can draw the circuit, equivalent circuit during pi to 2 pi. So it is like diode D will be in a reverse bias mode. That is nothing but open circuit mode. That is the off state. Supply voltage, here it is a supply voltage we are having, and here it is a load. So you can check here. This is a Vs minus plus. This is a Vd. Here it is a Id. Here it is a Is. Resistance R. V0, and here it is a I0. Where are we, right? Now you can check here, as diode is in a off state. Diode D. This is a diode D, na? Diode D is in a reverse bias mode, means what? It is in a off state. So it is like an open circuit here. We're having an open circuit. So whether the current will flow in the open circuit? No. Impedance of the open circuit is infinite now, we know. So current flowing through the open circuit is 0. So can we say that here Is, Id, I0 all will be 0, right? So let me write Is is equal to Id is equal to I0, all will be equal to 0 ampere only. All will be 0. Means current will not flow into the circuit. Now if I0 is 0, what about the V0? According to Ohm's law, V0 is equal to I0 into R. Okay, so V0 is equal to I0 into R. So it is equal to 0 into R. So therefore we can write V0 is equal to 0 volt, right? V0 is equal to 0 volt. Is this clear? So I0 0, V0 0. Now what about the VD? That is the voltage across diode. So you can check, can we apply KVL to this loop? Either you can apply KVL like this, that is tracing the loop in the clockwise, or tracing the loop in the anti-clockwise. In both the ways, you will be getting the same answer only. Okay, so yes, we can apply the, suppose, KVL to the loop. Let me write KVL to loop. It is like a minus Vs minus Vd minus V0 na, is equal to 0. What is V0? V0 is 0 volt, right? So this indicates your Vd is equal to minus Vs. Vd is a minus Vs. That is the Vd is a negative. Vd is a negative. Is this clear? Okay. So diode voltage is a negative. V0 is 0 volt, and these currents are 0 ampere. Okay. So you can check during pi to 2 pi. During pi to 2 pi, we're in the circuitry, waveform, right? Supply voltage is negative. V0, I0, 0. And what is Vd? Vd is a negative. Vd is a negative. Are you getting the point, right? So don't get confused here. Minus Vs, it doesn't mean that minus of this waveform. No, because you can check during pi to 2 pi. During pi to 2 pi, we have reversed the polarity of the supply voltage. So that's why here Vd is minus Vs, means your Vd actually is a negative only. It doesn't mean that minus negative of that your reverse negative that of negative supply voltage. It is not like that. If you consider like that, negative of that negative value, so that will be positive. It is not like that. Please get it cleared here itself. I am saying that as during pi to 2 pi, we have reversed the polarity of the supply voltage. Here it is minus, here it is plus. So if this indicates Vd is minus Vs, means our Vd is equal to minus value only, negative value only. Okay. So during pi to 2 pi, it is a negative voltage. Now Again, after 2 pi, what will happen? After 2 pi, again, the same cycle will repeat now. After 2 pi, you can check. Here it is a 2 pi. 0 to 2 pi, one supply cycle complete. 2 pi to again 4 pi, the second cycle will repeat. 4 pi to 6 pi, third cycle will repeat. Okay. So whatever the waveform we're having from 0 to 2 pi, the same will go on repeating. Same will go on repeating. Is this clear? So now you can check here. Input is a AC, right? In AC means what? How to check whether it is a AC or DC? Keep it in mind. AC means it is like we're having the two polarity voltages, positive as well as negative. Okay. So that is the AC. And DC means we're having only one polarity voltage. So you can check here. V0 we're having only positive and 0, positive and 0, positive and 0. So that's why it is a DC. Definitely it is not a flat DC. Definitely it is not a flat DC. But it is a pulsating DC. But it is a pulsating DC. Are you getting the point? In real life, what we are doing? Yes, we are actually connecting after this load. We are connecting, or across the load, we are connecting a capacitor. Okay. And so that, or you can say the filter. Okay. In the circuit, we are connecting the filter. And so that this pulsating DC can be converted into the flat DC. Can be converted into the flat DC. Right. So this is the circuit operation. Next, why it is known as a half wave rectifier? Why it is known as a half wave rectifier? Please listen. Half wave rectifier means, you can check here. We are getting pulse in the, we are getting the pulse in the output voltage only corresponding to the positive half cycle, na? Corresponding to the negative half cycle, whether we are getting the pulse here output voltage? No. So that's why only corresponding to the positive half cycle, we are getting the output as a non-zero. So that's why it is a half wave rectifier. Okay. In the full wave rectifier, you will understand. Corresponding to the positive half cycle also, I will be getting the non-zero output. Corresponding to the negative half cycle also, we will be getting the non-zero output. That is in full wave rectifier, I am saying. In half wave rectifier, corresponding to only positive half cycle, we are getting the output voltage as a non-zero. Corresponding to the negative half cycle, we are getting it as a 0. Right? So that's why it is a half wave rectifier. Next, it is also known as single phase, single pulse uncontrolled rectifier. Let me write. It is also known as a single phase, single pulse uncontrolled rectifier. Okay. This circuit is also known as single phase, right? You might be knowing this is a single, one means single, and phase, this is a phase. Okay. Single phase, single pulse uncontrolled rectifier. Uncontrolled rectifier. What is the meaning of this single phase, single pulse? Because corresponding to one input cycle, you can check here. Corresponding to one input cycle, we are getting in the output only one pulse, na? Yes or no? Corresponding to one input cycle of the supply voltage, in the output voltage, we are getting only one pulse. So that's why it is a single phase, single pulse rectifier. Yes or no? Are you getting the point? Right? Next, so my question is, sometimes they ask the question in ESC, GATE, or some PSUs also. Okay, previously they used to ask this type of questions. Okay, suppose if the input supply frequency is a 50 hertz. Okay, for this rectifier circuitry, suppose if the input supply frequency is 50 hertz, then what will be the output pulse frequency? Then what will be the output pulse frequency? Please listen the question carefully. We're having this rectifier, and they have given that the question is like, the input supply frequency is a 50 hertz, 50 hertz. Then what will be the output pulse frequency? Output pulse frequency. Yes, can anyone? Input supply frequency 50 hertz. Then what will be the output pulse frequency? Yes, it's the same. Some are saying 25 hertz. Okay, some are saying same. Okay. Yes, if the input supply frequency is 50 hertz, what will be the output pulse frequency? Yes, it is a 50 hertz only. Please listen. Why it is a 50 hertz? I'm writing. Let me write here first. Output pulse frequency. output pulse frequency. Output pulse frequency is equal to input supply frequency. Input supply frequency. Why? Because you can check from the waveform. Yes, corresponding to the one input cycle, corresponding to the one input cycle from here to here, whatever the one input cycle of the input na, in the output how many pulses we are getting? We are having only one pulse na, yes or no? Means corresponding to 0 to 2 pi, input is completing one cycle, and so corresponding to 0 to 2 pi in the output how many pulse means what? This is a pulse. Are you getting the point? This is a pulse. So corresponding to one input cycle of the supply, in the output we are having only one pulse. So suppose if the input supply frequency is 50 hertz, means input is completing 50 cycles in 1 second. So how many pulses will be getting in the output? Corresponding to the one cycle, we are getting one pulse na. So for 50 cycles, how many pulses will be getting? It is equal to 50 pulses na. So that's why here frequency of the output pulse is equal to the frequency of the supply. Is this clear? Right? Supply frequency is equal to your output pulse frequency. So that's why it is known as a single phase single pulse na. Single phase single pulse means corresponding to one input cycle, we are getting only one pulse in the output. Okay, so that's why single phase single. Is this clear? This type of question they have asked us some of the times. Okay, next, now let us derive the expressions. Let us derive the expressions here. Okay, so yes, let me write here. Average output voltage. Average output voltage. So it is a V0 average. V0 average. V0 average is nothing but average value of the output voltage. You can check here. Rectifier is a, yes, rectifier is a AC to DC converter. Input is a AC, output is a DC. And in a DC, what is the effective value? Effective value is the average value. In AC, the effective value is RMS value. Please keep it in mind. In AC, the effective value is a RMS value. That's why generally you say, you might be knowing that generally when we specify the AC quantity, just like a single phase 230 volt 50 hertz, what that 230 volt indicates? That 230 volt indicates it is a RMS value of that supply voltage na. So in AC, the effective value is a RMS. In a DC, the effective value is a average. Okay, so here now, so V0 average means our task is to find the average value of the output voltage. So we're having the waveform for the output voltage. It is like this, right? This is the output voltage na. Now you can check whatever the waveform of V0 we're having from 0 to 2 pi. The same waveform is repeating from 2 pi to 4 pi. Same will repeat from 4 pi to 6 pi. Are you getting the point? Whatever the waveform in the output we are having from 0 to 2 pi. Means this I am saying from 0 to 2 pi I am saying. Okay. Definitely in 0 to 2 pi we are having 0 to pi non-zero output. Pi to 2 pi we are having a zero output, right? So whatever the waveform we are having from 0 to 2 pi, the same will repeat from 2 pi to 4 pi na, right? 2 pi to 4 pi. Same will be there for 4 pi to 6 pi. So what is the periodic angle of the output voltage? The periodic output, yes, periodic means this waveform is periodic na. Whatever the pulse here, the same is repeating. So that's what is a periodic. So what is the periodic angle? It is a 2 pi. Periodic angle is a 2 pi. So let me write it as a 1 by 2 pi. Means this divided by 2 pi na? That divided by 2 pi is nothing but your periodic angle. Okay. So please try to understand how to write the average value. How to write the average value. Okay. It is a 1 by 2 pi. So it is divided by 2 pi means it is a periodic angle. Periodic angle. Okay. Next, what is the, yeah, let me write here. Yes. 0 to 2 pi we are having, and the periodic angle we are having a 2 pi. So that's why I've taken it as a 1 by 2 pi. Next, while finding the average value, for example, suppose we are having the 10 numbers 1, 2, 3, 4, 5, 6 up to the 10. How generally we take the average? It is like 1 plus 2 plus 3 plus 4 plus up to the plus 10, na? Right? So that's why here Plus 10 means first of all we are adding na, we are adding these numbers. So here now there the addition of the numbers, yes, it was possible only because we consider the discrete numbers na, 10 samples we consider 1 2 3 4 up to the 10. But here you can check 0 to 2 pi in the output voltage, it is a continuous waveform. Now we are having continuous waveform. So for the continuous waveform, how many samples are possible? We are having infinite samples. So whether can we add the infinite samples manually? Not possible. Samples, your signal system sampling theorem you might be knowing. Okay. So here please try to understand 0 to 2 pi, whatever the V0 waveform we are having, we need to add the instantaneous values of that V0 waveform. So adding the instantaneous values of V0 waveform, as V0 waveform is a continuous one, so it will be having infinite samples. We cannot add infinite samples one by one manually. So that's why we need to take the help of mathematical operator, integrator. What the integrator indicates? Integration of something means what? Integrate means we are adding. Integrate means we are adding only. Okay, so please try to understand. 1 by 2 pi, we need to integrate over 0 to 2 pi, right? 0 to 2 pi. So integration over 0 to 2 pi. Why this integration is there? Because we need to add the instantaneous values. Okay, 0 to 2 pi. Next, it is a V0 into d omega t. So please try to understand what this integration of V0 d omega t indicates. It indicates we are adding the instantaneous values of the output voltage over the interval 0 to 2 pi. And again, I have divided with a fundamental period, okay, or the periodic angle. So this is actually expression for your V0 average. Okay, V0 average, right? Now, again, you can check 0 to 2 pi in the V0 waveform. Between 0 to 2 pi, we are having two subintervals. We are having two subintervals. One is 0 to pi. Second one is pi to 2 pi. Yes or no, right? So let me write it as. V0 average. Therefore, V0 average is equal to 1 by 2 pi into integration over 0 to pi. During 0 to pi, what is the V0? V0 is same as that of the supply voltage, na? Right? So supply voltage is Vm into sine of omega t into d omega t plus integration from pi to 2 pi plus integration from pi to 2 pi. 0 to 2 pi we are divided as 0 to pi and pi to 2 pi. During pi to 2 pi, what is V0? It is a 0, na? So it is a 0 into d omega t. Right? Next, so what is the integration of this 0? Integration of 0 is a 0 only. Yes or no? So this term integration will become 0. So we'll be having only this term, na? Now can we simplify this term? Yes. So therefore V0 average. Therefore V0 average is equal to, yes, it is a 1 by 2 pi integration over 0 to pi Vm into sine of omega t into d omega t. Please try to understand how to derive the expression, because in power electronics we are having the n number of circuits, and for each circuit we are going to find the n number of parameters. So you cannot memorize each and everything, each and every expression you cannot memorize. So please try to understand how to simplify it. That is the important thing, because at the time of final examination also you need to simplify this only. You need to derive the expression there only. Are you getting the point, right? So it is equal to Vm is a constant, na, peak value. So let us write it as Vm by 2 pi. I'm taking this Vm outside, so it is a Vm by 2 pi. Okay. Now, what is the integration of sine? It is a minus cos of omega t, limit 0 to pi, right? So which is equal to Vm by 2 pi. We can put the limit. It is a minus of cos of pi plus cos of 0. So it is equal to Vm by 2 pi into minus of cos of pi is minus 1. So minus of minus 1, 1. And this is cos 0 is 1. 1 plus 1, 2 into 2. So therefore V0 average is equal to, yes, it is a Vm by pi. Vm by pi. No need to memorize the expression, right? No need to memorize the expression. It is a Vm by pi. Right? V0 average. That is the average value of output voltage is equal to Vm by pi. What is this Vm? Vm is nothing but the peak value of the supply voltage, na? Peak value of the supply voltage is nothing but your Vm. Okay, peak value of supply voltage. Next, V0 average you have written. Can we write the expression for I0 average? Yes, I0 average. is equal to V0 average divided by R. Okay, V0 average divided by R, because we know now according to Ohm's law what we are having, V0 is equal to I0 into R. Okay, R is a, yes, it is a passive element, it is a constant. So if I take the average value of this, so it is equal to I0 average into R. So I0 average is equal to V0 average by R, right? So we can write it as a Vm by pi R, no? Vm by pi into R. This is the I0 average. Next, can we write the expression for V0 RMS? RMS value of output voltage. RMS output voltage. You can say output, you can say the load voltage, doesn't matter. Okay, so V0 RMS. Please try to understand what this RMS indicates. RMS means root mean square. It is a square root of mean of squared value. Okay, means we need to take the square root of, yes, mean of squared value. So first of all, we need to take the mean. Mean is nothing but the average. We need to take the average of the squared value, and again we need to put it into the square root. Okay, we need to put it into the square root. So how to take the average of the squared value? This V0 average indicates, yes, average of instantaneous value. How to take the average of the squared value? How to take the average of squared value? Yes, it is, let me show you. Integration over 0 to 2 pi. If I write it as a V0 square into d omega t, 1 by 2 pi. What this term indicates? If your 1 by 2 pi, integration over 0 to pi V0 d omega t, if this indicates average of V0, if this indicates average of V0, then what this term indicates? Can we say that this is the average of V0 square? Yes or no? Average of V0 square. So average of V0 square means what? Average of the squared value, na? And what this MS stands for? Mean of the squared value. So that is nothing but the average of the squared value. And again, we need to put it into the square root. So it is the square root of mean of squared value. Are you getting the point? To the power 1 by 2 means it is the square root. So square root of mean of squared value. Is this clear? Again, now we can divide this 0 to 2 pi as 0 to pi and pi to 2 pi. Okay, so therefore V0 RMS is equal to 1 by 2 pi. Okay, let me write it as a integration from 0 to pi, because V0, 0 to pi V0 is same as that of the supply voltage. Pi to 2 pi V0 is 0, na? Waveform, recall that waveform. Okay, so it is a Vm square into sine square of omega t into d omega t. This is the one thing, plus integration from pi to 2 pi. What is the V0? 0, na? So it's square into d omega t to the power 1 by 2. Are you getting this point? Right? V0 is V, same as that of the supply voltage during 0 to pi. So it's a square. So that's why it is a Vm square sine square of omega t. And it is a during pi to 2 pi V0 is 0. Right? So that's why 0 square. So definitely this term will become 0 only. Right? So only this term we need to simplify. Right? So for that, this is a Vm square. So can we take it outside? It is a constant only, na? Right? So yes, I can take this Vm square outside. So if I take this Vm square outside of this square root, then it will become Vm. Also, can we take this divided by 2 pi also outside, out of this square root? Yes, we can take this divided by 2 also out of the square root. So it will be root 2 pi, and this will be Vm. Okay, so let me write V0 RMS. Therefore, V0 RMS is equal to Vm upon root 2 pi. Okay, Vm upon root 2 pi means I have taken this outside. This is also taken outside. So only thing is integration of this term. So can we directly find the integration of sine square of omega t? No, right? We need to replace that sine square of omega t with 1 minus cos of 2 omega t divided by 2. Okay, so let me write it as integration over 0 to pi 1 minus cos of 2 omega t divided by 2 into d omega t to the power 1 by 2. Further, can we take this divided by 2 outside? Yes. So therefore V0 RMS is equal to Vm upon 2 root pi. I am taking this divided by 2 outside. So that will become root 2. This root 2 and this root 2, it will become 2. Okay. 2 root pi into, what is the integration of 1? It is omega t. right? Minus integration of cos of 2 omega t, it is a sine of 2 omega t divided by 2, right? Limit 0 to pi to the power 1 by 2. Further we can write, therefore V0 RMS is equal to Vm upon 2 root pi into, it is like a, put the limit pi minus 0, okay, minus of sine of 2 pi divided by 2 plus sine of 2 into 0 divided by 2 to the power 1 by 2. What is sine 2 pi? Sine 2 pi is 0 na? That is sine 360, 0. Sine of 2 into 0, that is sine 0, 0. So only this term will remain. So to the power 1 by 2 means again it is root pi. So this root pi will get cancel out. Okay, so it is equal to Vm by 2. Vm by 2. This is your V0 RMS. Is this clear? RMS value of output voltage is equal to Vm by 2, right? Vm by 2, right? Next, can we write the expression for I0 RMS? Yes, I0 RMS we can write. Yes, I0 RMS means RMS value of output current. It is equal to V0 RMS divided by R. I0 RMS is equal to V0 RMS divided by R. Okay. Next, can we write the load power, output power, or the load power? Okay, so output power or load power. Load power or output power. So output is AC or DC? Output is AC or DC? It is a DC. Okay, so effective value will be average value. So load power means only your P0 average. We need to find, okay, P0 average, right? So how to find the P0 average? Let us discuss. Please check waveforms. Just a minute. How to go back to the previous slide. Correct. Yes. So output is, yes, here we are having the V0 and I0 waveforms, right? So how to find the P0 average? P0 means load power, na? Okay. Now in this case, you can check V0 into I0 is nothing but your P0, na? V0 into I0 is nothing but your P0. So if I want to draw the waveform of P0, that is the output power, how it will be? It is like a product of these two waveforms only. So you can check during 0 to pi, V0 and I0 both are non-zero. So what is the P0 during 0 to pi? During 0 to pi, P0 will be, yes, product of these two means what? It is a non-zero only. During pi to 2 pi, what is the output power? During pi to 2 pi, output power is V0 I0, V0 into I0. But what is V0? 0. What is I0? 0. So what is the product? 0 only. So if we want to draw the waveform of P0, it will be like during 0 to pi, it will be non-zero. During pi to 2 pi, it will be 0. Yes or no? And again from 2 pi to 3 pi, the same non-zero. Again 3 pi to 4 pi, it will be 0. Okay, so what is the periodic angle for that power P0 waveform? It is a 2 pi only. Are you getting the point? Because output power means what? Load voltage into load current product. And load voltage waveform we are having this one. Load current waveform we are having this one. Is this clear? So it is a V0 into I0 product. So let me write it as, yes, 1 by 2 pi integration over 0 to 2 pi. It is a V0 into I0 into d omega t. Average of power. So power is nothing but V0 I0. Okay, instantaneous value of load voltage, instantaneous value of load current. Product of these two, that is nothing but the power. And it is a periodic angle is 2 pi. And we are integrating it. So that's why this is the average. So now you can check here during 0 to out of the 0 to 2 pi, the effective interval will be only 0 to pi na. So we can write it as is equal to 1 by 2 pi integration from 0 to pi, integration from 0 to pi. It is a v0. What is the v0 value during 0 to pi? It is a Vm sin omega t. So it is a Vm into sine of omega t into do, Vm into sine of omega t, that is the v0. What about the I0? I0 is again v0 divided by r na. So it is a, let me write Vm into sine of omega t divided by r into d omega t. Is this clear? We are interested in finding the average value of the output power, which is equal to 1 by 2 pi, that is the periodic angle, okay, and 0 to 2 pi v0 into I0, means we are integrating it and dividing with the periodic angle. Whatever we done for v0 average, yes or no, the same thing we are doing for p0 average, right? So now we need to simplify it, right? So Vm into Vm square, okay, we can take that Vm square outside, this r also we can take outside of the integration. So it will be like p0 average is equal to, yes, it is a Vm square by 2 pi r, Vm square divided by 2 pi r, okay, into integration, yes, into what? Integration of sine square of omega t, right? Integration over 0 to pi sine square of omega t into d omega t. So further we can write it as Vm square divided by 2 pi r. Yes, this can be written as integration over 0 to pi sine square of omega t. It is a 1 minus cos of 2 omega t divided by 2 into d omega t. Sine square theta, 1 minus cos 2 theta by 2. Okay. So this is equal to Vm square divided by 4 pi r. Okay. Into these two I have taken outside. Yes, this will be like a omega t. Integration of 1 is omega t. Integration of cos of 2 omega t, it is a sine of 2 omega t divided by 2, limit 0 to pi, which is equal to Vm square divided by 4 pi r into, it is like a pi minus 0 minus sine of 2 pi, that is a 0 only, plus sine of 2 into 0. So sine 2 0, sine 2 into 0, it is a 0. Sine of 2 pi, that is sine 360, it will be 0. Okay. So it is like this pi and this pi will get cancelled out. So it is a Vm square by 4r. Okay. So let me write, therefore P0 average is equal to what? Vm square divided by 4r. Further, can we write this term as equal to Vm by 2 into Vm by 2r? Yes or no? So what this Vm by 2 indicates? Vm by 2, you can check. Vm by 2 is nothing but V0 RMS, yes or no? Right? And what about this V0 RMS by R? That is the I0 RMS now. So V0 RMS is Vm by 2. So what about the I0 RMS? Vm by 2R. Okay. So here can we write, replace Vm by 2 means V0 RMS into what is Vm by 2R? It is a I0 RMS. Please be careful. This is very important. Means at the left hand side, we are having the average value P0 average. But at the right hand side, this is the product of RMS voltage and RMS current. Is this clear? The same thing we discussed in the first chapter while finding the expression for the conduction loss of a MOSFET, na? Piecewise modeling of the devices, right? We're having the devices are modeled as either resistive, only pure resistive, or the second thing is voltage source, and third one is the voltage and resistance. And in the case of pure resistor, what expression we return? It is the same, na? V0 RMS square by R or I0 RMS square into R, yes or no? Or V0 RMS into I0 RMS. So please keep it in mind. If it is an average, P0 average, even though it is average at the left side, most of the students, okay, they think that left side average means what? The average output power is equal to V0 average into I0 average. No, always keep it in mind. If the resistive load, if the load is resistive, then the output power P0 average is equal to V0 RMS into I0 RMS only. Again, this can be written as, also this can be written as, which is equal to V0 RMS square divided by R, which is equal to I0 RMS square into R, right? All are the valid expressions. These three, right? All three are the same only. Okay. This is the P0 average, right? Next, let us check for the conduction time of diode. Conduction time of diode. Conduction time of diode. Yes. If you check the circuit operation, yes, during which interval the diode is in on state? Diode is in on state only from 0 to pi, na? Right? Only from 0 to pi the diode is in on state. Yes or no? Yes, diode is in on state. VD0 means what? From 0 to pi diode is in on state, na? Here it is diode D is in on state. This is not DON. This is a diode D in on state. Okay, D dash on. Okay, so diode D is in on state during 0 to pi. Pi to 2 pi diode is in off state, na? Right? So let me show here. During pi to 2 pi, diode D is in off state. So what is the conduction time of diode? Let us first find the conduction angle. After that, we will discuss for the conduction time. Okay. Yes. 0 to pi diode is in on state. So what is the conduction angle? Conduction angle is like pi minus 0. So that is the pi radian. Right. And as we know, na, omega t indicates the angle. So time will be angle divided by omega, na? Right. So therefore, conduction time of diode will be pi by omega. Are you getting the point? It is a pi by omega. So let me write it as pi by omega. Conduction time of diode is equal to pi by omega, because diode is in on state only from 0 to pi. Okay. So conduction angle is pi and time is pi by omega. Right. Next, what is the PIV rating? PIV rating of diode. PIV rating of diode is equal to, PIV means peak inverse voltage. Please listen it. PIV, peak inverse voltage. What this peak inverse voltage meaning? Peak means maximum. Inverse means reverse voltage. Okay. So what is the value of maximum reverse voltage across the diode? That is nothing but your PIV rating of diode. So you can check here in this circuit. Yes. Check the VD waveform. During 0 to pi, VD is 0. During pi to 2 pi, what is VD? It is a negative, na? So that's why this is the reverse voltage. Okay. So what is the peak value of this reverse voltage? Yes, you can check. I'm sorry. What is the peak value of this reverse voltage? It is a Vmax, na? Same as that of the supply voltage. Okay. So peak inverse voltage of a diode is equal to Vmax, is equal to Vmax. Are you getting the point? Okay. So it is equal to Vmax. What is this Vmax? Vmax is the peak value of the source voltage. Please be careful. Don't get confused. Here, while writing the PIV rating, we need to write only the magnitude, because in this term already the inverse word is there. Are you getting the point? Okay, you might be thinking that, yes. Yes, you might be thinking that, sir, this is the negative voltage, na? Right? Peak negative. Okay, but in this term they have already mentioned it is an inverse voltage, na? So that's why we want to write only magnitude. Right? Suppose if they give a circuit and if they ask for the peak inverse voltage rating of the diode, and if they give the options like Vm, minus Vm, okay, and other two are the remaining options. If you tick for minus Vm, 0 marks will be getting. Okay, so please keep it in mind. PIV rating means we are supposed to write only the magnitude. Okay, so peak inverse voltage. Next, let us find the input power factor. Input power factor. Okay, so input power factor. Yes, input power factor. It is also known as the supply power factor or supply power factor. So how to find the input power factor or the supply power factor? Let us discuss. Okay. So if you check the circuit, yes, if you check this circuit, in this circuit we are having the supply, that is the source, it is a load, and here we consider it as an ideal diode now, right? So if this diode is ideal, what about the losses of this diode? You can check when diode is in an on state, the voltage across diode is 0. So the conduction loss will be 0 voltage into current, okay, non-zero current. So that's why that will be 0 only na. And when diode is in an off state, at that time voltage is non-zero. But what about the current? Current flowing through the diode is 0 na. So what is the product of voltage and current? It will be 0 again. Okay, so please keep it in mind, as this is the ideal diode we considered. So that's why the power loss in this diode will be 0 only. So now can we say that whatever the power supplied by the source is equal to power consumed by the load? Yes or no? Are you getting the point? Right? Because in this circuit we are having only 3 elements. Out of that, one is the switching element, and that switching element is the ideal we have considered. So that's why the power loss in that switching element is a 0 only. We discussed now ideal switches and practical switches. In ideal switches, yes, what are the power loss? It is a 0 only now, right? So that's why here power loss is a 0. Okay, so we can say that whatever the power supplied by the source is equal to power consumed by the load. Okay, so let me write power supplied by source is equal to power consumed by load. Right? Power consumed by the load. Is this clear? So now what is the power supplied by source? So input is AC, na source is AC or DC? Source is AC. Okay. So what is the power supplied by source? Can we write it as power supplied by source is equal to Vs RMS into Is RMS into power factor cos phi s. Please try to understand the meaning of this term. In AC circuit, what is the expression of the power? Vi cos phi. What that V indicates? V is the RMS value of the voltage na. So that's why here Vs is our supply voltage and RMS is nothing but RMS value of the supply voltage. Is RMS means RMS value of the supply current, that is the source current. And cos phi s is nothing but cosine of angle between these two. Okay, that is the cos phi s. Our task is to find the supply power factor or the input power factor, means our task is to find the cos phi s value, right? So now which is equal to power consumed by the load? Output side is DC. What is the load power effective? It is a P0 average na. P0 average. Now can we write it as which is equal to yes, V S RMS into Is RMS into cos phi s is equal to what is the P0 average? We have written na V0 RMS into I0 RMS, that is P0 average. Just now we written P0 average is V0 RMS into I0 RMS. So let us put here V0 RMS into I0 RMS. Okay, so therefore we can write cos phi s, that is the input power factor, is equal to V0 RMS into I0 RMS divided by Vs RMS into Is RMS. Right? Now if you check the circuit operation, whether I0 and Is all are both will be same or different. If you check the circuit operation, yes, yeah, here it is. Okay, you can check the circuit operation. We have discussed circuit operation during 0 to pi. You can check Is and I0 both are same or different? Both are same. During 0 to pi both are same. During pi to 2 pi also you can check, we have written during pi to 2 pi. Okay, Is and I0 both are same. Yes or no? Right? So if Is and I0 are same, then can we say that the RMS value of this and RMS value of the source current both will be same only? Are you getting the point? Okay. So I0 RMS and IS RMS will be same only because during 0 to pi, diode is in an on state and we're having load current is equal to source current. Second thing, during pi to 2 pi, we are having diode is in an off state. Source current and load current both are zero, na? Right? So I0 waveform and IS waveform will be same. So that's why their RMS value will be same only. So that's why this will get cancelled out. So further we can write input power factor. Input power factor. IPF means input power factor is equal to cos phi s. Is equal to cos phi s is equal to V0 RMS divided by Vs RMS. This is the expression for input power factor. Now V0 RMS and Vs RMS both will be same or different? Come on. Whether V0 RMS and Vs RMS both will be same or different? Please check the waveform. Recall the waveform of V0 and Vs. Some are saying same, some are saying different. Please check the waveform, you will understand. Different, na? Yes, here it is, we discussed. Vs means this type of, this waveform we're having Vs. This is a full, na? Positive as well as negative. And V0 is only this. So whether both are same, V0 waveform and Vs waveform both are same? No, both are not same. Right? So that's why here we cannot cancel out V0 RMS and Vs RMS. Further, we can write it as V0 RMS, we are having the expression, na? It is a Vm by 2. And Vs RMS expression we know, it is a, if we are having a sinusoidal supply, then what is the relation between RMS and the peak? It is a Vm by root 2. So further we can replace this as a Vm by 2 and this as a Vm by root 2. Vm will get cancelled out. So it is like a root 2 by 2. Okay, 0.707 will be getting, right? So the not required. This at the time of numericals, okay, we'll discuss how to simplify, right? So this is the analysis of single phase half wave uncontrolled rectifier. Okay, single phase half wave uncontrolled rectifier with purely resistive load, right? Next, my question is why it is known as an uncontrolled rectifier? Why it is known as an uncontrolled rectifier? Come on. Why it is known as an uncontrolled rectifier? Yes. Because if you check here, input is we are having the fixed value. And if I use the diode here, in the output, I'll be getting only this pulse, na? This pulse 0, this pulse 0. Can I turn on the diode at somewhat that is omega t 30 degree, omega t 60 degree? No. So we'll be getting only this fixed pulse, na? So that's why, yes, it is an uncontrolled rectifier. We are getting the fixed value in the output voltage. Okay. So this pulse is fixed. So that's why it is an uncontrolled rectifier. Or from the V0 average expression also you will understand, right? You can check the V0 average expression. Yes, here we have written. It is a Vm by pi, na? Vm is a peak value of the supply voltage. It is a fixed one. Once the supply is connected, na, it is a fixed one. So pi is also constant. Okay. So that's why this Vm by pi you will be getting, it is a constant only. Okay. So that's why we cannot change the output voltage. So that's why it is an uncontrolled rectifier. It is a uncontrolled rectifier. Is this clear? Right? Okay. So we'll take a break here. After the break, we'll discuss for purely inductive load. Purely inductive load. Yes. Some students have raised their hand.
Sir.
Yes, please.
Sir, by considering the input power factor, you equated the RMS side to the average output power PO average. Why?
Yes. Okay, this.
That line
because,
I did not understand.
Because you can check input side we're having the AC.
Yes, sir.
Output side we are having a DC,
Okay, sir.
right? So that's
Got
why
it, sir.
effective value here is a DC na in the output. At
So
output
that we
side.
took average.
Yes, yes. So that's why we need to take the average only,
Okay, sir. Thank you.
right? Okay. Next.
Hello, sir.
Yes,
Sir.
yes, please.
Sir, you said that output pulse frequency equal to input supply frequency. How, sir?
Okay. You can think on this waveform, you will understand. You can check corresponding to one input cycle, na? One
Yes,
input
sir.
cycle of the is from 0 to 2 pi.
Okay.
So corresponding to the 0 to 2 pi in the output, how many pulses I am getting? 0 to, you can check over 0 to 2 pi in the output, how many pulses we are getting? Whether we are getting only one pulse in output voltage.
Yes, sir.
So that's why corresponding to one input cycle in the output we are having only one pulse, na?
Okay.
So that's why the frequency is same. If you check, we're having the 50 hertz supply. The meaning is input supply is completing 50 cycles in 1 second,
Okay. Okay, sir.
right? So in 1 second, supply is completing 50 cycles. And for one cycle in the output, we are having one pulse. So for 50 cycles of the input supply, how many pulses will be getting in the output? 50 pulses, na?
Okay.
So in 1 second, we are getting 50 pulses. So what is the output frequency? Again, it is 50 hertz.
Okay. Understood, sir.
That's why it is the, yes, same frequency.
And one more doubt, sir. In
Yes, please.
average output voltage, once you
Yes.
open average output voltage slide.
Okay.
Sir, in beginning, 1 by 2 pi
Okay.
integration of 0 to 2 pi V naught d omega
Yes.
t. Sir,
Yes.
1 by 2 pi, I didn't understand, sir. 1 by 2 pi, how to take it?
1 by 2 pi means here we need to take it corresponding to the fundamental period or the periodic angle.
Okay.
You can check the V0 waveform. V0 waveform we are having from 0 to pi non-zero.
Yes, sir.
Pi to 2 pi it is a 0. Right? And this same waveform will repeat, na? Whatever the waveform we are having from 0 to 2 pi, same will repeat from 2 pi to 4 pi. So what is the periodic angle? It is a 2 pi.
Okay, sir. 21 slide, sir. 21.
Right, number 21. Okay. Huh.
Sir, in denominator, Vm square by 4 pi or how, sir? Okay, 1 by 2 is taken outside.
Yeah, this divided by 2 I have taken outside.
Taken out. Okay, okay, sir.
Right?
Okay, sir. Thank you.
Okay.
Hello, sir.
So we'll take.
Sir?
Hello.
Yes. We will take a break here. At the end, we will discuss. Okay. Otherwise, it will yes difficult, na?
Sir, small doubt, sir.
Yes, please.
Sir, uncontrolled rectifier means fixed DC.
Uncontrolled rectifier means if your input is fixed, na,
Yes, sir.
then in the output also we are getting the fixed value.
Sir, controlled rectifier means, sir, controlled DC means variable DC, sir.
Controlled DC means we can vary that magnitude of the output voltage. That you will understand when we discuss the controlled rectifier, na, you will understand.
Sir, one pulse means, sir.
One pulse.
Yes, sir.
One pulse
This
means
is single phase
yes,
means
yes.
single pulse uncontrolled rectifier. This you know.
Yes. One pulse means this is the one pulse, na.
Okay, sir.
This is a one pulse. 0 to pi we are having output voltage. This is a one pulse.
Sir,
Whether
I
it is
mean
a fixed
single.
DC, whether it is a fixed DC, no. Actually, ideally, what we expect rectifier should give the fixed DC, na, flat DC.
Yes, sir.
But whether our rectifier is giving flat DC, no. So that's why it is a pulsating DC, na. This is a pulsating DC.
Sir, that's
Right?
why single pulse. Okay,
Yes,
sir.
single pulse. Okay.
Okay.
Hello, sir.
Sir?
Yes, please.
Sir.
Last doubt, please.
Okay, sir. Last.
Yes,
Yes.
yes.
Sir, you are saying cos phi is equal to cos phi from sending end side is V naught RMS by Vs RMS.
Yes, correct.
Sir, I naught waveform is equivalent to IS, na, sir?
Yes.
When we are seeing in the waveform, Vs and IS doesn't having any phase difference, then how we are getting that power factor, sending end power factor? It should be
Okay,
one, na? Why it is getting 1 by root or something like that?
Okay. No. But here you can check your Vs is a sinusoidal, na?
Yes, sir.
But whether your Is is sinusoidal here?
No, sir, not a sinusoidal.
No, no, it is not a sinusoidal. You can say that there is no phase difference when Is is also like this, positive cycle, negative cycle.
Oh, okay, sir.
But in this case, your Is is not having the negative cycle,
Okay, sir.
right? So,
So
right?
we can't use the definition of phase difference as power factor in this.
No, you can't use that definition here. Huh? We
Okay,
need to
sir.
simplify in this way only, right?
Only how much power is getting into our load side. We are checking. that
Yes,
one.
yes, yes, yes. Okay,
Thank you,
okay,
sir.
right? So it is 7 almost. We'll start at 7:15. Okay, right? 7:15 will start, and at the end of the session, we will discuss. We'll take the other doubts, right? Okay, okay. Okay. So now we are going to discuss single phase half wave uncontrolled rectifier with a purely inductive load. Okay. So L is a pure inductor. So what will happen? Let us discuss. Single phase half wave uncontrolled rectifier with a L load, purely inductive load. Okay. So suppose we are having a circuit, single phase AC supply. Suppose switch is here, diode, and here it is a inductor. Suppose this switch is closed at t is equal to 0, right? Right. So, right. So single phase half wave uncontrolled rectifier with purely inductive load. So here we are having a circuit diagram. Vs is equal to Vm into sine of omega t. That is a purely sinusoidal supply. During 0 to pi, Vs is a positive, pi to 2 pi negative, and again positive, right? Next, here we have placed the switch. That switch is closed at t is equal to 0. So t is equal to 0 means at this instant, yes, we are going to close this switch. Okay. So let us discuss the circuit operation. Now here in the load we are having a inductor. So if you recall from the network theory, what is the basic tendency of the inductor? Inductor is the element which opposes the sudden change in the current. It stores the energy in its magnetic field, and also it releases the energy. Okay. Why the inductor releases the energy? In order to oppose the change in the current. Please try to understand. Inductor is the element which stores energy in its magnetic field, and in order to oppose the change in the current, the inductor releases the energy. Okay. So this is the basic tendency of the inductor, right? So now if you check this circuit here, Vs is equal to Vm into sine of omega t. So for omega t 0 to pi, Vs positive, so polarity is plus here and minus here, right? Suppose at t is equal to 0, at t is equal to 0, the switch is closed, right? So let us discuss the circuit operation. At t is equal to 0, we are closing the switch. The meaning is before t is equal to 0, it is like a switch was open. Okay. So before t is equal to 0, if the switch was open, so it is like there was yes, no possibility of inductor storing the energy before t is equal to 0. Yes or no? we are closing the switch at t is equal to 0. So before t is equal to 0, it is like a switch was open. So if the switch was open for t less than 0, so it was like current was not flowing from source towards the inductor, that is the load. So that's why inductor initial current is equal to 0. So that's why inductor initial energy is also equal to 0 only. Okay, so it is a 0, right? Now let us discuss the circuit operation. At t is equal to 0, switch is closed. So from omega t 0 to pi, from omega t is equal to 0 to pi, let us discuss what will happen in the circuit. Okay, so from 0 to pi, it is like a supply voltage is positive means plus here and minus here. Okay, so supply voltage is positive means diode will be in the on state. Diode will be in the on state. Okay, so let me draw the equivalent circuit during omega t is equal to 0 to pi, right? Diode will be in the conduction mode. So for omega t is equal to 0 to pi, it is like diode will be in the conduction mode, switch is closed. Switch is closed, diode is in a conduction mode, right? Supply voltage Vs, and here it is a inductor. So it is a Vs, polarity will be plus here minus here, right? This is a switch which is closed, and here it is a diode D. Voltage across diode is a Vd. Current flowing through the diode is a Id. This current is a I0. This is the inductor L. This voltage is V0, right? And this current is a Is. Okay. So we are having this type of circuit during 0 to pi. Now, can we apply KVL to this circuit? Can we apply KVL to this circuit? Yes, we can apply KVL. Okay. So what is the KVL equation? Plus Vs minus Vd minus V0 is equal to 0. But what is Vd? Voltage across diode. Diode is in a on state now, so Vd will be 0, right? So let me write here. Vd is equal to 0 volt. KVL to loop. KVL to loop. It is like a plus Vs minus Vd minus V0 is equal to 0. Vd is a 0, so therefore it is like V0 is equal to Vs, right? But what is a, yes, V0 is equal to Vs. But what is Vs? Vs is Vm sin omega t, na? So let me write. Now, here I am writing. Now, V0 is equal to Vs means what? Vm into sin of omega t. And what is V0? You can check. V0 is nothing but voltage across inductor, na? What is the expression for voltage across inductor? It is a L into di0 by dt. Yes or no? So can we write it as L into di0 by dt is equal to Vm into sin of omega t, right? Now, yes, from this can we write? Yes, L into di0, or let me shift this L also to the right hand side, and I am shifting this dt to the right hand side. So we'll be getting it as equal to, yes, di0 is equal to Vm by L, okay, into sin of omega t into dt, right? Now integrating both these sides. Integrating both sides. So from this we can write it as di0 is equal to integration of Vm by L into sin of omega t into dt plus integrating constant, that is a C. Okay. Next, now can we simplify this? Yes, we can simplify. Integration of di0 is a I0, which is equal to this Vm by L is a constant, na? So we can take it outside. Okay. And integration of sin of omega t with respect to dt here. Please be careful. Integration is with respect to time dt. Okay. So we can write integration of sin of omega t is a minus cos of omega t divided by omega. We need to write. Okay. Because integration is with respect to time. Okay. So let me write it as Vm by L into, yes, integration of this term. It is the integration of sin is minus cos, so it is a minus cos of omega t, right, divided by omega, right, plus integrating constant C. Let us consider it as equation 1. Now we need to find the value of C by using the initial condition. Initial condition means just now we discussed before t is equal to 0, it is like a switch was open, right? So before t is equal to 0, switch was open means current flowing through the inductor was 0. So at t is equal to 0 minus, t is equal to 0 minus What is the inductor current? T is equal to 0 minus. Here T is equal to 0 minus, inductor current will be 0 only. Okay, so now at T is equal to 0, even though the switch is closed, what will happen? Our inductor will act as an open circuit, na? Transient theory, right? If initial current flowing through the inductor is 0, then at the instant of switching, inductor will act as an open circuit. So at T is equal to 0 also, inductor will act as an open circuit, means current in the circuit will be 0. So let me write here, at T is equal to 0, at T is equal to 0, I0 is equal to 0 ampere. Okay, because of the inductor, right? Because of the inductor. Now can we put these two values in equation 1? Yes, put these two, or let me write from equation 1. Therefore from 1, yes, we can write I0 is 0 Vm by L into minus of cos of omega into time, put T is equal to 0, so it is a omega into 0 divided by omega plus C. Now from this, can you find the value of C? Yes, so therefore you can check C is equal to, what is the cos of omega 0? Omega into 0, it is a cos 0. Cos 0 is 1 na? So it is like a yes, we can write it as a minus of Vm by omega L. Okay, 0 is equal to minus of Vm by omega L plus C. So therefore C is equal to Vm by omega L. Okay, this is a C. This is equal to C. That is a Vm by omega L. Now we need to put this C in equation 1. Okay, we need to put this C in equation 1, right? So let me write, put this C in equation 1. So if you put this C in equation 1, it is like a I0 is equal to, therefore I0 is equal to Vm by omega L into, yes, omega I am taking here. Okay, so it is a minus cos of omega t into minus cos of omega t. Okay, next here it is a C. Replace this C with Vm by omega L. So plus Vm by omega L, right? So now therefore we can write it as, therefore I0 is equal to, it is like a Vm by omega L into 1 minus cos of omega t. This is the expression for the current in the circuit, that is the I0, right? This is the I0 expression. Now you can check here, we are having the expression for, yes, V0, which is equal to Vs. During 0 to pi, V0 is equal to Vs. Okay, next, during 0 to pi, I0 is this expression. Okay, I0 is this expression. So what this expression indicates, you can check this circuit here. Diode D is in an on state. Okay, it is like inductor is storing the energy. Na? Inductor is storing the energy. If I want to draw the waveform of the I0 during 0 to pi, if we want to draw the waveform of I0, how it will be? You can check at T is equal to 0 or at omega T is equal to 0. This I0 is equal to 0. Let me write, at omega T is equal to 0. I0 will be like Vm by omega L into 1 minus cos of 0 na. So cos of 0 is 1. So 1 minus 1, it is a 0. So that's why I0 is 0. At omega T is equal to pi by 2. That is a 90 degree. Put here cos of pi by 2. Cos pi by 2 is 0 na, right? So cos pi by 2 is 0. So it is a 1 minus 0. So this term will be 1. 1 into Vm by omega L. So I0 is equal to Vm by omega L. At omega T is equal to pi. You can check at omega T is pi means cos of pi. Cos pi is minus 1. 1 minus of minus 1, it is a 2 na. So 2 into Vm by omega L. 2 into Vm by omega L, right? So here it will be 2 into Vm by omega L. At omega T is equal to 3 pi by 2. That is a 270 degree. Okay, that is 270 degree. So at 3 pi by 2, what will happen? It is a 1 minus cos of 3 pi by 2. What is the cos of 270 degree? You can check cos value 1, 0, minus 1. Okay, and again 0 na. Okay, so it is a cos of 3 pi by 2, it will be 0. So again it will be Vm by omega L. And at omega T is equal to 2 pi, it is like I0. Yes, I0 is equal to like your cos of 2 pi. Yes, cos of 2 pi will be 1. So 1 minus 1, 0. So it is equal to 0. So you can check the I0 wave shape will be having, means it will be starting from 0, it will go on increasing, it reaches the peak value of 2 Vm by omega L and again decreases to the 0, right? So you can check the I0 waveform, whatever I have drawn. Yes, so it is a increasing at omega t is equal to pi, it is reaching the peak value. What is the peak value? It is a 2 Vm by omega L. So it is a 2 Vm by omega L. This value will be 2 Vm by omega L. 2 Vm by omega L. Okay. Now please check what is happening in the circuit. Okay. Please check. So you can here at 0 to pi, we know diode is in on state. So we draw this circuit. Okay. This circuit we draw equivalent. Okay. So it is like a initially before t is equal to 0, it is like current in the circuit was 0. So as soon as that t is equal to 0, switch is closed, right? Switch is closed and diode is in on state. Our inductor will oppose the sudden change in the current. So that's why you can check current flowing through the circuit will go on increasing slowly. This is a slowly increasing inductor current or the circuit current is increasing slowly. So here what is happening, as here current is increasing slowly, current is increasing slowly. So in the circuit what is happening, right? In this circuit what is happening, from 0 to pi, it is like inductor is storing the energy. From omega t is equal to 0 to pi, inductor is storing the energy. Always keep it in mind. In the case of inductor, if di 0 by dt is positive, please listen. In the case of inductor, if DIL by dt, let me say consider it as a DIL because current flows through the inductor. Okay. In the case of inductor, if DIL by dt is positive, then the meaning is your inductor voltage is positive, because let me write here. Yes, for inductor, we know V is equal to L into DIL by dt. Okay, or VL is equal to L into DIL by dt. Okay, so if DIL by dt is a positive, the meaning is inductor stores energy. Inductor stores energy. Inductor is storing the energy means what? It is like an inductor is acting as a load on your source. Inductor is acting as a load on a source. Okay. So DIL by dt, in our case, it is a di0 by dt because inductor is connected in a load branch. Inductor is connected in a load branch, and you can check here. Yes, in this waveform, current is increasing now here. Current is increasing from 0 to pi. So what is the slope of this curve? Slope of this curve is nothing but your di0 by dt, which is nothing but the d by dt of I0 means what? Inductor current here. So what is the slope of current flowing through the inductor during 0 to pi? It is a positive. Means your inductor is storing the energy from 0 to pi. From omega t is equal to 0 to pi, what is happening in the circuit? Inductor is storing the energy. Inductor is storing the energy. So definitely your diode D will be in the on state only. Diode D will be in a on state only, right? And when diode D is in on state from 0 to pi, it is like a V0 is equal to Vs. So V0 waveform, you can check the 0 to pi, V0 is same as that of the Vs, 0 to pi. After pi, what will happen? After pi, what will happen in the circuit? If you check after pi, it is like after pi, supply voltage polarity will be reversed. So it is like a minus here and plus here. So please try to understand this. This is very important. Okay. So after pi, supply voltage is negative. Supply voltage is negative means upper plate at a lesser potential, lower plate is at higher potential. Okay, so it is like a plus here, here it is a minus. This supply voltage will try to circulate current in the anti-clockwise direction. But if you check carefully, till omega t is equal to pi, it is like a supply voltage was positive and current was flowing in this direction, that is in the clockwise direction. At omega t is equal to pi, if you check inductor current is here, this current is a non-zero, na? It is a positive. This current is positive. The meaning is current flowing through the inductor, that is a I0 direction is in a downward direction. Here you can check if this current is a positive, the meaning is current flowing through the load branch, that is a current flowing through the inductor is in a downward direction. So at omega t is equal to pi, current flowing through the inductor is a finite value and its direction is in a downward direction. So after omega t is equal to pi, when supply voltage is reversed, this supply voltage will try to circulate current in the anti-clockwise direction. But whether our inductor will allow the sudden reversal of the current through it? No, I am saying whether the inductor will allow the sudden reversal. I am saying why sudden reversal? Because till pi, it is like current flowing through the inductor was yes in a downward direction. Once after pi, once supply voltage will try to release the energy in the anti-clockwise direction. When supply voltage will try to circulate current in the anti-clockwise direction, then anti-clockwise means what? In this branch the current is supposed to flow in the upward direction, na? But whether our inductor will allow the sudden reversal of current means what? At pi current is positive, and if we want the negative current means what? Definitely this current should be, yes, this current should switch from positive to the negative value. But whether the inductor will allow the sudden reversal of the current? No, na. Inductor is having a tendency that it opposes the sudden change in the current. So what is happening in the circuit? From omega t is equal to pi to 2 pi, this inductor, our inductor will go on releasing the energy. Our inductor will go on releasing the energy in opposition to that of the supply voltage. So from pi to 2 pi, what is happening in the circuit? Our inductor is releasing the energy in opposition to that of the supply voltage. Why the inductor is releasing the energy? Because inductor is having a tendency that it opposes the sudden change in the current. So in order to oppose the sudden change in the current, our inductor will release the energy in opposition to that of the supply voltage. Are you getting the point? Means whatever the energy stored by the inductor from omega t is equal to 0 to omega t is equal to pi. Now inductor is utilizing that energy, right? Inductor is releasing that energy in opposition to that of the supply voltage, in opposition to that of the supply voltage. Are you getting the point? So that's why even though after omega t is equal to pi, supply voltage is negative, but our diode will be in a conduction mode only. Why? Because you can check here, as inductor is releasing the energy in opposition to that of the supply voltage, it is like a inductor energy will be greater than that of the supply energy. So that is nothing but inductor voltage is greater than the supply voltage. So if inductor voltage is greater than the supply voltage, definitely our diode D will be in a conduction mode only. Is this clear? Please try to understand this operation. We're having an inductor. Before this, whatever we discussed, it was only resistive. Resistor is the element, it is a passive element. Resistor doesn't stores energy. So there is no issue of releasing the energy also, right? But inductor is the element and the capacitor is also the element we're having. These two elements stores energy in their fields. Inductor stores the energy in magnetic field. Capacitor stores energy in its electrostatic field. Yes or no? Inductor opposes the change in the current. Capacitor opposes the change in the voltage. So here, please try to understand. 0 to pi, we're having the circuit like this. Inductor is storing the energy. So that's why current flow through the inductor, if you check, it is like this. And we have not drawn this arbitrarily. We are having the mathematical proof now. We have derived this expression. And from this expression, we are having this waveform. From this expression, we have drawn this waveform. Is this clear? From 0 to pi, V0 is same as that of the supply voltage, and inductor current or the load current go on increasing. It is like inductor stores the energy. After pi, what will happen? Again, inductor releases the energy in opposition to that of the supply voltage. Okay, so let me write from omega t is equal to pi to 2 pi. From omega t is equal to pi to 2 pi. From omega t is equal to pi to 2 pi. Yes, inductor L releases energy. So when inductor stores energy, we consider the DIL by dt positive, means inductor stores energy. So when inductor releases the energy means what? DIL by dt should be negative. So you can check here. We are having DIL by dt here. It is a decreasing, na? I0 is decreasing. So that's why the slope will be negative only, right? So inductor releases the energy. So we'll be having the circuit like this. Diode and switch. Here it is a supply voltage. And here it is inductor. So this is the minus, here it is plus. This is the Vs. plus minus, this is a V0 inductor, I0 diode D, okay, and this is a switch. Voltage across diode is VD, current flowing through the diode is ID, okay. So let me write here also, during 0 to pi, what is a VD? During 0 to pi, what is VD? 0 to pi, diode is in a conduction mode na, so VD is equal to 0, okay. So let me write here VD is equal to 0, right? I am writing here VD is equal to 0 volt, right? ID is same as that of the supply, load current, and which is equal to source current also. IS also equal to ID is equal to I0. All are same. We're having only one loop, na? All are same. Next, during pi to 2 pi, inductor releases the energy. Okay, inductor releases the energy. You can apply KVL, again we'll be getting the same equation, right? Same equation. So what is the V0 here? We can apply KVL here. V0, let me write. Sorry, VD first. VD is equal to 0 volt. Diode is in a conduction mode. Please try to understand. Even though the supply voltage is negative, but diode D is in a conduction mode only, because inductor energy is greater than the supply energy. Okay, so VD is 0 volt. Next, apply KVL. It is like minus VS minus VD minus V0 is equal to 0. Okay, so VD is here 0 volt. So therefore, V0 is equal to minus VS. Means load voltage is a negative. Load voltage is a negative. You can check. Load voltage here we are having, it is a negative. Right? Load voltage is same as that of supply voltage, but it is a negative. 0 to 2 pi. And what is inductor is releasing the energy means what? Actually in the circuit, what is happening? If you check Vs waveform, as from pi to 2 pi, inductor releases the energy in opposition to that of the supply voltage. In opposition to that of the supply voltage means supply voltage is trying to circulate current in the anticlockwise direction. But inductor, in order to maintain the current, in order to oppose the change in the current, inductor is releasing the energy in opposition to that of the supply voltage. But you can check here, after pi, as time increases, after omega t is equal to pi, as time increases, supply energy also increases. Na? So supply energy increases, supply voltage increases means what? Supply energy will increase. Supply energy increase means what? The opposition to the inductor energy, that is the supply energy. Okay, opposition to the inductor energy is increasing, because inductor is releasing the energy in opposition to that of supply voltage. As time increases after pi, supply voltage magnitude increases, means supply energy increases. So opposition to inductor energy is increasing. If opposition to the inductor energy increases means resultant energy decreases. So that's why your resultant current decreases here. Resultant current decreases. This will continue till 2 pi. This will continue till 2 pi. After 2 pi, we are having again next cycle. After 2 pi, we are having the next cycle. So we'll be getting this type of waveform only. We'll be getting this type of waveform. Okay. So you can check during this interval also. What is the VD? VD is 0 volt because diode is in a conduction mode only. Right? Diode is in a conduction mode. What is V0? V0 is same as that of the supply voltage. It is a negative. Supply voltage is negative. V0 is also negative. So you can check the waveforms. Yes, this is also negative. This is also negative. Current is decreasing. Current is decreasing. Are you getting the point? Okay. This is the circuit operation. This is the circuit operation. Okay. Next, please don't raise the hand. We will discuss all your doubts. Okay. At the end of the session. Right. So next. So now here, what is the V0 average? Can anyone? What will be the value of V0 average in this case? V0 average in this case, what will be the? Yes, V0 average is a 0, right? V0 average is a 0, right? Because you can check average value of this means what? Area under this plus area under this. Addition of these two. You can check whatever the pulse we are having from 0 to pi, the same is there from pi to 2 pi. But it is a reverse, now it is the opposite. So that's why V0 average will be 0. Or you can simplify it by using our expressions. Okay, V0 average. Let me show here. V0 average. That is the average output voltage is equal to 1 by 2 pi integration from 0 to 2 pi. It is a V0 means same as that of the supply voltage. So it is a Vm into sine of omega t into d omega t. If you simplify it, you will be getting a 0 only, right? You will be getting a 0. Next, can you find the I0 average here? Yes, we can find the I0 average. Don't blindly use here I0 average is V0 average by L. No, right? I0 average, you can check the I0 expression waveform. I0 waveform is like this, na? So whatever the waveform we are having from 0 to 2 pi, the same we will repeat from 2 pi to 4 pi. Same will repeat from 4 pi to 6 pi. So what is the periodic angle? It is a 2 pi. Yes or no? So it is a 1 by 2 pi. Integration from 0 to 2 pi. During 0 to 2 pi, what is the expression of I0? We have written. It is a Vm by omega L into 1 minus cos of omega t. Right? Vm by omega L into 1 minus cos of omega t. So it is a Vm by omega L into 1 minus cos of omega t into d omega t. So you can check it is equal to Vm upon 2 pi omega L. Okay, 2 pi omega L into integration of 1 is omega t minus integration of cos of omega t. It is a sine of omega t, right? Limit 0 to 2 pi. So you can check it is equal to Vm upon 2 pi omega L into, it is like 2 pi minus 0 minus sine of 2 pi plus sine of 0. What is the sine of 2 pi? It is a 0. Sine of 0, this is also 0. So only thing is this 2 pi will get cancelled out. So what is the average? Vm by omega L, right? So average is equal to Vm by omega L. So I0 average is equal to Vm divided by omega L. Vm by omega L, right? Is this clear? It is a Vm by omega L. Next, what is the load power in this case? What is the load power? Yes, can anyone? What will be the load power? Come on. Yes, load power 0, right? Load power is a 0. Why? Because you can check real power consumed by the inductor is always 0. We know it. Okay. Or you can take the product of these two, V0 and I0. Okay. And you can find the average value. You can check here. I0 is increasing here. V0 is positive. V0 negative and I0 is decreasing. Means same na. If you take the product of this and this, and if you take product of this and this, you will be getting equal and opposite. Okay. So that's why average will be 0. Right. So that's why we'll be getting the 0. So let me write P0 average is equal to 0. Now, what is the conduction time of diode in this case? Conduction time of diode. Come on. Conduction time of diode. Diode is in on state for all the time, na? Yes or no? Right? 0 to pi also diode is in a conduction mode. Pi to 2 pi also diode is in a conduction mode. So what is the conduction time of diode? Diode is in a conduction mode for all the time. Okay. Right? Diode is in a conduction mode for all the time. Diode is in conduction mode for all time, right? For all time. Okay. So this is the conduction time of diode. If you want for over one cycle of the supply, if you want, then it is like a 2 pi by omega only. Okay. So that is all time only, right? All time only, because you can check here. After this, here diode is in on state na 0 to pi as well as pi to 2 pi. So after 2 pi again the same is repeating. So that's why again diode will be in the conduction mode only. So in this circuit, diode will not turn off. Are you getting the point? Diode will not turn off. It will be in the conduction mode only for all the time, right? Next, so that's why there is a no point of like a PIV rating of a diode and those things. Is this clear? Right? Okay. So this is actually the special case, purely inductive load. Okay. Because most of the books, if you see, they discussed only R load, RL load, RLE load. Okay, most probably RLE load, 3 loads. Generally, they don't discuss like the RE load or L load or C load. But some of the times in the GATE ESE examination, they have asked questions related to this also. So please keep it in mind. Okay, and this point is important. Right, VL is L di by dt. If DIL by dt is positive, inductor stores energy. Also, let me add here, if DIL by dt is negative, the meaning is inductor releases energy. Releases energy. Okay, releases energy. Right. Next. Now let us discuss the circuit operation for a purely capacitive load. For pure capacitive load, what will happen? Right. So same single phase half wave uncontrolled rectifier. HWR means uncontrolled rectifier. Okay, with the capacitive load. Okay, C load, with the C load, capacitive load. Right. Same circuit diagram. Diode D, capacitor C. This voltage is V0. Current is a I0. This is a ID. This is a VD. This is a IS. Okay, so waveform should be like this. Vs, 0 to pi, pi to 2 pi, 2 pi to 3 pi, right? V0, okay, this is a V0, I0, right? This is a till pi by 2 only. Let us discuss the circuit operation. Okay. So, yes, with purely capacitive load, you can put a switch here, right? But I have not shown here. You can consider switch is present. Okay, and this switch is going to close at t is equal to 0. Okay, at t is equal to 0, switch is closed. So Vs is same Vm into sine of omega t. So 0 to pi Vs positive, next pi to 2 pi negative, 2 pi to 3 pi again it is a positive, right? Now before t is equal to 0, before t is equal to 0, it is like a switch was in an open state. Okay, switch was open. So let me write before t is equal to 0, switch was open. Switch was open. So when switch was open means this was open. Okay, so that's why current was not flowing from source towards the load. So therefore there is a no point like a capacitor charges. Okay, so voltage across the capacitor will be 0. So therefore capacitor voltage is equal to 0 volt. Okay, capacitor voltage is equal to 0 volt. Means like here capacitor voltage means in our case now it is a V0. Now it is a V0, right? Next, at t is equal to 0, right? At t is equal to 0, switch is closed, and you can check after this where supply voltage is positive. So switch is closed, the supply voltage is positive, means diode is in a on state. So diode starts conduction. Yes or no? Diode starts conduction. So what will happen in the circuit? Let us discuss. Okay. So for t greater than 0, if we want to draw the equivalent circuit, it will be like supply voltage, polarity, this is positive here, here it is a negative, switch is closed, diode is in a conduction mode, and capacitor, here it is a capacitor go on charging like case. Okay. So let me draw the circuit. For t greater than 0, for t greater than 0, the circuit will be like this: supply voltage, switch is closed, diode is in a conduction mode, and here it is a capacitor. This is a Vs, polarity plus minus, voltage across diode is Vd, current flowing through the diode is Id. Okay. Capacitor C, this voltage is V0 and this current is I0. Right. Now you can check in this circuit. What is the V0 here? Can we write V0 is equal to Vs? That is a Vm into sine of omega t. Yes or no? Right. So let me write V0 is equal to Vs, which is equal to Vm into sine of omega t. Okay. Next, but till which instant that will be true? That depends on the instant till which your diode D will be in a conduction mode. We know diode D is a passive element. It is an uncontrolled switch. Okay. So let us discuss the expression for the current in the circuit. Expression for the current in the circuit. So now you can check here. In this case, okay, we are having supply voltage Vs and this is the V0, right? So if we apply KVL, it is a plus Vs minus Vd minus V0 is equal to 0. Okay. So first thing is Vd is 0 volt because diode is in a on state, right? So now what will happen if we apply KVL to loop? It is like a plus Vs minus Vd minus V0 is equal to 0. Vd is 0. So therefore it is like a Vs is Vm into sine of omega t is equal to V0 na, is equal to V0 where, sorry, yes, is equal to V0. But V0 means what? Voltage across capacitor na. What is the expression for voltage across capacitor? 1 by C integration of IC dt na. Yes or no? 1 by C integration of IC dt. Okay. So let me write it as therefore, yes, therefore Vm into sine of omega t is equal to 1 by C integration of current IC. Instead of IC, let me write it as a I0 into dt. Are you getting the point? Vm into sine of omega t is equal to 1 by C into I0 into dt. Right? Now further we can simplify it as, yes, we need to simplify it. Okay. So we can write it as, yes, this can be written as differentiating both these sides. Okay. Differentiating both these sides because we need to find the expression of I0, no? Expression of I0. So that therefore let me write it as Vm into sine of omega t is equal to 1 by C into integration of I0 dt as it is. Let us differentiate both the sides with respect to dt. Okay, differentiate both the sides with respect to dt. So differentiate both the sides with respect to dt. With respect to dt or with respect to time, you can say. With respect to time. So here it is d by dt of this term na, Vm into sine of omega t, which is equal to 1 by C into d by dt of this integration of I0 into dt. Now you can check here, differentiation of integration means what? Differentiation, that is a derivative, and integration, both are opposite processes na? Yes or no? Suppose if I take the integration of x square and again if I take the differentiation of that term, again we'll be getting the same term na? So that's why these two will be cancel out. Okay, differentiation and integration. So we'll be getting it is equal to 1 by C into I0 only at the right hand side. So what will happen to the left hand side? Differentiation of this term, it is a Vm into what is the differentiation of sine of omega t? It is a cos of omega t into omega, because this derivative is with respect to time. So we need to multiply with omega also. So therefore, what is the I0? I0 is equal to, you can check, omega c into Vm into cos of omega t. Okay, omega c, right, into Vm into cos of omega t, right? This is the expression for the I0, expression for the I0. Is this clear? Are you getting the point? Okay. So now what this current expression indicates? Current is a cosinusoidal function na? Yes or no? Current is a cosinusoidal function. Okay. So you can check at omega t is equal to 0. This current will be, yes, it is like a omega c into Vm, right? At omega t is equal to pi by 2, what will happen? At omega t pi by 2, cos of pi by 2. What is cos pi by 2? 0 na? So current will become 0 at pi by 2, and this is very important point. So at pi by 2, what is happening in the circuit? Let us discuss. That is very important. So let me write here. I am writing here only at yes, omega t is equal to 0. Okay, it is a I0 is equal to omega c into Vm, omega c into Vm, right? Omega c into Vm. This is at omega t 0. At omega t is equal to pi by 2. So what is I0? It is a cos of pi by 2. So it is a 0. So it is equal to 0. So we are having the current waveform. It is a cosinusoidal, and at pi by 2 it is reaching the 0 value. So let us check the waveform. You can check here. I0 waveform we are having. Okay. It is a starting from non-zero value. What is this non-zero value? Yes, you can get here. This value is at omega t 0. It is a omega c into Vm, na? Right? So I can write here. It is a omega c into Vm. This value will be omega c into Vm. This is omega c into Vm. After that, as omega t increases, current will decrease. As omega t increases, cos of that angle decreases. So that's why here current decreases. At omega t pi by 2, at omega t pi by 2, you can check. At pi by 2, current becomes 0 because the cos of pi by 2, that will be 0. So here current is reaching the 0 value at pi by 2. So during omega t 0 to pi by 2, current is decreasing. Similarly, what is happening with the voltage across the capacitor during 0 to pi by 2? You can check. We are having the expression for V0. No, we have written. Yes, here it is. V0 expression we have written. V0 is equal to Vm sin omega t. Na? It is the same method of the supply voltage. Okay, so you can check here. During 0 to pi by 2, supply voltage is reaching the peak value. So that's why here V0 is also reaching the peak value. Okay. At omega t pi by 2, what is happening? Supply voltage is a Vmax, na? So that's why this voltage also Vmax. The meaning is from 0 till pi by 2, your capacitor is like a capacitor charges. At pi by 2, capacitor voltage becomes equal to Vmax. At pi by 2, capacitor voltage becomes Vmax. So you can check in this circuit at pi by 2. Let me draw, or better to draw, let me draw the circuit at omega t is equal to pi by 2, right? Let us discuss. So at omega t pi by 2, what is happening? At omega t is equal to pi by 2, we are having I0 is equal to 0 ampere. What is the V0? Is equal to Vmax, na? Same method of the supply voltage. So circuit will be like this. At pi by 2, I am drawing. Na? So here we are having a diode. Here it is a capacitor. This voltage is pi by 2, means this is a Vmax. This voltage is also Vmax, na? Vm is equal to V0, or V0 is equal to Vm. This is a capacitor C. Now you can check here in this circuit what will happen after pi by 2. After pi by 2, what will happen? This capacitor has reached the peak value, na? After pi by 2, if you check, the supply voltage waveform is decreasing. So supply voltage decreases means as this, can we say that this voltage is greater than the supply voltage? Because our capacitor will oppose the sudden change in the voltage, na? So it is like you can check for the diode at the cathode, the voltage is equal to Vmax. And at the anode, after pi by 2, I am saying, after pi by 2, at the anode of diode, the voltage will be Vs, and voltage at the cathode will be Vmax. So cathode voltage is peak, that is a Vmax. Anode voltage after pi by 2, it is the same as the supply voltage, na? So that's why that's after pi by 2, supply voltage is decreasing. So anode voltage is less than that of the cathode voltage. So what will happen to the diode? Your diode will feel the reverse voltage, and diode will turn off. Are you getting the point? Okay. So in the circuit, what is happening? After pi by 2, diode will be in a reverse bias mode because of the reverse voltage. Because of the reverse voltage. So let me draw the let me draw the circuit. Yes, for omega t is equal to pi by 2 to pi. Omega t is equal to pi by 2 to pi. What is happening in the circuit? Here we have the supply voltage. This voltage is Vs only. Diode will fill the reverse voltage. Capacitor will try to discharge, but diode will not allow the reverse current. Na? So that's why this V0 will be equal to Vm only. So this is a I0. This is your Vd, and this is a Id. Is this clear? So you can check here. After reaching the peak value, when supply voltage decreases, because supply is a sinusoidal we are having, after pi by 2, supply voltage is less than the pi Vm. Supply voltage is less than the Vm. So this voltage is less than that of this voltage. So diode will fill the reverse voltage and diode D will turn off. So once diode turns off, what will happen? Capacitor is not having any path available for the discharging. So that's why your V0 will be constant only. And whether if V0 is constant, V0 will remain constant. After that, what will happen? This diode will never turn on. Na? You can check for negative half cycle also. You can check for positive half cycle of the supply also. Your diode will not, switch into the forward bias mode again. Okay. So that's why the conduction will be only from 0 to pi by 2. Conduction will be from 0 to pi by 2. Is this clear? Right? So please be careful. This is a V0. It is increasing, reaches the peak value, and after that it will be Vm only. I0, diode will be in a conduction mode only from 0 to pi by 2. So let me write here, during 0 to pi by 2, diode is in a on state. Diode D is in a on state only from 0 to pi by 2. After that, the diode is in a off state only. After that, the diode is in a off state only. Are you getting the point? Right? So this is for capacitive load. This is for capacitive load. So let me write here. Next, can we draw the waveform for the Vd? That is a bit interesting. Can we draw the waveform for voltage across diode? Yes, voltage across diode. How it will be? Yes, Vd waveform. Voltage across diode. Right? So Vd. Omega t 0 to pi by 2, pi by 2 to pi, pi to 2 pi, 2 pi to 3 pi. Okay. So yes, 0 to pi by 2. What is the Vd? 0 volt. Na? Diode is in a conduction mode. So Vd is equal to 0. After pi by 2, what will happen? After pi by 2, diode is in off state only. So what is the voltage across diode? You can check this circuit. Diode is in off state. Na? So what is the voltage across diode? Voltage across diode is equal to Vs minus Vm. Na? Vs minus Vm. And after pi by 2, Vs is decreasing. Vs is decreasing. Na? Right? So that's why you can check Vs minus Vm will be negative. Vs minus Vm will be negative. Right? So at omega t is equal to pi, this Vs will become 0 and voltage across diode will reach the V max value, minus V max value. So waveform will be like this. It will be reaching the minus V max till this instant. Okay. So this is equal to your minus V max. Right? You can check now. Vs is decreasing. So difference between Vs and V max, that difference will be negative and it is increasing. At omega t is equal to pi, Vs is 0. So anode voltage is 0. Cathode voltage is Vmax. So 0 minus Vmax. So that's why it is a minus Vmax. After pi, what will happen? After pi, supply voltage is negative half cycle. Na? After pi, supply voltage is negative. Yes or no? So if supply voltage is negative, means this voltage is negative. So what is the Vd? Vd is like this negative voltage minus this Vmax. So that's why, yes, it will be again adding in the negative values. So that will be like this, will be like this till this instant. Let me show you this type of waveform will be getting. Okay, and again till this instant at 2 pi, again we'll be reaching this value, this type of waveform. You can simply apply the KVL and you can check. So this type of waveform we are getting. Okay, this type of waveform we are getting. Again, it will be like this. Only negative pulse. And what is the value of this peak? This is equal to 2 Vmax. This is equal to 2 Vmax. At one side, you can consider Vs. Second side, you can consider Vmax. Take the difference of the two. Vs minus Vmax. During pi by 2 to pi, it is like this. At pi, Vs becomes 0. So 0 minus Vmax. So that's why it is a minus Vmax. This is equal to minus Vmax. Right? From pi till this instant is like a 3 pi by 2. At 3 pi by 2, what is the supply voltage? At 3 pi by 2, supply voltage is minus Vmax. Na? So supply voltage is minus Vmax, and at the cathode voltage is Vmax. So minus Vmax, minus Vmax, and that minus Vmax. So that will be your minus 2 Vmax. Difference we are saying, na? Anode voltage minus cathode voltage. So that's why it is a minus 2 times Vmax. Again at 2 pi, it will be again minus Vmax. Again, it will be 0, and this type of waveform will be getting voltage across the diode. So diode will be in a conduction mode only from 0 to pi by 2. What is the PIV rating here? PIV rating, yes. 2 times Vmax, na? Peak inverse voltage is 2 times Vmax, right? So let me write PIV rating of diode. PIV rating of diode is equal to 2 times Vmax, right? Conduction time of diode. Conduction time of diode. What is the conduction angle of diode? It is a pi by 2, na? So conduction time is pi by 2 divided by omega. So it is like a pi by 2 omega, right? Pi by 2 omega. Is this clear? Right? So, right? So this is about the purely capacitive load. These are the special circuits, let me tell you, because generally on rectifier, okay, in real life, if you check, we're having the loads like a purely resistive or inductive type of loads, okay, or RLE type of loads, okay, because capacitive load generally we don't have, right? So very less loads we are having, right? So this is these are the special cases we discussed, the purely inductive load and purely capacitive load, right? Next, now let us discuss the RL load. Let us discuss the operation for the RL load. So, sir, how previous one is called rectifier? Output voltage is same as that of. No, that's why I told you that these are the special cases, right? We cannot say that this is the rectifier circuitry, but sometimes they ask the question like, for a single phase half wave uncontrolled rectifier, means you need to consider that we're having a supply, we're having a diode, and we're having a load, and on that load, in the load, we are having the inductor or capacitor, right? So what type of nature will be there, right? That we have discussed. Okay. Yes. Next, let us discuss the RL load. RL load. Now in the load, we are having the resistor and an inductor. So let's discuss what will happen. Okay, so resistor and inductor. Single phase half wave uncontrolled rectifier with the RL load. Okay, RL load. Right. So, let me draw the circuit. This is the Vs, diode D, voltage across diode is Vd, current flowing through the diode is ID. This is a IS RL V0, and here it is a I0, right? So, pi, 2 pi, and here it is 3 pi, right? 2 pi and 2 pi. This is the VS. This is your VL. Okay. Sorry, VR, not VL, VR. Voltage across resistor. So now let us discuss the circuit operation here. V0 will be like this. Consider this angle is theta. This is a pi. Here it is a beta, right? So this is a theta. This angle is theta. Okay. So, yes. Due to the lack of space, actually I have not drawn the waveform of VD, but we'll draw at the end. Okay, voltage across diode, because diode voltage waveform is also very important, right? They have asked the questions for calculating the conduction time of diode, PIV rating of diode, and suppose if the diode is replaced with a thyristor, then in that case, for finding the circuit turn of time, we require the voltage across that devices, na, right? So I will draw that at the end. So single phase half wave uncontrolled rectifier with RL load. Okay. So same circuit diagram, the only change is in the load we are having a resistor and an inductor here, right? Resistor and an inductor. Already we discussed about the separate resistor, separate inductor case. Resistor is the element which never stores energy in its resistor is not having any field. Okay. So resistor never stores the energy. Okay. The only thing is inductor is the element which stores the energy and as well as it releases the energy. Okay. Now, so we are having this circuit. Suppose initially circuit will be at the rest position. Okay. So the meaning is before this cycle means this is like a very first cycle we are having. Okay. Before t is equal to 0, the circuit was like at the rest position, means before that there was no current flowing through the inductor. So the energy stored by the inductor was 0. Okay, energy stored by the inductor was 0, right? Next, you can check here after omega t is equal to 0, after omega t is equal to 0, what is happening? Let us consider for omega t is equal to 0 till omega t is equal to theta. From omega t is equal to 0 till omega t is equal to theta. It is like we are having a supply voltage here, it is a positive, right? And that is greater than the VR. Please check how we have drawn the waveform of VR. You can check here, VR means voltage across resistor. VR means the voltage across resistor. So let me show here. VR, that is this branch, this is a voltage. This is a voltage across resistor VR. And voltage across inductor, it is like a plus here. Let me show here, plus here, minus here. This is a voltage across inductor. So V0 means what? It is a combination of VR and VL, right? It is a combination of VR and VL, that is nothing but your V0. So now you can check, as we know, in the case of resistor, VR is equal to what? I0 into R. So whatever the waveform of I0 we are having, na, the same waveform will appear for the VR. The nature will be same. The only thing is there will be a change in magnitude. There will be the change in magnitude. Okay, so you can check I0 waveform and your VR waveform, both will be in phase only, right? Both will be in phase only, right? So here 0 to theta, I0 increases, VR also increases. Theta to beta, I0 decreases, VR also decreases. We'll discuss why the I0 is increasing and here I0 is decreasing, and 0 to theta why the I0 has increased. We'll discuss. Okay. Next. Now let us check here. Can we write here V0 is equal to VR plus VL? V0 is equal to VR plus VL. So therefore VL is equal to what? V0 minus VR. VL is equal to V0 minus VR. Okay. So one by one, let me write here. Yes. For omega t is equal to 0 to theta. For omega t is equal to 0 to theta. So for 0 to theta, you can check 0 to theta, right? Vs is positive. So Vs positive means polarity is a plus here, minus here. Okay, here it is a plus, here it is a minus. V0 is like plus here and minus here. Okay, V0 is like a plus here and minus here. Okay, so what is the voltage across the diode here? If this is the highest potential point, here it is a highest potential to appear. Definitely our diode will be in a forward bias mode. Diode starts conduction. Diode starts conduction. So for 0 to theta, we can draw the equivalent circuit. Here it is a supply voltage. Diode is in a conduction mode. Here we are having a resistor R and an inductor L. This is a Vs. Polarity is a plus here, minus here. Diode D. Voltage across diode will be Vd. Okay. This current is a ID. This current is a Is. R, L. This voltage is a V0. Okay. And voltage across, let me show you. The voltage across resistor is here. And voltage across inductor is here. Plus minus VL. Okay. So it is like 0 to theta. Diode is in a conduction mode. Current is flowing like this. So Vd is equal to 0. Vd is equal to 0 volt, right? Vd is a 0 volt. What about the V0? V0 is the same as that of the supply voltage. V0 is equal to same as that of the supply voltage, right? Now, what about the I0? You can check here. In the load, we are having the inductor. Before omega t is equal to 0, what was the current flowing through the inductor? Current flowing through the inductor was 0. Because I said, na, before t is equal to 0, it is like a circuit was at the rest position. Current flowing through the inductor was 0, right? So after omega t is equal to 0, yes, the diode is in a conduction mode. Our inductor will not allow the sudden change in the current. So you can check here, I0 waveform is, yes, it is a current I0 is increasing slowly. Current I0 is increasing slowly. You can check the I0 waveform in the case of purely resistive load, and you can check the I0 waveform in this RL load. Both waveforms are different. In a purely resistive load, I0 waveform is like a in phase with the supply voltage, right? But here your I0, you can check the slope here. You can check the slope here. Current I0 is increasing slowly. Why it is increasing slowly? Because why it is increasing slowly? Because of this inductor. Inductor is the element which opposes the change in the current, na, right? So therefore, current flowing through the inductor go on increasing slowly. current flowing through the inductor means what? Current flowing through the load. Current flowing through the load is nothing but current in the circuit, na? So that's why your circuit current go on increasing slowly. Circuit current go on increasing slowly. So let me write here. Yes, during this interval, yes, I0 increases slowly. I0 increases slowly, right? Because of presence of inductor. Okay, as inductor opposes change in current, right? Inductor opposes change in current, right? Change in current. So that's why definitely I0 waveform should be like slowly increasing. It will be slowly increasing. Now you can check here where V0 is equal to Vs. Okay. And V0 means what? VR plus VL. Na? You can apply KVL to this part only. Only to this part I am saying apply KVL. It is a plus V0 minus VR minus VL. Na? Right? So it is like a plus V0 minus VR minus VL. So what it indicates? It indicates VL, okay, is equal to V0 minus VR. Very important. VL is equal to V0 minus VR. But what is V0 during this interval? V0 is equal to Vs, na? So can I write VL is equal to Vs minus VR? So voltage across inductor is what? It is a Vs minus VR. So you can check during 0 to theta what is happening. During 0 to theta in the circuit, what is happening during 0 to theta? The red one is a waveform of VR and the black one is a waveform of Vs. Okay, so you can check here during 0 to theta whether Vs is greater than VR or less than VR. Definitely it is a yes, greater than VR. Okay, so if Vs is greater than VR, so what about the VL? Vs is greater than VR. So VL is positive or negative? VL is positive only, na? Right? So let me write here. Yes, as Vs is greater than VR. Vs is greater than VR. So Vs is greater than VR. So therefore, VL is equal to Vs minus VR is a positive. VL is a positive. Now VL positive means what? We know now voltage across inductor is L into di by dt. Yes or no? Right? Voltage across inductor means what? It is a L into di means in our case what? It is a I0 na? Inductor is in a load branch na? So that's what it is a di0 by dt. It is a positive na? So what this indicates? L di0 by dt is positive means definitely your di0 by dt is also positive. So what this indicates? di0 by dt positive. Just now we discussed in the previous case, purely inductive. If di0 by dt is positive, the meaning is our inductor is storing the energy, na? Yes or no? Right? So let me write here. As di0 by dt is positive, as di0 by dt is a positive, so therefore inductor stores energy. Inductor is a storing the energy. Very, very important. During 0 to theta, I am saying during 0 to theta, inductor is a storing the energy. Right? So you can check the waveform here. If we are having the waveform for Vs and VR like this, yes, and as we know, VL means what? Vs minus VR, na? So can I, if we take the difference of this waveform and this waveform, can I say that? Yes, can I say that? Yes. Yes. So can I say that Vs minus VR means this shaded region, this indicates voltage across the inductor? Yes or no? You can check now. Vs minus VR means what? This shaded region. This is nothing but your voltage across inductor, na? Voltage across inductor. So let me write here. This indicates your voltage across the inductor during 0 to theta. So till now, whatever we discussed, it is like from 0 to theta, inductor stores the energy, current flowing through the circuit go on increasing slowly. V0 is same as that of the supply voltage. Diode D is in a conduction mode. That's it. Are you getting the point? Right? Next. Now what will happen after theta? What will happen? That is interesting. Let us discuss after theta what will happen. So let us consider from theta to pi. From omega t is equal to theta to pi. What will happen? Let us discuss. Okay. So from theta to pi. For omega t is equal to theta 2 pi. So for theta 2 pi, yes, we are having the supply voltage is positive or negative during this interval. Supply voltage is positive only, na? So it is like a plus here, minus here. This is a Vs, right? Supply voltage is positive only. Diode D will be in a conduction mode. What will happen to the inductor? And yes, V0 will discuss. This is a V0. This is a R. This is a L. This voltage is like a VR. This is like a VL. Okay. This is a VD. And here it is a ID. This current is a IS. Okay. So after theta, what will happen? After theta, what will happen? So you can check here. After theta, yes, waveforms we are having. After theta, what is happening in the circuit? You can check. After theta, it is like your Vs is less than that of your VR. Na? So if Vs is less than VR means what about the VL? VL will be positive or negative? Yes. Vs. Yes. In this also, VL is Vs minus VR. If Vs is less than VR means VL is negative. If VL is negative means what? Inductor will go on releasing the energy. Inductor will go on releasing the energy. So let me write what is happening in this circuit during this interval. Okay. So it is like a diode is in a conduction mode. So VD is equal to 0 volt. VD is equal to 0 volt, right? Next, V0, you can apply KVL. V0 is equal to Vs. That is same as that of the supply voltage. Again, apply KVL to this part. We will be getting plus V0 minus VR minus VL is equal to 0. So therefore, VL is equal to what? It is a V0 minus VR. But V0 is Vs, na? So it is a Vs minus VR. So this is a VL. During this interval, whether Vs is less than VR or greater than VR, you can check. Vs is less than VR, na? VR is like this, Vs is like this. So Vs is less than VR. If Vs is less than VR, what about the VL? If Vs is less than VR, VL will be negative. Okay, so as Vs is less than VR, so therefore VL is a negative. VL negative means what? Di0 by dt, positive or negative? Di0 by dt also negative. Okay, so let me write. VL is a negative. And what is VL? It is a L into Di0 by dt. It is a negative, right? So therefore Di0 by dt is a negative. Di0 by dt is negative. The meaning is inductor releases the energy. Inductor releases the energy. Inductor L releases energy. Inductor L releases energy. So you can check here. Yes, in the waveforms, yes, what is happening? From theta to pi, Vs is less than VR. Inductor releases the energy. So current go on decreasing. Current go on decreasing. Now you can check during this interval, inductor is releasing the energy because at omega t is equal to theta, current flowing through the inductor is positive. Na? Whether it is a positive or negative current, it is a positive. So what is the direction of current flowing through the inductor? It is in downward direction. Na? Current flowing through the inductor was in a downward direction, right? So after theta, supply voltage magnitude is lesser. So what will happen? Yes, our inductor will, in order to oppose the change in the current, our inductor will release the energy in this same loop. Na? Supply voltage is, yeah, let me, yes. Yeah. Supply voltage is polarity plus here minus here only theta 2 pi because supply voltage is positive only. Na? So supply voltage polarity is plus here minus here. Inductor also releasing the energy in this direction. Supply voltage also circulating the current in this direction. So can we say that inductor energy and supply energy both will be adding? Yes or no? Both are circulating the current in the same direction. So that's why inductor energy and supply energy both will be adding here. Both will be adding during this interval. I am saying during theta 2 pi. Okay. So let me write. During this interval, during omega t is equal to theta 2 pi. Yes. Supply energy and inductor energy. Yes, both will be adding. Both will be adding. Okay. Means both will be assisting to each other like, okay, both will be adding. Okay, so you can check here now. Yes, so inductor is releasing energy, supply voltage magnitude is decreasing, means supply energy is decreasing actually, strictly speaking. Okay, so this energy is decreasing, so that's why inductor is assisting the energy. Okay, so inductor energy is assisting to the supply energy. Okay, so here current go on decreasing, right? Because di0 by dt negative na, so negative means current should be decreasing. Okay, so during this interval theta to pi, what is V0? We discussed that V0 is same as that of the supply voltage only. Okay, next, after pi, what will happen? After pi till beta, what will happen in the circuit? You can check. At pi, current is like a positive only. At omega t is equal to pi, current is a positive only. After pi till beta, what will happen? Because after pi, supply voltage polarity is negative na. So what will happen? Let us discuss. So for omega t is equal to pi to beta, for omega t is equal to pi to beta, supply voltage is negative, so minus plus, supply voltage will try to circulate current in the anti-clockwise direction. But whether our inductor will allow the sudden reversal of the current through it? No, inductor will not allow the sudden reversal of current, right? So this is the VD, this is the ID, this is the IS. Okay, here it is the I0, RL, V0. Next, consider this as a VR, this as a VL. Okay, this as a VR, here it is a VL. Okay, next, now at omega t is equal to pi, at omega t is equal to pi, where having the current is a positive. Current positive means direction of current is in the downward direction only na, direction of the current flowing through the load or the inductor is in a downward direction only. After pi, supply voltage polarity is reversed, means supply voltage will try to circulate current in the anti-clockwise direction. But whether our inductor will allow the sudden reversal of the current? No, inductor will not allow the sudden reversal of the current, right? So due to that, what will happen? Because you can check na, current here downward direction, that is nothing but total current is in a clockwise direction. After pi, supply voltage is trying to circulate current in the anti-clockwise direction, means in this branch, load branch, the current, yes, should flow in the upward direction. But whether our inductor will allow the sudden reversal of current from positive value to the negative value? No, right? So that's why what is happening in the circuit, inductor will release the energy after pi. Inductor will release the energy after pi. Now my question is, during pi till beta, whether inductor energy and supply energy both will be in the same direction or both will be in the opposite direction? Yes, during pi to beta, inductor energy and supply energy both will be in the same direction, that is adding, or both will be opposing. Yes, opposite, right? Both will be in the opposite direction. Correct? Good. So here let me write, from pi to beta, from omega t is equal to pi to beta, inductor releases the energy, supply voltage is trying to circulate the energy like this. But you can check near to the pi, near to the, now you might be thinking that sir, supply voltage is having a very high voltage na, very high magnitude, so how the inductor can circulate the energy in opposition to that of the supply voltage? You can check here, near to the pi, you can check, at omega t is equal to pi, supply voltage 0. After pi, what is happening? Supply voltage is increasing na. Near to pi, what is happening? The near to the pi, supply voltage magnitude is very less na. Near to the pi, supply voltage magnitude is less, so that's why supply voltage energy is also less. So that's why supply energy is less. So can we say that our inductor can successfully release the energy in opposition to that of the supply voltage and through the diode? Yes. Are you getting the point? Okay, here supply voltage is not the constant. So that's why what is happening, inductor energy, you can check na, inductor energy is what? It is a half Li square na. Inductor energy is equal to half into L into I square. And what is the current flowing through the inductor at omega t is equal to pi? It is a non-zero current, it is a high current na. So what is the energy of the inductor? Definitely energy of the inductor is a high, because current is a high. So inductor energy is high, magnitude of the supply voltage near to the pi is very less. So definitely our inductor can successfully release the energy in opposition to that of the supply voltage and through the diode. Okay, why the inductor is releasing the energy? Because inductor releases the energy in order to oppose the sudden change in the current, right? So here let me write, yes. So inductor is releasing the energy from pi till beta. At beta, what is happening? At omega t is equal to beta. Why the inductor has released the energy only till beta? Yes, why the inductor has released the energy only till beta? What is happening? Because after beta, it is like our inductor energy is less than that of the supply energy. So that's why resultant current, that's why your resultant current will not be clockwise now. Because as after pi, as omega t increases, supply energy also increases, na? Supply voltage increases, so supply energy will increase. So inductor is releasing the energy only till beta. After beta, it is like a supply energy is greater than the inductor energy. So that's why our resultant circuit will be at the rest position next. Okay, so from pi to beta, let me, yes, yes, we are having the circuit like this. So inductor L releases energy. Inductor L releases energy, right? Inductor is releasing the energy. Now, when inductor releases the energy, so resultant current will be in the clockwise direction only. Yes or no, right? So resultant current in the clockwise direction. So again, diode will be in a conduction mode. VD is equal to 0 volt, right? So VD 0 volt. What about the V0? V0 is equal to Vs only. V0 is equal to Vs only, right? What about the VL now? VL, come on, VL means what here? V0. Yes. Or let me apply KVL. You will be getting V0 is minus Vs. Okay, minus Vs minus VD minus V0. Okay, KVL will be like this. Let me write the KVL here. So KVL to loop, KVL to loop. So we'll be getting it as minus Vs minus VD minus V0 is equal to 0. So VD is 0, na? Diode is in a conduction mode. So therefore V0 is equal to minus Vs. V0 is equal to minus Vs. Okay, now V0 is minus Vs. You can apply KVL to this loop. KVL to this loop, it is a V0 is equal to VR plus VL, na? Now here V0 is minus Vs. So minus Vs is equal to VR plus VL. So this indicates VL is equal to minus Vs minus VR, right? VL is equal to minus Vs minus VR. So you can check both are negative means what? Inductor voltage is negative only, na? So inductor voltage is negative means di0 by dt is negative. So that's why inductor is releasing the energy. Inductor is releasing the energy. So you can check the waveform. Okay, V0 is equal to minus Vs. Yes, I0 is decreasing because inductor is releasing the energy, and to the inductor energy, supply energy is opposing, na? And after pi, as the time increases, supply voltage magnitude increases, so supply energy increases. So due to that, to the inductor energy, the opposition is increasing, na? To the inductor energy, opposition is increasing, right? So that's why resultant current will be decreasing. So you can check the waveform. Here the resultant current, here the resultant current will be decreasing, right? Resultant current will be decreasing. Okay. So now, yes, what about the V0? V0 will be same as that of the supply voltage. Supply voltage negative, V0 is also negative. Okay. So till beta, it will be like this. Now what? From theta till beta, from omega t is equal to theta till beta, what will be the VL? 0 to theta, we have indicated VL means this shaded portion, na? So from theta to beta, yes, what will the VL? VL is equal to, you can check from theta to pi. From theta to pi, VL is equal to Vs minus VR, na? So Vs minus VR, that will be like this. Yes. Yes. Vs minus VR means this magnitude. I am writing only magnitude here. From pi to beta, supply voltage is negative and this is positive. So this voltage minus this voltage means both will be negative. So your VL will be like this. Okay. This shaded region and this shaded region, it indicates your VL. So please check it carefully. It is a very interesting. Please check it carefully. From 0 to theta, you can check. This is a VL. It is a positive VL because during 0 to theta we had a VL positive because Vs was greater than VR. Inductor was storing the energy. From theta to beta, where VL is like this. This is shaded region. Na? This is the VL. This VL is a negative VL because your VS is less than VR. Na? VS is less than VR. So that's why your VL is equal to VS minus VR. So that's why it is a negative actually. Okay. Now you can check. Can we say that this area and this area, I am saying this area and this area, that is 0 to theta, the value of VL area, and theta to beta, the area of this VL waveform or this shaded region, whether both will be same or different. Both will be same only. Please try to understand. 0 to theta VL and theta to beta VL, both are same. You can check area of this one and area of this, both will be same, you will be getting. So what it indicates, during 0 to theta, it is like a VL is positive. Theta to beta, it is like a VL is negative. So the meaning is 0 to theta, whatever the energy stored by the inductor is equal to theta to beta, that is the energy released by the inductor. Means whatever the energy inductor is storing now from 0 to theta, the inductor is releasing the same energy from theta to beta. So what is the average energy of the inductor over a one cycle? It is a 0 only now, right? So please keep it in mind. Always keep it in mind. In the case of inductor, right? In the case of inductor, energy stored by the inductor is always equal to the energy released by the inductor. And also the average voltage across the inductor is also 0. Average voltage across the inductor is also 0. You can check here wherever VL positive means this one area and VL negative is this area. So you can take the average. Average will be your 0 only. Okay, average will be 0, right? So that's why you can check in a purely inductive load also. Na? In a purely inductive load, what is the V0 we are having? V0 is a one pure sinusoidal supply, na? 0 to 2 pi. So average voltage, that was 0 in that case also. Here also it is a 0 only. Okay, next. So this is from pi to beta, right? This is from pi to beta. After beta, what will happen? From beta to 2 pi. From omega t is equal to beta to 2 pi. From omega t is equal to beta to 2 pi. What will happen in the circuit? Yes, now inductor has already released the energy, right? So inductor is not having the energy to release, or it is like a supply energy is greater than the inductor energy. So what will happen? As inductor energy is less than that of the supply energy, so resultant current will try to circulate. Supply will try to circulate current in the anti-clockwise direction. But whether our diode will allow the anti-clockwise current? No, na. So that's why diode will become a reverse bias and diode will turn off. So from pi to beta, it is like circuit will be at the rest position. Circuit will be at the rest position. So this is a Vs minus plus. This is the diode voltage Vd. This is the Id. Okay. RL. This is a V0. Is. I0. Right? I0. So now you can check in this circuit. Diode is in a off state. Na? Diode D is in a off state. So when diode is in a off state, whether the current will flow from source towards the load? No. So our circuit currents I0, ID, Is all will be 0 ampere only. Next, what about the V0? Current is not flowing through the load. So therefore load voltage also equal to 0, right? V0 also equal to 0. What about the Vd? You can apply KVL to this loop. Okay, it is like a plus Vs plus V0 plus Vd is equal to 0, right? So therefore, yes, in that V0 is 0. So therefore Vd is equal to minus Vs. Vd is negative. Vd is a negative voltage. From omega t is 0 till omega t is equal to beta. What was Vd? Vd was 0 now because diode was in a conduction mode. From beta till 2 pi, what is the Vd? Vd is a negative voltage. It is the same method of supply voltage, but it is a negative. Okay, but it is a negative. Is this clear? So these are the waveforms. So you can check the waveform from omega t is equal to beta to 2 pi V0 0, I0 0. Okay, we can draw the waveform for Vd also. Let me draw the waveform for Vd. Vd waveform. Voltage across diode. It will be like this. Vd 0, this is omega t, from 0 till beta pi, here it is a beta and here it is a 2 pi, right? Next here it is a 3 pi. Yes, the waveform will be like this. From 0 till beta, it is a 0 only na, because diode is in a conduction mode. After beta till 2 pi, it is same as that of the supply voltage but negative. You can check at omega t is equal to beta. What is supply voltage at omega t is equal to beta? At omega t is equal to beta, supply voltage is this value na? Supply voltage is this value. So therefore diode voltage at beta suddenly increase to the negative value, non-zero negative value. So that's why here you can check waveform of voltage across diode. It is suddenly increasing, right? Suddenly increasing. And after that, same as that of the supply voltage. This will continue till 2 pi. After 2 pi again, the same cycle repeats. Same cycle repeats. Okay. So from pi to beta, we can say diode is in a conduction mode. Diode is in a conduction mode. Okay. Beta to 2 pi, diode is in an off state. Right. So this is the circuit operation for REL load. Okay. For REL load. Please try to understand. I am repeating it. What is happening in the circuit? From omega t is equal to 0 to theta, Vs is greater than your Vr, VL is positive, right? Inductor go on storing the energy. V0 is same as that of the supply voltage. I0 increases slowly. Vd is equal to 0 volt. This is from 0 to theta. From theta to pi, what will happen? From theta to pi, from theta to pi, Vs is less than Vr. Okay, VL is negative. Inductor releases the energy. I0 decreases. Okay, V0 is same as that of the supply voltage. This is from theta to pi. Pi to beta, Vs is negative. Inductor opposes the sudden change in the current. Inductor releases the energy in opposition to that of the supply voltage. Okay, I0 decreasing, and beta I0 becomes equal to 0. V0 is same as that of the supply voltage. But from pi to beta, Vs is negative, so V0 is also negative, right? Pi to beta, diode is in a conduction mode, so Vd is equal to 0 only. Beta till 2 pi, from omega t is equal to beta till 2 pi. Okay, from beta till 2 pi, what is happening? It is like a inductor energy is less than the supply energy. So diode D will be in the off state. Diode is in off state means circuit current will be 0. Circuit current is 0. Load voltage is 0. Load current is 0. Right? So you can check both are 0. And diode voltage is same as that of the supply voltage, but it is a negative. So this is the diode voltage. Okay. So next. Now we are going to derive the expressions. Okay, derive the expressions. One more thing, this beta is known as the extinction angle. Beta means the extinction angle. Let me write here. Yes, this beta means what? It is the extinction angle. What is the extinction angle? Extinction angle means it is the angle till which, the inductor releases the energy. Inductor releases the energy. Always keep it in mind. Beta value is always greater than pi. Beta value is always greater than 180 degree. In some of the local books, local publications, they have given that beta means only from pi to beta they consider the angle, and they are saying that beta is equal to this. Beta means like this angle only they are saying, but it is not true, right? Don't refer the local books. Okay, so beta is always greater than pi, right? So next, let me write here. Beta is the extinction angle. Beta is extinction angle. What is the extinction angle? It is the angle. It is angle or instant, you can say. It is angle till which inductor L releases energy. Inductor L releases energy. Is this clear? Right? So next, V0 average. Come on, V0 average. Average value of output voltage. If you check the waveform, yes, V0 waveform. From 0 to 2 pi, whatever the waveform we're having, the same will repeat from 2 pi to 4 pi. So periodic angle is 2 pi. Na? So it is like 1 by 2 pi. Right? Integration from 0 to beta. Integration from 0 to beta. We need to take. Okay. So let me write it as 1 by 2 pi. Integration from 0 to beta. Vm into sine of omega t into d omega t, because value of V0 is same as that of supply voltage. Na? So it is equal to Vm by 2 pi into integration of sine is minus cos of omega t limit 0 to beta. So if we simplify it, it will be Vm by 2 pi into Vm by 2 pi into, it is like minus cos beta, right? Plus 1. So it is a 1 minus cos of beta. This is a V0 average. V0 average. Correct? V0 average. Next, I0 average. Average load current. I0 average is equal to. So how to find the I0 average? Please check. In the load, we are having a resistor and inductor. Na? So V0 is equal to VR plus VL we are having. Okay, V0 is equal to VR plus VL. Out of that, what is the average voltage of the inductor? It is a 0. Na? So average voltage of the inductor is a 0. I am saying average voltage. Average voltage of the inductor is 0. So therefore, can I write V0 average is equal to VR average? Right? So because inductor is storing the energy from 0 to theta, and from theta to beta, inductor is releasing the same energy. So average energy is 0, average voltage 0, everything is 0, right? So therefore V0 average is equal to VR average. So therefore we can write V0 average is equal to VR average means what? I0 average into R, na? Because VR means what? I0 into R, and R is the, yes, we are having a constant value, na, R, resistance, ohm. So it is I0 average into R. So therefore I0 average is equal to V0 average divided by R. Okay, V0 average divided by R. For REL load, always keep it in mind, I0 average is always equal to V0 average by R, even though the inductor is present in the load branch, but I0 average is V0 average by R only, because average voltage across inductor is 0. Average voltage across inductor is 0, right? Next, V0 RMS. V0 RMS. RMS value of output voltage. Root means square, na? Square root of mean of squared value. So you can write it as 1 by 2 pi integration from 0 to beta V0 square into d omega t, na? To the power 1 by 2. So it is equal to 1 by 2 pi integration from 0 to beta. V0 is Vm sin omega t, na? So it's square. Vm square sin square of omega t d omega t to the power 1 by 2, right? So this can be written as, I am taking this Vm square outside divided by 2 pi outside. So it is a Vm upon 2 root 2 pi. Okay, Vm upon root 2 pi integration from 0 to beta 1 minus cos of 2 omega t divided by 2 into d omega t to the power 1 by 2, right? So it is equal to, further can we take this to outside? Yes. So it is a Vm upon 2 root pi into integration of 1 is omega t, okay, minus integration of cos of 2 omega t, it is a sine of 2 omega t divided by 2, right? Limit 0 to beta to the power 1 by 2, right? So next, put the limits. So we can write it as, therefore V0 RMS, therefore V0 RMS is equal to beta minus 0, right? Beta minus 0. Sorry, before this term, Vm upon 2 root pi, Vm upon 2 root pi into beta minus 0 minus sine of 2 beta by 2 minus sine of 2 beta by 2, okay, to the power 1 by 2. Or this can be written as Vm upon 2 root pi into, it is like a beta minus 2 beta divided by 2 to the power 1 by 2. This is a V0 RMS. I0 RMS we cannot directly write for REL load. Okay. So for that, actually, we need to derive the expression for I0, right? So how to derive the expression for I0, right? Let us discuss. So yes, you can check the equivalent circuit for omega t is equal to 0 to beta. We're having the circuit like this, na? Vs, here it is a diode in a conduction mode, here it is a R, and here it is a L. This type of circuit we're having. So Vs is Vm sin omega t. This is a R, L. This is a V0, and here it is a I0, na? Right? This circuit we're having from 0 to beta. And what is the V0? V0 is equal to same as the supply voltage. Yes or no? We have written V0 is equal to Vm into sine of omega t. But what is the V0? V0 is equal to what? It is a VR plus VL, na? And what is VR? I0 into R. I0 into R plus VL means L into di0 by dt is equal to Vm into sine of omega t, right? Are you getting the point? V0 means what? I0 into R plus voltage across inductor L into di0 by dt. So same thing. I have replaced V0 with this expression. So further we can write this as di0 by dt, okay, plus R by L into I0, which is equal to what? Vm by L into sine of omega t. Sine of omega t. This is a differential equation in the form, yes, it is like a dy by dx plus py is equal to q. This is a standard expression, na, differential equation. How to simplify this differential equation? Yes, how to simplify this? We need to find the integrating factor, which is equal to e to the power integration of p into dx. And after that, we need to write the solution. What is the solution? Y into integrating factor is equal to integration of q, okay, into integrating factor into dx plus c. This is actually the differential equation solution we're having. So our differential equation is in this form only. Instead of y, we're having I0. Instead of x, we're having t. Instead of p, we're having R by L, na? Or instead of q, we're having this term Vm by L into sine of omega t. Okay. So let me find the integrating factor for this. Okay. So IF. Yes. Therefore, IF is equal to e to the power p into dx. P means R by L, na? So e to the power integration of R by L into dt. So it is like e to the power RT by L. This is the integrating factor, right? So next, what is the solution? Solution of, yes, solution is y into integrating factor, na? In our case, y means what? It is a I0. So I0 into integrating factor. So I0 into e to the power RT by L is equal to integration of q. What is a q in our case? Vm by L into sine of omega t. Okay. So it is a Vm by L into sine of omega t into again integrating factor, na? Into IF is there, integrating factor. So we need to multiply with this term into e to the power RT by L into dt plus c. Now you can check this integration we are having sinusoidal, that is a trigonometric term, and the exponential term also, na? So we need to simplify it with the help of integration by parts. Yes or no? What is the integration by parts? We need to check which is the, what is the first function? LIATE, na? We are having LIATE. What is a L? Logarithmic, na? I means inverse. A means, yes, arithmetic. T means trigonometric, and E means exponential. So this will be like your second, and this will be like your first function. So by parts means it is like a first integration of second, and those things we need to do. Okay. So I'm directly writing the solution. Solution of this differential equation. Okay. We'll be getting it as equal to I0 is equal to Vm upon under root or Vm upon mod Z. Let me write it as in terms of mod Z. That will be good. Vm upon mod Z into sine of omega t minus theta. Okay, sine of omega t minus theta minus Vm upon mod Z. Okay, into sine of minus theta. So that minus this means plus into sine of theta into e to the power minus r upon omega L. Okay, into omega t, r upon omega t, r by L into omega t. Into t, right? So this is the actually solution of this equation. now can we find the RMS value of this expression with the help of this expression? Not possible, na? Is this clear? So that's why please keep it in mind. As and when if the load is a real load, okay, right? We are not going to find the RMS value. And also if RMS is we are not calculating, so we cannot directly find the input power factor also. So in that case, what we need to do, we for real load or for real E load, okay, that is like if the supply voltage is sinusoidal and if the supply current is non-sinusoidal, then in that case input power factor how to find, that we will discuss at the end. Okay, at the end I am going to tell you. Okay, so please keep it in mind. For real load we are not going to write the expression for I0 RMS, and at the same time we are not going to write the expression for input power factor. How to find the input power factor expression, that I will tell you at the end. Okay, because for that we need to take the help of Fourier series expression, Fourier series analysis. Okay, so we'll discuss it later. So is this clear? So this is the expression, right? This is the expression. Now, so I0. Now, yes. What is the conduction time? Conduction time of diode. Conduction time of diode. Diode is in on state from. Diode is in on state from omega t 0 till omega t is equal to beta, na? So conduction angle is beta minus 0. That is a beta divided by omega. This is a conduction time of diode, right? Beta minus 0 by omega. That is a beta by omega. What is the PIV rating of diode? PIV rating of diode. Come on. What is the PIV rating of diode? We are having the waveform for the diode voltage, na? Yes. So what is PIV rating? This is a Vmax, na? Vmax, right? Next. So it is a Vmax. PIV rating of diode is Vmax. Is this clear? Right? Okay. Now one more thing. Whether there will be any relation between inductor value and a beta, extinction angle beta and inductor value, whether there will be any relation? Yes, can anyone? I am saying that, is there any relation or there will be any relation between inductor value and this beta? Yes, no? Who decides this beta? Who decides this beta? Inductor. How? Because we know beta is nothing but this is the extension angle and this is the instant till which inductor releases the energy. Okay, now you can check. Suppose if we are having a very high value of inductor here, suppose we are having the L value is very high. If L value is very high, during omega t is equal to 0 to theta, inductor will store more energy because inductor energy is equal to half into Li square, na? Right? So if L value is very high, therefore energy stored by the inductor is also very high. So during 0 to theta, if inductor stored energy is high, so after theta, right, whatever the time required for the inductor to release the energy is also equal to what? It is a high time requires. Okay, so that's why your beta will be more. Always keep it in mind. Okay, if value of inductor is more, your extension angle beta is also more. Okay, extension angle beta is also more. Is this clear? Right? So friends, this is about the single phase half wave uncontrolled rectifier with RL load. Okay, here we have discussed some sample cases for a single phase half wave uncontrolled rectifier. Tomorrow we are directly moving towards the single phase half wave controlled rectifier, because the difference between the controlled rectifier and uncontrolled rectifier is the only thing is we need to replace this diode with a thyristor, and in that case you will understand. For the thyristor, if we use alpha is 0 degree, na, we will be getting the same operations, same waveforms, whatever we are having in the case of diode. Is this clear? Right? Okay. So now the forum is open for you. If you are having any doubts, please ask.
Sir,
Sir? Yes,
Sir?
yes. Please, please. One by one.
sir, for omega t is equal to theta to pi, you said that Vs value is less than Vr, no sir.
Omega t is equal to
Theta to pi.
theta to pi. Yes. Huh.
Ps is less than Vr, no sir. How you are saying that Ps is less than Vr, sir?
Okay, okay, okay. Please keep it in mind here. Because 0 to theta, what is happening? Load inductor is increasing, na?
Yes, sir.
Okay. And whether is there any relation between VR and I0?
VR and I0.
Yes.
Yes, sir.
VR is equal to I0 into R, na?
Yes, sir.
So you can check the slope here. It is increasing like this. At the theta, I0 reaches the peak value. So definitely at theta, your VR will reach the peak value. After
Yes,
that,
sir.
yes, as your I0 decreases, your VR also decreases. But you can check the slope of Vs after theta and slope of VR after theta. At theta, what is happening actually? At omega t is equal to theta, what is happening? Your VL is 0, na?
Yes, sir.
At omega t is equal to theta, VL is 0. The meaning is Vs and VR both are same.
Yes, sir.
Yes or no? Right? So what is happening actually? At this instant, Vs and VR both are same. 0 to theta, VR is less than Vs. After theta, VR is greater than Vs. Are you getting the point? If Vs,
No, sir.
if VR is greater than Vs, then and only then we'll be getting the VL is negative, na?
Yes, sir.
Right? So that's why at theta, VL and sorry, at theta, VL is 0. So your VR and Vs both are same value, both are same. So that's why the difference is 0, na? Vs minus VR difference is 0. That is nothing but VL is 0. Right?
Okay, sir.
Keep it in
Sir,
mind.
under what,
VR
sir?
waveform and I0 waveform both will be in phase. Okay. Yes. Next.
Sir,
Sir, you
No,
have
no, the
taken the
same
limits.
questions. Yes. You please ask. Yes.
Sir, you have taken limits from 0 to beta, no, sir.
Yes.
The wave is completing up to 2 pi, no, sir.
Which waveform completing till 2 pi? Just a minute. Let me open it. Yeah.
Here the limits.
Wave, wave is only till beta, na?
It's 2 pi, no, sir.
Diode will be in the conduction mode only till beta.
Okay, we will take conduction mode, sir, there.
No. Conduction mode, that is the, you can see the equivalent circuit here, na? Yes. Diode is in on state, na? And from 0 to beta only you are having V0, same as that of the supply voltage, the same expression we have written. After beta, what is your V0? 0, na?
Yes, sir.
And till which instant the current I0 will be non-zero? Only till beta. Right?
Okay. Yes,
Because
sir.
after beta, what is happening? Diode is in open circuit mode. So that's why your I0 will be 0. I00 means whatever the expression of this I0 is valid only till beta, na?
Yes, sir.
Right? Okay. Yes.
Sir, my question is not that, sir.
Yes.
In
Yes.
V naught average, we have taken the integration limits from 0 to beta, no, sir. That one I asked, sir.
Okay. Just a minute. I will clarify that. Yes, here it is. Yeah. 0 to
no,
2 pi, 1 by 2 pi. Yes.
No, sir. V average, sir. V not average.
Yes, I will tell you now V0 average why I have taken 0 to beta integration limit. Okay.
Okay, sir.
So you can check waveform for V0 is 0 to 2 pi. Whatever the waveform 0 to 2 pi, same will repeat from 2 pi to 4 pi. So
Yes,
periodic
sir.
angle is 2 pi. It is okay.
Yes, sir.
Now between 0 to 2 pi, we are having two intervals now. One is 0 to beta and beta to 2 pi.
Yes, sir.
And in 0 to beta, what is the value of V0? Same as that of the supply voltage.
Yes, sir.
And from beta to 2 pi, what is the value of V0?
It's 0.
0. So what is the integration of that 0 during 0 beta to 2 pi? 0 only, na? So effective interval is only 0 to beta.
Okay, sir.
Right? So that's why we've taken only 0 to beta. Okay. Or if you want, you can write it as 1 by 2 pi integration from 0 to 2 pi V0 into d omega t. In the next step, you can write it as integration from 0 to beta. It is a Vm sin omega t plus integration from beta to 2 pi. It is a 0 into d omega t. But what is that integration beta to 2 pi integration of 0? That will be 0 only, na? So only
Okay,
effective term will be like 0 to beta only, right?
Okay, sir. So another doubt
Right.
from yesterday class, sir.
Yes.
In IGBT, if we are considering M plus buffer, no, sir.
Yes.
In that we have high forward voltage blocking and small reverse voltage blocking, no, sir.
Yes.
How we are getting that small reverse voltage blocking, sir?
Small reverse voltage blocking means, suppose if you are applying a less reverse voltage, then our IGBT can block. That is the meaning actually. Because you can check in IGBT, corresponding to that, I think that junction J1, right? And we
Yes,
are having
sir.
the layers like P plus and N plus. Okay. Both layers
sir.
are like a thin layers. Okay. And both are heavily doped. And that junction
sir.
was in a reverse bias mode. So that's why there was a not much scope for the depletion layer to grow, right? Now,
Yes,
who
sir.
decides how much voltage our device will block? Our switch will block or not? That depletion layer decides, na?
Yes, sir.
If the depletion layer is having a space available to grow, definitely our depletion layer will block high voltage.
Yes, sir.
Right, so you can check in that case, in that particular IGBT, if you check with the N plus, right there. So that
Yes,
P
sir.
plus N plus junction was in a reverse bias mode. So that whatever that, as that junction is in a reverse bias mode, so whatever the depletion layer will be present across that junction, okay, that depletion layer will be having a very less space available to grow. So that's why our that depletion layer will block, yes, very less voltage, we can see. Right?
Okay, sir.
And that less voltage will be anything. You can say it as a 10 volt, it may be 15 volt, depends on again the thickness of your P plus and N plus. Right? But generally for power applications, we consider that, because for power applications, we are having a high voltage, na? So
Yes,
that's
sir.
why we're considering that IGBT blocks only forward voltage. Okay.
Okay, sir.
Hello, sir.
Hello,
Sir,
Yes.
sir,
Please.
what
Sir, while inductor is releasing the current means, will the polarity changes, sir, while discharging?
Yes.
Sir, but
I have
in the
shown the
case,
same polarity, right?
no, sir, while charging it is plus minus means, while it is discharging with the polarity changes like in capacitor, sir.
Whether the polarities are changing in the capacitor?
No, sir, you said while discharging the polarity will, if the upper plate is plus means, while discharging the lower plate will be plus, like that I'm asking, sir.
Yes, that will be like that only. But while here discussing, na,
Yes, sir.
what I have considered the same polarity.
Yes,
But
that
what
only
is
I'm
the-
asking.
What is the value of that? It is a negative, na?
Okay,
So
sir.
with this polarity, if I am saying that negative VL means what, actual polarity will be reversed only.
Okay, sir. Sir, with the inductor, with purely inductive load, can you please go to the page, sir?
Yes, please. Just a minute. Purely inductive.
Oh.
Just purely inductive. Yes, here it is.
The interval between pi to 2 pi, it is releasing here, it is de-energizing, sir. At the time, why we are not changing the polarity, sir? That's one.
Where?
Here only, sir. From the interval pi to 2 pi.
After pi, why we are not changing the polarity, you are saying?
Sir, generally in inductor, if it start discharging means the upper plus will become in the lower side, like that in capacitor. But here we didn't change like that. It's as original polarity itself. Why it's like that? I'm asking.
Yes. Please listen it. Actually, the thing is, it is happening like this, whatever you are saying. Because you can check what is voltage across inductor here. V0.
V0, VL.
Voltage across inductor V0, na?
Yes, sir.
Now inductor we have connected in a load branch. So voltage across inductor is a V0 only.
Okay, sir.
Now you can check the V0 waveform. From 0 to pi, we are having V0 positive means voltage across inductor is positive.
Okay, sir.
That is like your inductor is storing the energy. And from pi to beta, V0 is negative, na?
Okay, sir.
So what that V0 negative indicates, it is like your polarity will be reversed only, na?
No, sir, I'm not asking that, sir. While discharging, the below side of the bottom side of the inductor should come plus, no, sir, but he didn't mention it, right?
Yeah. I am not mentioning, but the actual thing is you can say, just a minute. Let me tell you. Yes, let me, yeah. Suppose I'm writing this as a 5 volt, okay?
Okay, sir.
If I write by keeping this as a minus 5 volt, okay? Whether it will be same as that of reversing the polarity and writing 5 volt. These two are same or different?
Same, sir.
This one and this one both are same, na?
Yes, sir.
Same thing is here in our inductor also. Yes, you can
Okay.
see. Right? I am not reversing the polarity, because the thing is, if you reverse the polarity, na, in power electronics, you are having a sinusoidal supply. So
Okay,
it will
sir.
create a more confusion.
Okay,
Right?
okay, sir.
So the thing is, you can check here. Here V0 positive means what? Here it is plus, here it is minus. I am considering the same polarity only. So
Okay.
if V0 positive means here it is plus, here it is minus only. But with this polarity, if V0 is negative, na, then
Yes, sir.
meaning is actually polarity will be reversed.
Okay, okay, sir.
Right?
Sir, and another doubt in 33F, sir.
In
33F, 33.
33F. Yes.
Sir, that voltage across diode diagram.
Voltage across diode diagram. Okay. Yes.
Sir, here after 2 pi at one point, the diode voltage becomes 0, sir, which indicates the diode is in on state or off state, sir, because you told the diode will be permanently in off state, but it here reaches 0, then it means it will be in on state, no, sir, voltage 0.
No, it is in an off state only, but you can check, this is reaching the 0 volt for how much time? Very short time, na?
Okay, okay,
And
sir.
it is reaching to 0 and again it is increasing in the negative value.
Yes, sir.
So whether the diode is having the time to turn on?
No, sir.
It is
Not
continuously in the off state only, right?
Sir, and last one doubt, sir. That I not RMS lastly is discussed, no, sir, for RL load. I not RMS.
Yes. REL, na?
I not RMS. I not RMS. Right?
Just a minute.
RL.
We wrote that, na?
Yes, sir.
Why it is not showing here? Yes, here it is now. Just a minute. I not RMS you want, right?
Yes, sir.
Yes.
Sir, previous slide.
Not RMS, this is I0 actually. Huh?
Previous slide, sir.
Yes.
Sir, here you told V not equal to Vs, sir, from 0 to beta. But in one interval like pi to beta, V naught becomes minus Vs, sir. Then how can we take it as only plus values, sir?
Okay. You can check here. Pi to beta, supply voltage is positive or negative?
Again.
Slow,
So pi to beta supply voltage is negative, sir.
Negative.
and out clear.
What is the V0 waveform from pi to beta?
Eight out for the jaldi.
V0 waveform from negative. Sir.
So both
Plus
are same or
out
different?
Oh, minus into minus positive like that.
No, minus positive is not like that. Please don't get confused. Here, From 0 to pi, actually we are considering Vs is positive, means polarity will be upper
ଲମ୍ବା
terminal
ଲାଇନ
positive,
ଲାଗିକି
lower will be negative.
କେତେ ଫୁଟ
Yes, sir.
And after pi, we are reversing the polarity of the supply voltage.
ନା
Now,
ମୋର ଲାଇନ
Yes, sir.
so after reversing the polarity of the supply voltage, if I am getting V0 is equal to minus Vs, the meaning is V0 is actually negative.
Okay, sir.
So that's why it is a same method of the supply voltage only. It is not like that minus of that minus supply voltage means it will be positive. No, it is not like that. If I from 0 till 2 pi, if I keep the voltage and polarity will be like plus here minus here, na? And if I am getting it as a V0 is equal to Vs, okay?
Sir,
And if I am getting that is negative.
Sir, that point I didn't understand, sir, because pi to beta, it is V out is equal to minus Vs, but you told 0 to beta, V out is plus Vs here. That one.
No, you can check now from you can check the waveform. Do you have any doubt in the V0 waveform first?
No, sir.
If you don't have any doubt in a V0 waveform, so you can check from pi to beta supply voltage waveform and V0 waveform, both are same or different?
Yeah, yes, sir, same, sir.
Both are same, so directly I can write now Vs is equal to V0.
Okay, sir. What I'm asking is we no need to mention the minus, sir, because it is in negative like that.
Yes, we did not to maintain the minus because the thing is here pi to beta supply voltage is also negative and V0 is also negative, means both are same only, na?
Okay, sir.
We did not to mention here, right?
Yes, sir.
Okay.
Thank you, sir.
Sir.
Yeah.
Hello, sir. Hello, sir.
Yes, please.
Good evening, sir.
Good evening.
In average output voltage in RL load.
RL load average output voltage, na?
Yes, sir.
RL load. Do you know the slide number? RL load average output voltage. Yes, here it is.
Sir, here it is 0 to pi. Output voltage is positive now, sir.
Huh.
And pi to beta output voltage is negative now, sir.
Huh.
At that time, answer will be different now, sir.
No. Why the answer will be different? You can check the V0 waveform and Vs waveform. You guys are thinking in the way like positive and negative. That's why it is a confusing. Yes. Okay. Huh. You can check here. Yes.
Yes, sir.
0 to pi Vs is positive.
Yes, sir.
V0 is positive. Means
Yes,
both
sir.
are same or different?
Same, sir.
Pi to beta, say supply voltage is negative.
Yes, sir.
V0 is also negative.
Yes, sir.
Both are same or different?
Both are same now, sir. But output voltage is representing positive terminal is above and negative terminal is below now, sir.
Okay. If you
Why we are interchange the supply voltage interchange చేస్తున్నాం change output voltage not change na, sir.
supply voltage interchanges, but
Output voltage is considering same sign na, sir. Plus is upper terminal and minus is below terminal.
okay.
At that time output voltage is negative na, sir. Not same that
Okay. Yes. The thing is, if you are considering this as a negative, na, right? And if you are saying that V0 average is 1/2 pi, integration from 0 to pi. Okay.
1/2 pi.
Vm, yes.
Sir.
Please tell me what is in your mind. Yes.
Yes, sir.
If you want to find the V0 average, how you will
Sir.
find? Please tell me your
1/2 pi.
expression so that I will correct it. That will be good.
1/2 pi.
Yes. Just a minute. Let me write here. 1/2 pi.
0 to pi.
Integration from 0 to pi.
Vm sin omega t d omega t.
Vm into sine of omega t into d omega t. Okay, this is the thing, right? Plus
Pi to beta minus Vm sin omega t d omega.
If you write in this way, na, this
Yes,
will be wrong. Why? Because let me tell you. You are putting limit for sinusoidal here pi to beta. Okay.
Yes, sir.
And you are saying that your output voltage is negative of that value. You can check sinusoidal varying like this.
Okay, I can understand, sir.
Are you getting the point?
Yes, sir. Yes, sir.
So from
Again,
pi to
what?
beta means this is a beta, this is a pi. Okay. So this
Positive
indicates
beta.
your pi to beta like this. Okay.
Yes, sir. Yes.
So minus of this will be like you are saying that your V0 will be like this. One is
Positive.
0 to pi, and after that you are saying that it will be like this. Whether it is the true?
No, no, sir.
No. So that's why we cannot write in this way, right?
Okay, okay. Thank you, sir.
Yes, yes. Okay.
Sir,
Yes, please.
sir, regarding the RL load diagram, the waveform.
Waveform, na?
Sir.
Just a minute. Yes.
Similar to how you said beta depends on the inductor, will theta also depend on the inductor?
Theta, definitely. Theta also will depend on inductor.
Can we
Definitely.
say theta is the midpoint between 0 and beta?
Theta is the midpoint between 0 and beta. Yes, yes. No, we cannot exactly say that. Okay.
For this ideal case only.
No, we cannot say that like that, because you can see this theta is very close to your pi.
Okay, sir.
Okay, and actually this beta is also not. This is also very close to your pi. This angle
Yes.
will be definitely somewhat lesser. Okay, than that of this one.
Okay.
But yes, yes. That
Like-
whatever first you asked, na, whether that theta and L is having some relation. Definitely, good question.
Sir.
Right. Okay.
My last doubt is,
Yes.
is there any chance that theta can coincide with pi and go into second quad, that negative half cycle,
Theta can coincide with pi.
and go into negative half cycle?
No,
Can there be a
theta-
possibility?
Theta will be always less than pi only.
Okay, sir.
Because the thing is, what is happening? This slope, na,
Sir.
and your VS slope, both are not same.
Okay.
So that's why somewhere at this point, na, yes, VL will be 0. VL will be 0 before pi.
Okay.
Right?
Okay, sir. Got it.
Yes. Yes.
Good
Hello,
evening, sir.
Sir,
Good evening.
sir, once
Sir,
that
and L load, sir.
Okay. L load, pure
And-
inductive.
Hi, yes, sir. L load.
Just a minute. Yes.
Sir, in this case, when the inductor is discharged means upper is negative
Will you
plus.
please speak a bit louder?
Hi, yes, sir. Now it's okay,
Yes.
sir.
Yes, it is okay.
सर नॉर्मली इंडक्टर अगर डिस्चार्ज होने के मतलब ऊपर की प्लेट पे नेगेटिव और नीचे पॉजिटिव होता है ना सर।
Okay, okay. हाँ.
हाँ, कैन आई स्पीक हिंदी या सर?
यहाँ क्या?
हेलो।
Yes.
हाँ, इंडक्टर जो भी है ना डिस्चार्ज होने के लिए वो अपर प्लेट इज नेगेटिव, डाउन प्लेट इज पॉजिटिव नॉर्मली।
बराबर, correct.
हाँ, in this case we are taking, you said the example of the plus 5 minus 5 in the of the terminals as you said, no sir, when I ask this question.
Yes, yes.
Sir,
The thing is, you can, if you want to solve like that, you can solve in that way also. Okay, you will be getting the same answer, same waveform, right?
but
Here is
sir,
what I am considering. I am not changing the polarity of the VL. Okay.
okay.
I am keeping the same polarity, but with the same polarity, if I am getting the negative value na across the voltage across inductor, negative value, then the meaning is
Yes.
like polarity is reversed only na.
Yes sir.
In your case, if you reverse the polarity, then VL will be always positive only in your case.
Yes.
And
Sir,
in my case, what is happening? This negative V0 means what? It is like a reverse polarity only.
means negative terminal is treated as a positive.
Yeah. Negative terminal. If you keep the polarity like this, plus here and minus here, okay. If the voltage is positive, means this is higher, this is lower, right?
Yes sir.
If I am keeping this polarity as it is, and if voltage is negative, na, the meaning
Yes, sir.
is if this polarity is here, plus here, minus here, and if voltage is negative, na, then the meaning is this is a higher and this is a lower. But instead of denoting in that way, I am keeping the polarity as it is, but I am representing it in waveform in form of negative values, na.
Yeah, I understand. You're treating as a negative as a positive. That's why you're
Yes,
taking
yes,
as a
yes.
minus PS.
Yes.
Okay, so it's
Right?
huge
Because if
confusion
you
in that.
check,
That's
if you reverse the polarity na, then in that
Yes,
case,
sir, yes,
what
sir.
will happen? If you
V
are
naught
saying
equal to
that the
VS.
polarity will be reversed, then whether you will be representing this as a negative? No, na?
No, positive.
Positive only means that will create a more confusion in power difference actually. So that's why generally don't change the polarity. Definitely in network class you might have studied that the polarity should be reversed, and that is true. When inductor releases the energy, polarity should be reversed. But in our case, what we are doing, instead of reversing the polarity, I am writing this voltage, that voltage as a negative only. Na? So same polarity and negative voltage, the meaning is the polarity is reversed only, right?
Yes, sir. Yes, sir.
Okay, okay.
Hello,
Sir,
good
one
evening,
more,
sir.
sir.
Yes, sir.
Ah, yes, please.
Sir, can
Sir, in
you
last
open
case-
that C load, sir?
Will you?
Hello.
C load, sir,
Ah,
C
yes,
load.
please. Pure capacity.
Yes, sir, pure capacity load.
Just a minute.
Waveform, sir.
Yeah. Yes. Yes,
Sir,
here it is waveform.
For omega t equals to pi by t to pi, sir.
Pi by 2 to pi. Okay.
Yes, sir. The capacitor voltage opposite to the diode, discharging to diode, then it will open circuit, no, sir? Open.
When capacitor voltage,
Capacitor voltage, capacitor is discharging through diode, then it will reverse bias, no, sir?
yes, na. Capacitor will try to discharge in this way, but diode will fill the reverse voltage, na.
Sir, up to which time, sir, that is going on discharging?
That will be full. You can check here. 0
sir.
to pi by 2, it is like our capacitor has charged to the peak value.
Yes, sir.
After pi by 2, what is happening? Supply voltage is less than that of this maximum value of the capacitor voltage. So
Yes,
this
sir.
voltage is lesser, this voltage will be more. Yes or no?
Yes, sir, yes, sir.
So diode will be in the off state. Whether capacitor will discharge, not possible. So capacitor voltage will remain same, that is the VM only, right?
Yes.
Next, you can check after pi what is happening. Supply voltage is negative, na? Supply voltage negative means here minus, here it is plus. So if it is minus here, if it is plus here, so it is like this is negative and this is VM, means these two will be getting added, na?
Yes, sir.
So diode voltage will be more negative. So diode will be reverse bias mode only. So from pi to 2 pi, we don't have any, means there is no chance of diode will be in a conduction mode. So therefore diode will be in off state only. So if diode is in off state, capacitor will not discharge at all. This will continue till 2 pi. After 2 pi, what will happen? Again, you can check after 2 pi, what will happen? After 2 pi, supply voltage is again positive. So it is plus here and minus here. Yes or no?
Yes, sir.
Now you can check here. After 2 pi till this instant, means till peak value. From this point to this point, supply voltage is less than that of capacitor voltage. Na? So that's why again, here it is VM and here it is VS. So this voltage is lesser, this voltage will be more, diode is in an off state only. So whether capacitor will discharge, not possible. Again, after this point, again, this supply voltage is the reverse, na? Negative, sorry, decreasing. Supply voltage decreasing means what? This is peak value and this is what? Lesser again. So that's why again, diode will not turn on. So capacitor will not discharge at all. Yes or no?
Okay, sir. Up to which that the diode is only turn off.
Yeah, diode will be in the off state only after pi by 2.
Okay, sir. Can you explain that
Right.
once? The I naught, sir. Omega C VM.
Okay. Actually, the thing is, we know na, as capacitor go on charging, right?
Yes, sir.
So initially this capacitor voltage is 0 volt. Yes or no?
Yes, sir.
So if this voltage is 0 volt means this current will be flowing like this. So that's why current will be at a peak value. After that, as capacitor voltage increases, na?
Yes, sir.
As capacitor voltage increases, this difference decreases.
Yes, sir.
So you can check this current go on decreasing. At pi by 2, when capacitor voltage becomes equal to peak value. Okay. So this is also peak, this is also peak. Resultant voltage 0. So your current will be 0.
Okay, sir.
In the case of capacitor, always keep it in mind. At the instant of switching, capacitor current will be peak. After that, as capacitor go on charging, na capacitor current decreases,
Decreases.
right?
Okay, sir.
Yes, yes. Okay.
Extinction angle is the angle till which inductor releases energy or stores energy.
Beta means
The angle
you are
till which,
asking for beta.
yes sir, yes sir. Sir, inductor
Okay.
energy or stores energy.
Inductor.
Beta is the angle till which inductor releases energy or stores energy.
No, releases energy.
Okay, then sir, if inductance value increases, then beta value also increases. Means
Yes.
beta. Yes sir.
Hello.
Hello sir.
Will you please speak a bit louder?
Sir, if inductance value increases, then extinction angle value also increases.
Yes, yes, it increases.
Okay, and sir, what is theta?
What is theta?
Yes sir.
Theta is the angle till which inductor stores energy.
Okay, okay sir.
Right? Means from 0 to theta, inductor stores energy. After theta till beta, inductor releases energy.
Okay, and sir,
Right?
that, yes sir, and that last integration that we did, sir, that
Okay.
integrating factor 1.
Okay, IF means for RL load.
Sir, so sir, there that integration, sir, what is that limit for that integration?
Just a minute. Yes. This one you are saying?
Yes sir, in the next slide. Yes sir,
Here.
here. Yes, sir. The final
Okay.
solution before that, that integration, what is the limit for that integration?
Okay. Here, limit will be from 0 to theta we need to put. Right?
But sir, but here we are doing it for omega t equal to 0 to beta.
Yes, I have drawn this circuit for 0 to beta, but whatever the circuit will be there na for 0 to beta, same will be there for whatever the circuit will be there for 0 to theta, same will be there for theta to beta also.
Yes sir.
Diode will be in a conduction mode only. V0 will be same as that of the supply voltage only. Yes or
Yes.
no?
Yes sir.
Right? So same means we can simplify it till omega t is equal to 0 to theta. Okay. But again, you will be getting the same expression from theta to that pi also, right?
So sir, we will have to multiply it by 2 because 0 to beta plus 0 to theta plus theta to beta, we have to do like that, or only 0 to theta limit.
Okay. No. Here in this case, only till 0 to theta.
Okay, sir.
Yeah.
And last doubt.
If you want to find the beta value, na,
Yes, sir.
from this also we can find the beta value. How? You can check at omega t is equal to beta, I0 is 0, na?
Yes, sir.
So in this expression, simply replace omega t with beta, okay, and I0 with 0. You will be getting the value of your beta, okay?
Yes, sir. And sir, last,
Huh.
sir, in the starting we were discussing that SCR is current control or charge control. So, sir,
Okay.
in that if there is both the options, sir, as you mentioned, can you repeat that? If there are both the options, then which option we should select, charge or current?
Okay, if there are there will be both the options, mean charge and current, then we need to tick for the charge. Charge.
Okay, yes, sir. Okay, thank you, sir.
Right. Okay.
Hello, sir.
Yes, please.
When finding the root mean square value, in place of mean value, when can we substitute in the mean value, sir? Means average value.
Please repeat and please speak a bit louder.
Sir, when we finding the root mean square value, sir, for any value,
RMS
output
value?
voltage. Yes, yes, sir. RMS value. RMS M means mean value, na, sir.
RMS M means mean, means average.
Yes, sir. Yes, sir. That on that average value, can we substitute in the previously when we are finding the average value, that average
No,
value
no,
can
no,
we
no,
sub?
no, no, no,
No,
no,
sir.
no, no. You cannot put that value average here because
Okay.
you can check RMS means what? Square root
Okay.
of mean of squared value, na?
Yes, sir. Yes, sir.
We need to take the average of the squared value, and then we
Yes.
need to put it into square root. But
Yes.
previously in V0 average, whatever we discussed now, we have calculated.
Yes,
That
sir.
was the average of V0. But in the
Yes.
RMS, we require the average of V0 square.
Yes, sir. So that's
So
why
we
found
cannot
this
blindly
value.
use that expression here, right?
Yes, sir. So that's
Okay.
it.
Okay.
Thank you. Thank you, sir.
Yes, yes. Yes, next.
Audible, sir?
Yes, please speak a bit louder. Huh?
Hello, now audible, sir?
No, please speak a bit louder.
Okay, okay. Sir, I have doubt in yesterday's class, sir.
Doubt in?
Yesterday's class.
Yes, please ask.
Yeah. In BJT, sir, we have NPN transistor. Consider.
In BJT, we are having
high forward blocking, right, sir?
Please speak a bit louder.
Sir, in BJT, we have in power BJT, we have high forward blocking and low reverse blocking. We get this
No
high
reverse
forward-
blocking. Yes,
yeah.
yes.
We get this high forward blocking by using n minus layers, right, sir?
Yes.
I have doubt that, sir, in P at the junction, on the both sides of the junction, ions accumulate in the equal amount, right, sir? Positive ions in one side, negative ions in other side.
Okay.
In n side, I have a space for positive ions, but in P plus side, which is highly doped, I don't see there is a much space for negative ions, sir. How it
Okay.
is going to close? Yeah.
Okay. Means you are saying that the width of that P side layer is lesser. N
Yes,
minus we are having the scope for increasing that. Okay. The width. Okay.
Yes, sir.
But if you check the mobility of electrons and the holes, if you consider, right?
Right.
In which case it will be more?
Electrons, sir.
Electrons case that will be more. Okay. So even though your space is less here at the P plus side, na, right? And that your N minus layer, okay, N minus layer will be like acting as a what we can say, the depletion layer. No, sorry, that yes, depletion layer absorbing material. You can check in ESC 2021. They asked the one question in a power diode that lightly doped N minus layer will act as, okay, they have asked some question like this. Okay, so it is like a it acts as a absorbing. Okay, absorbing material means what? Due to that N minus, what is happening? Our first thing is a rate of grow of depletion layer is reducing due to that N minus layer. Okay, so even though you are having the less space at the P side now, you will be your device can successfully block the voltage.
Okay, sir.
Due to that N minus layer specifically. But
Yeah,
if you don't have that N minus layer also, okay, then it is very difficult to block the high voltage.
Right, sir. Means, sir, in both sides of the junction, ions will not accumulate equally.
In both sides of the junction?
Like at junction J1, we have P plus and N minus. In forward blocking means on P side, less charges will be accumulated, and on
Yes.
N minus side, less positive charges will be accumulated. Is
Yes,
that something
yes.
like that?
At N minus side, you will be having somewhat, width of the depletion layer at N minus side will be somewhat more compared to that of your P side. Huh?
Okay.
Actually, this is the real case. It really, in real life, this is happening in this way. Because N minus layer is having what the thing is, it is having a less number of charges and width is more, na?
Right.
So more number of charges can be, occupy their space in this layer compared to that of your P plus. And when any depletion layer breaks down, na, it depends on its capacity. So even though your P type layer is having a less capacity, na, right, less width, but your N minus layer is having a sufficient space. So that's why altogether it will increase the blocking, right?
Right. Okay, sir. Thank you. Understood.
Sir.
Yes.
Sir.
Yes, please. One by one.
Sir, slide number 37.
37.
Yes, sir.
Yes.
Once explain that graph, sir. I didn't understand.
Okay. Simply you do one thing. Okay. 0 to pi by 2, it is okay. Diode is in a conduction mode now, so that's why it will be 0 only.
Yes, sir.
After pi by 2, what is happening? Recall the circuit diagram. After pi by 2, we are having, yes, circuit diagram is like this. Yeah, this is na.
Yes, sir.
After pi by 2. So you can check pi by 2 to pi. This supply voltage is like plus here, minus here. Okay.
Yes, sir.
And here voltage is Vm.
Yes, sir.
So you can check what is Vd here. Vd is equal to this voltage minus this voltage na.
Yes, sir.
So this voltage is pi by 2 to pi. This voltage is less or greater than that of Vm. Lesser.
Okay, sir.
Right? Pi by 2 to pi, Vs is less than that of Vm. Check the waveform of the supply voltage. 0 to pi by 2, we are having the supply voltage increasing. At pi by 2, it reaches the peak value.
Yes, sir.
After pi by 2 till pi, it decreases na.
Yes, sir.
From pi by 2 to pi, Vs is positive, but it is less than that of the peak value. The meaning is this voltage minus this voltage will be equal to your Vd.
Yes, sir.
So from pi by 2 to pi, what is the Vs? Vs is decreasing. So this voltage is decreasing. So whatever the difference between these two, the difference will be increasing na.
Yes, sir.
So that's why here we are getting this increasing till pi. At omega t is equal to pi, what is happening? At pi, supply voltage is 0 na.
Yes, sir.
At pi, supply voltage is 0. Supply voltage 0 means this voltage is 0. So 0 minus this voltage means 0 minus Vm. Therefore, Vd will be minus Vm. So you can check at pi, it is a minus Vm.
Okay, sir.
Now after pi, what will happen? After pi, you can check supply voltage is reverse na. So that's why minus here and plus here.
Okay, sir.
So what is Vd now? This voltage, which is already negative, minus this Vm. Are you getting the point? Means supply voltage is negative. In that, Vm is getting added. So that's why resultant voltage across diode will be increasing only na. So that's why here it will be increasing.
Okay.
At 3 pi by 2, you can check at 3 pi by 2, this voltage is Vmax. Yes or no? This voltage is Vmax. This voltage is also Vmax. But this voltage plus this voltage will be your Vd na, because its polarity is reversed now.
Okay.
So that's why it will be reaching 2 times Vmax means here.
Okay.
Right? And after that, again, what will happen? After 3 pi by 2, right? After this instant, supply voltage is negative only. 3 pi by 2 till 2 pi, na? 3 pi by 2 till pi. Supply voltage is negative only, but it is decreasing, na?
Yes, sir.
So that's why this difference will again decrease. So it will be like this. This type of waveform will be getting. At 2 pi, supply voltage will be 0. So 0 minus Vm means again it is a minus Vm, na?
Yes, sir.
After 2 pi, again what will happen? After 2 pi, supply voltage is positive means plus here, and here it is a minus, right? Plus here, minus here. So this minus this, you can check the difference will be decreasing na?
Yes, sir.
Because after 2 pi, this Vs is increasing in positive values. So Vs increases and this is constant na Vm. So difference decreases. So that's why it is like this only. Okay.
Okay, sir. Sir, another doubt, sir.
Yes, yes.
Slide number 32, sir.
32.
Yes, sir.
Okay. Yes, 32. Huh.
Once explain that I naught average and P naught average expressions.
V naught average and P naught average.
Sir.
V naught average. V0 average, na? You can check the V0 waveform, from that you
Oh,
will
sir,
understand.
only P0 average, sir.
Okay, okay. P0 average. Okay.
Yes. Why it
P0
is-
average is the average value of output voltage. You can check here. V0 and I0 waveform, you will understand. If I take the product of these two, because P0 means what? V0 into I0, na?
Yes, sir.
So if I take the product of these two waveforms, what will happen during 0 to pi? This is positive, this is also positive. So product will be positive now.
Yes, sir.
And from pi to 2 pi, V0 is negative, I0 is positive now.
Yes, sir.
So what is the product of negative and positive? Negative. Right? So here we are getting 0 to pi, we are getting the positive values of P0. Pi to 2 pi, we are getting the negative values of V0. And you can check this slope and this slope, both are same or different for I0. Same slope.
Yes, sir.
So that's why your average will be 0, right?
Okay, sir.
Okay.
Sir, in slide number 48.
Slide number
48.
48. Okay.
Oh, sir. I not average, sir.
I0 average.
Next slide, sir. 14.
Okay.
Once explain that, sir.
Okay. V0 means what? In the load we are having resistor and inductor, na?
Yes, sir.
So here you can check V0 is equal to VR plus VL.
Yes, sir.
In that case, what is the average value of the inductor? It is a 0.
Why, sir?
The same thing, na? Inductor average voltage. The thing is, you can same thing I explained here. Yes, you can check here. During 0 to theta, inductor is storing the energy, na?
Yes, sir.
VL is positive.
Yes, sir.
We have written here 0 to theta, inductor stores energy. Yes, VL is positive.
Okay,
Yes,
sir. Average.
VL is positive. Okay. And from theta to beta, what is VL? Negative.
Yes, sir. Average.
So 0 to theta we are having positive and theta to beta we are having negative. So average will be 0 only.
Okay,
right?
sir. Got it. Sir, last out. In DC, why effective output is average, sir?
In DC, why?
Effective output is average.
Okay. In please always keep it in mind. In DC means we expect a flat DC, na?
Yes, sir.
So in a flat DC, because in AC, why the effective value is RMS?
Don't know.
So the thing is like we have defined the systems like for AC, RMS value is like effective value. By default, whatever the value specified na is your RMS value. But in DC, if you check, suppose we are having a flat DC na. So for that flat DC waveform, if you find the RMS value, if you find the average value, you will be getting both will be the same values.
Yes.
So that's why generally the statement is in DC, the effective value is average value. Okay.
Okay, sir.
Right?
Thank you.
So generally, if we say, suppose I am having a DC voltage source of 200 volt. So what is the meaning of that? We are having a flat DC voltage of 200 volt. So
Yes.
average value will be 200, right?
Yes, sir.
Okay.
Hello, sir.
Yes, please.
Sir, could you open the white paper?
Which one?
Anyone for rough paper, sir.
Okay. Rough. Blank you are saying.
Yes, sir. Sorry, blank.
Just a minute. Yes.
Could you draw for the pure inductor and capacitor side by side?
What you are saying?
Pure inductor and capacitor with the diode.
Diode here. And inductor, na?
Yes, sir.
And
another circuit with the capacitor, sir.
here AC supply.
Same, sir. Our what we teach in that same.
Okay. AC supply is here. Okay. Right. And here you want the
Same AC and
AC
capacitor.
supply. Here it is a diode, na?
Yes, sir.
And
Same
here it is a
capacitor.
capacitor. Okay. Yes.
Sir, in this first case, for the reverse direction of the diode, the capacitor charges for the plus V.
In this
inductor is charging for the plus V0.
Inductor is charging for
plus Vs for the positive cycle.
V0 here.
V0 equal to Vs first the positive cycle.
Okay. 0 to pi you are saying.
0 to pi is charges to the Vs.
Barabar.
For the negative cycle, what will happen, sir?
In the negative cycle, actually the thing is here it is minus, here it is plus, na?
Yes, sir.
And if you recall the I0 waveform for this case, it is like this. Okay, this is like pi and this is 0, na?
Yes, sir.
So what is happening in the inductor case? This is I0. 0 to pi inductor current increases. At pi,
Yes, sir.
inductor current is at is a positive value, na? So
At the
positive
peak
value
value.
is what? At pi, current is in a downward direction,
Yes, sir.
right? And after pi, what is happening? Supply voltage is trying to circulate current in the opposite direction.
Yes, sir.
But whether our inductor will allow the sudden reversal current. Sudden reversal means after this current should, yes, suddenly fall to the negative value. But whether this sudden
No.
change inductor will allow? No, no.
No, sir.
So that's why what the inductor is doing, whatever the energy stored by the inductor from 0 to pi, inductor will release that energy in opposition to that of the supply voltage till 2 pi, right?
Okay. Yes,
So
sir.
this is
I
the
understand.
thing in
Sir,
the case of means in the inductor case, always keep it in mind. When inductor stores energy and when inductor releases the energy, na, in both
sir.
the cases, the direction of current flowing through the inductor should be same,
Okay.
right? But in the case of capacitor, it is not like that. In the case of
Yes,
capacitor,
sir.
you can check. During 0 to pi by 2, your capacitor will be getting charged. Okay.
Yes, sir.
At omega t is equal to pi by 2, it is like a capacitor will be charged to the voltage. Vc is equal to Vm. Na?
Yes, sir.
Now, in this case, what will happen? After pi by 2, you can check. After pi by 2, supply voltage is like this. Na? Supply voltage you are having here, it is like this and again negative. Okay. So till pi
Yes,
by
sir.
2, it is like pi by 2 here. After pi by 2, what is happening? Supply voltage is decreasing. Na?
Yes, sir.
So if supply voltage decrease means what? This capacitor, whether this capacitor will allow the decrease in the voltage? No. But suppose even the suppose capacitor, if suppose capacitor is discharging, capacitor can allow even, but the discharging path is not available here. How
Yes,
the
sir.
capacitor discharges? In the case of capacitor, here you can check. If capacitor is charging here, na, suppose this is IC and capacitor charges like this, then how the
Yes, sir.
capacitor discharges? While discharging the capacitor, voltage should be same, that is polarity plus here minus here only, and current is in a opposite direction.
Yes, sir.
Are you getting the point? So suppose
Huh.
when if this capacitor want to discharge, then this capacitor will try to circulate current in the opposite direction, na?
Yes, sir.
But whether this diode will allow the opposite current? No.
No.
Right?
That's why it's off.
That's why capacitor is not discharging, right?
Okay, sir. Sir, in last one, RL load.
Okay.
Sir, could you explain why we're taking the VR as the more than the pi value in the graph?
Just a minute. Yes. In the graph. Yes.
Why you take the VR up to the beta, why not up to pi, sir? At that time, my network is cut off.
I have taken VR up to beta.
Yes, sir.
That is the question, na?
Yes, sir.
Because you can check here we are having the load REL load. And what is the
Yes, sir.
current that is flowing through the load branch? I0.
Yes.
So voltage across resistor means what? I0 into R.
Yes, sir.
So R is a constant, na?
Yes, sir.
So your VR depends on I0 nature.
Yes, sir.
If I0 is like this, okay, then definitely your VR also will be till beta only. After beta, I0 is 0, na?
Yes, sir.
So what about the if I0 is 0, then VR will be 0 only, right?
Yes, sir.
Okay. So
Sir,
that's the VR will be till beta only.
Sir, without first we find the VR, after that we go to the I naught, no, sir.
No, actually the thing is, this is explanation actually we are doing. Okay. But actually the thing is, current is flowing like this. Okay.
Okay.
And depending on this current, actually we are having VR.
Okay.
Right? And current nature will be like this only because of the presence of inductor, na?
Yes, sir.
If inductor will not be there, then how will be the nature of I0? It will be like in phase with the V0, na?
Sure.
You can
Same as
check
the
the
previous
slope
cases.
of V0. You can check the slope of V0 and you can check the slope of I0. You will get the difference, right? Here you
Okay.
slowly increase. Here you can check comparatively here the fast increase, na? In a V0.
Yes, sir.
Right? Here it is a slowly increasing. Okay?
Okay, sir. I got it. Thank you so much, sir.
Yes, yes.
Sir,
Hi, yes, please.
my voice is audible, sir.
Hi, yes. You are
Sir,
audible.
during pi to beta.
In this circuit?
Yes, sir.
Okay. During pi to beta?
The potential between the anode and cathode, how it will be like, look like, sir.
During pi to beta, the potential?
Between anode and cathode of the diode.
Okay,
Will you explain, sir, how it will be allowing during negative voltage supply?
Okay. Huh. The thing is, yes, from pi to beta supply voltage positive or negative? Negative, na?
Yes, sir.
Here it is minus, here it is plus,
Okay.
right?
Okay, sir.
This supply voltage will try to circulate current in this direction,
Yes, sir.
but you can check till pi or at omega t is equal to pi. What was the current flowing through the load? It is a positive current, na?
Yes, sir.
So if this is positive current, means current is like in a downward direction only in this branch.
Okay, sir.
So at pi, if current here is non-zero and current direction is in downward direction, so can we say that current flowing through the inductor is in downward direction at pi?
Yes, sir.
After pi, whether our inductor will sorry. Yes. After pi, whether our inductor will
Yes, sir.
allow the sudden reversal of the current.
No, sir.
Sudden reversal means if current is anti-clockwise, na, means in this branch the current should flow in the upward direction.
Yes, sir.
So upward means from this positive value to the current should reach to the negative value directly in a short time, zero time. So inductor will not allow. So for that, what the inductor is doing, whatever the energy stored by the inductor, na, from like that, whatever the inductor energy was there, right? The inductor will continue go on releasing that energy even after pi also.
Yes, sir.
And you can check near to the pi, the value of the supply voltage is very small, na?
Sir.
So supply voltage value is small means what? Your supply voltage energy is small.
Yes, sir.
So supply energy is lesser than that of your inductor energy.
Yes, sir.
So that's why what is happening, your inductor energy is greater, so resultant current will flow into this case or into the clockwise direction only. Or in other way, you can say inductor voltage is greater than that of the supply voltage.
Okay, sir.
Because if inductor voltage is greater than that of supply voltage, then and only then the diode will be in the conduction mode, na?
Okay, sir.
Right? Same is happening. And till beta only it is happening, because till beta only inductor energy, inductor is having energy to release. After beta, you can check. The thing is, after pi, as the time increases, supply voltage value is also increasing, na?
Yes, sir.
So supply voltage value increasing means supply voltage energy increases.
Okay.
So that's why inductor energy, opposition to the inductor energy is increasing. So that's why current is decreasing. And after beta, it is like a supply energy becomes greater than the inductor energy, and our resultant current, circuit current will become zero, right?
Yes, sir.
Okay.
But after zero negative, after below the zero, anode will blocks the negative voltage, sir.
After below zero means
Going to the negative half cycle. Now voltage source is going to the negative half
supply
cycle.
voltage going negative.
Anode will block the current flow in the circuit now, sir.
Please repeat.
After zero crossing point at the voltage. But diode
Supply
anode
voltage zero crossing.
Yes, sir. The diode anode terminal will block the flow of the current in the circuit now, sir.
No. Please, that is what I am saying. The thing is, due to this inductor voltage, na,
Yes, sir.
our diode will be in a forward bias mode only after pi. In a pure resistive load, what happened? In purely resistive load, it is like a resistance is like a passive element. Okay. So it will not store energy at all. But what the inductor is doing, inductor is storing the energy, and after theta, the inductor is releasing the energy.
Okay, sir.
So if inductor is releasing the energy, means in the circuit, what is happening? From pi to beta, it is like a inductor voltage is greater than the supply voltage.
Yes, sir.
You can check from pi to beta, inductor voltage is positive or negative. We have written from pi to beta, inductor voltage is positive or negative. From pi to beta, you can check inductor voltage is negative, na?
Negative.
If inductor voltage is negative, means it is like the, yes, you can check here. Inductor voltage with this polarity, if inductor voltage is negative, means it is like a polarity will be plus here and minus here, na?
Yes, sir.
So it is like inductor voltage is greater than that of this voltage. Now, inductor voltage and supply voltage both are opposing, na?
Yes, sir.
right? Both are opposing. And if inductor voltage is greater, what about the VD? VD will be positive only.
Okay.
So even though after omega t is equal to pi, your supply voltage is negative, but diode is in a forward bias mode only. This is due to the inductor.
So cathode negative voltage will be very less than the anode negative voltage, sir.
No. Here, that it is not like that the anode is having a negative voltage. No, you can check. For example, suppose. Let me show you one
Sir, it should
example.
maintain difference, na sir. Anode cathode voltage difference, na sir.
No, you can apply KVL to this loop first. What is the KVL equation here? It is a minus Vs, right?
Sir.
Minus Vd, minus Vr, okay? And minus VL is equal to 0. So therefore Vd is equal to what? It is a Vs, okay?
Okay, sir.
Minus Vr minus VL, okay?
Okay, sir.
Yes or no?
Yes, sir.
Now you can check if VL value, okay? If your VL value is already negative, na?
Okay, sir.
So negative means this minus will become plus.
Okay, sir.
So you can check this voltage minus this voltage, and this Vs is actually negative, right? So we have reversed the polarity. So actually this should be negative. So if your VL will be greater than this of this minus Vs minus Vr, then definitely your Vd will be positive, na?
Yes, sir.
Don't think that here it is negative means here it is negative. It is not like that. Are you getting the point?
Okay, sir.
Already, actually the thing is voltage across diode is positive only.
Okay.
And voltage across diode means what? Anode voltage minus cathode voltage.
Sir, I am asking like that, sir.
If anode voltage minus cathode voltage is positive, then it is like our diode will be in a forward bias mode.
Okay, sir. For example, anode at terminal anode minus 5 volts, cathode would be minus 10 volts like that, sir.
Yes, like this. If you are considering that negative, then that will be more negative. Cathode,
Okay,
like that. Okay.
Okay, sir. So pure inductor circuit, sir.
Pure inductor
circuit.
Pure inductor circuit.
Yes, sir. Once please open once.
Just a minute. Yes.
Waveform, sir. Waveform.
Just a minute.
Sir, in this waveform, VD waveform is drawn, sir.
In this waveform,
voltage across the diode waveform.
Voltage across diode waveform.
Yes, sir.
Yes. We have one to draw.
Before those waveforms, sir, I can understand. Here,
For this,
anywhere, sir. Please draw the voltage across the diode VD waveform, sir. Can you draw?
VD waveform will be 0 here.
Why, sir?
Because diode is in a conduction mode only.
Okay.
Diode is in a conduction mode now. If diode is in a conduction mode, that's why the current is non-zero, na?
Yes, sir.
So VD will be 0 only here, right?
So complete continuous always.
Continuous zero. VD means, right?
Okay, sir. And in SCR, N, what is the difference between N plus layer and N minus layer, sir?
What is difference between N plus and N minus?
Sir, layers.
N plus means what? We are having electrons only in that layer, but the number of electrons, na, or the density of electrons is very high.
Okay, sir.
And N minus means what? It is like a lightly doped layer. Lightly doped means what? Number of electrons per unit volume, okay, will be very less.
Okay, sir.
Means in one case we are having a very high number of electrons. In second case we are having a very less number of electrons. Okay.
But
and that N minus N plus, it is like it will be decided by your density. Density means number of charges per unit volume.
Okay. Plus denotes highly doping, minus denotes lightly doping, sir.
What?
Here plus denotes highly doping, minus denotes lightly doping, meaning, sir.
N plus means
highly doped N-type layer.
Yes.
N minus means lightly doped N minus layer.
N minus is the lightly doped N minus. You in the power diode one that constructional diagram I shown na. You can check that. In that we have represented that in a N plus or P plus, we are having a density like a 10 to the power 19.
Yes, sir. Colorful.
And whereas in the n minus that case, we shown it as a 10 to the power 12 or 10 to the power 13.
And the last doubt, sir.
Huh.
Why are in MOSFET only high conductor losses more than IGBT and BJT, sir?
Okay, because the thing is in the MOSFET, you can check in yesterday we discussed in the MOSFET, the charges are flowing through the n minus layer maximum.
Okay, sir.
Most of the path now we are having from just like a source towards the drain. Okay.
Yes, sir.
The charges, negative charges are moving from source towards the drain through the n minus layer only.
Okay, sir.
And that n minus layer is having a like a lightly doped n minus we are having.
Yes,
so lightly doped layer is like means what its resistivity will be more.
Okay, sir.
Resistivity is more means what it is like our diode is acting as a resistor, on state resistor. So
Okay.
that's why the power loss will be more.
Power loss will but high switching frequency is possible. How it will be possible?
High switching frequency is possible because in the case of MOSFET, we don't have that conductivity modulation phenomena. Na?
Okay, sir.
Whereas if you check in the other devices where having conductivity modulation. Conductivity modulation means from heavily doped layers, okay, those heavily doped layers are injecting the charges into that n minus layer na, in other devices.
Okay.
But whereas this is not happening in a MOSFET, okay.
Okay.
So that's why what is happening in other devices due to the conductivity modulation, those devices in those devices that n minus layer is storing charges.
Okay, sir.
And due to that, to remove those charges, it takes time na. So
Yes.
that's why we keep it in a reverse bias and that thing, right?
Yes.
We discussed that dynamic characteristic during turn off, okay?
Okay, sir.
Right.
In this inductor, the negative voltage appears suddenly, na, sir.
In
this,
inductor?
in this diagram, voltage across the inductor appears negative suddenly raised, sir.
In this inductor, okay, voltage across inductor means V0, huh?
Sir.
Huh.
It will raises to the negative voltage suddenly.
Yeah, it can, because inductor is the element which opposes the change in the current.
Okay, sir.
Inductor will not oppose the change in the voltage.
Okay.
Right?
Okay, sir. From pi to beta, it will gradually decrease the total negative voltage.
Yes.
And by the discharging the current.
Yes. Okay.
Thank you very much.
Yes,
Hello.
please.
Hello, sir.
Akshay.
Sir, I had a doubt from last class. In IGBT with the N plus buffer layer absent, we had when we apply a reverse voltage across it, we had two junctions which were reverse biased.
Okay.
One junction had the N minus layer as part of the junction, so it had scope to grow. But the other junction doesn't have that much scope to grow, right, sir? So if we apply a large reverse voltage, then the one junction would be all right, but the other junction, will it be able to sustain that?
In IGBT, you are saying
with the N plus
IGBT, na?
Yes, sir.
IGBT, I don't think I am having that one here. Okay. Just a minute. Huh?
Okay, sir.
Let me open that. Yes. In IGBT, you are saying 26.8. Yes, here it is. Right?
Yes, sir. In IGBT section.
IGBT you want.
Yes, sir.
Yeah. In this.
Yes, sir. Here, if we remove the n plus buffer layer.
Okay.
And apply a reverse voltage.
Okay. Reverse
then
means it is your emitter
bottom
positive,
positive.
collector negative.
Yeah, emitter. Yes, sir. So then J1 junction would be reverse biased.
J1 would be the J1 will not be there. This J1 will not be here. Okay. N minus is not there, you are saying?
N plus is not there, so N minus will be there.
Yes. J1
So,
will be
reverse biased.
Okay.
And J3 also will be reverse biased.
J3 also will be reverse biased, right?
Okay, so J1 junction has the N minus layer, so the depletion layer has the scope to grow. So there is no problem there.
Yes.
But J3 junction, the P plus and N plus layer are only normal known. The width is actually not that high comparable to the N minus layer.
Okay.
So like, will it be able to sustain a large depletion?
No. The thing is that your J3 layer, okay, means P plus N plus, it is having a less space available.
Yes.
So that will be directly becoming short circuit before your J1. Are you getting the point?
Sir, like,
hello.
No, sir, I didn't get how it.
Thing is your J1 will block most of the voltage.
Okay.
J3, it is not required to block the voltage by the J3 even. You can check because J1 is having a high capacity to block the voltage, na?
Okay, so it is like a combined effect of both.
Yeah, combined effect you can see, right?
Okay, sir, got it. Sir, then one more thing, in power MOSFET, we had a green shaded area, right, between the source and the gate.
In power MOSFET,
this green shaded area, is it air or some other medium?
No, green shaded area only here to represent there is a no connection between your source terminal and a gate terminal.
Okay,
right,
sir.
to represent that. This is not like a SiO2 layer and those things, okay?
Okay, sir.
Okay, yes.
Got it, sir. Clear. Thank you, sir.
Yeah. Yes, next.
Hello, sir. Sir, we have N plus and N minus layer side by side, right, sir?
Where, in which device?
In any device, sir, means.
Okay.
N plus N minus layer side by side. N is highly doped, N minus is lightly doped.
Okay.
And there is no junction between them.
Please speak a bit louder.
Sir, there is no junction between N plus and N minus, right, sir?
Yes.
Then why electrons doesn't distribute between them? Because there is no junction. One is highly doped, having more electrons. Another is having less electrons.
The thing is, unless and until you maintain a electric field, right?
Yes,
our charges will not move. Are you getting the point?
Right.
If we maintain the electric field means you can maintain either in form of your voltage, okay? Your voltage source is like your electric field only, na?
Right.
So if we give the force to them, then and only then they will move. Otherwise, they will not move, right?
And if we, sir, just directly short N plus and N minus layer, remove it from circuit and directly short them side by side, then it is a closed path, right, sir? And then electron should distribute, na, sir?
Please repeat. If N plus and N minus were removed from the circuit
and shorted them,
and I have connected here.
Yeah.
Next.
Connected from one side to another side means both outer terminals I have connected and inner terminals are already at connected point. Then it's a closed loop side, right?
So whether you are applying the voltage here or not?
No voltage, sir.
Means only you are saying N plus and N minus. I am clubbing together just like.
Yeah.
Okay. Then what will happen? You are asking.
then I am thinking that n plus layer has more electrons, so it will be uniformly distributed in both the areas, n plus and n minus.
No, it is not like that. It is not like that. Okay. Few charges from the n plus layer. Yes, few charges from the n plus layer. Yes, they will cross that barrier. Okay, barrier in the sense n that two layers junction. Okay, boundary we can say. Okay, and they can move into the n minus. Few only. Okay.
Okay, sir.
Right, but
Thank
not the most. Okay.
Okay. Thank
Yes. Any other? Right. Shravan Kumar, do you have any doubt?
No, sir. No, sir. Over. Thank you, sir.
Okay. Yes, Shivraj, what is theta actually? Yes, I will write it in notes. Okay, theta is equal to actually tan inverse of omega L by R. Okay, that is the impedance angle, right? And what is the mod Z, that I will write here, and after that I will upload the notes, right? Okay.
Sir. Sir, could you explain please that extension angle, sir?
Yes.
So extension angle. Extension angle, sir.
Beta.
Extension, sir. Extension angle is beta.
Extinction angle.
Yes, sir.
So, do you want that slide?
Yes, sir. I did not get the point how that inductor is releasing this energy.
Okay. Just a minute.
Okay.
Yes, you want extension angle, no?
Yes, sir.
Hey, these are the yesterday notes. No, okay. Okay, please ask. I'm checking here, but I'm not getting that slide here. Okay, these are yesterday's slides only. Yes, please ask.
Sir, you are told that this angle till which the inductor release energy, sir. I did not get that point.
What I told?
Sir, it is angle till which the inductor release energy, sir.
Okay.
Sir,
So the thing is actually, if you check from 0 to theta, inductor is storing the energy. Is it okay?
Yes, sir. Inductor is storing
Yes
energy.
or no?
Yes, sir.
And after that, what is happening?
Inductor is releasing energy, sir.
Inductor is releasing the energy, right? Okay.
Yes, sir. Yes,
So
sir.
here, from theta till beta only, inductor is releasing the energy.
Yes, sir.
So the
Beta.
instant till which inductor releases energy is the beta, na?
Sir, the instant.
Instant till which inductor releases the energy.
Yes, sir.
Angle means it is not like that. You are supposed to measure from that angle like beta minus theta. It is not like that.
Okay, sir.
Beta is nothing but that angle from 0 to beta. We need to measure.
Okay, sir. Okay.
Are you getting the point? Right?
Sir, we should consider that inductor is charging and discharging also.
We should consider
Both charging and discharging from 0 to.
yes. We should consider both charging and discharging, right?
Oh, okay, sir. Okay.
Okay.
Sir, I have one more doubt, sir. I have confusing to how to define that voltage blocking or based on depletion layer or any other factor, sir.
How to define the voltage blocking? Na? Actually, it is based
sir.
on the width of your n minus layer, lightly doped layer.
Okay, sir.
Right?
Yes, sir.
That defines the voltage blocking capacity of a device.
Okay, sir. Suppose, sir, without there is, sir, it can be voltage blocking is also higher.
Voltage blocking?
Sir, suppose width of a layer is higher, then we can voltage blocking rating is also higher.
Voltage blocking is also higher. Okay, but there should be the lightly doped layer.
Okay, sir. Okay, sir. There should be lightly doped means the resistivity is in high.
Yes, yes.
Okay, sir.
Right. Okay. Okay.
Yes. Thank you, sir.
Okay. Okay. Thank you. Thanks to all of you.